Do you know how chip designers make chips from the range of gigahertz up to terahertz? Welcome to Static Timing Analysis Marathon, where we decode the heartbeat of every ASIC and SoC. From the basics of STA, what it is, how it works, and why it's faster than dynamic analysis, to deep concepts like setup, hold, skew, and clock uncertainty. This series takes you inside the timing calibration of modern high-speed chips. You will explore timing paths, DAGs, false paths, RC delays, and process corners, and then dive deeper into the real tools: Liberty, that is .lib, SDC, SPEF, SDF, and TWF, learning how each files shape your STA flow. But we don't stop there. We go hands-on with OpenTimer, performing real timing analysis, debugging violations, and fixing setup and hold violation in live demo. Stay tuned till the end, because once you grasp STA, you look at the chip design sign-off point of view.
Hey guys, welcome to the first episode of Static Timing Analysis, and in this episode we are going to talk about the series skeleton, STA introduction, types of timing analysis in VLSI, dynamic and static timing analysis, why STA is preferred for ASIC or SoC, how STA works so fast, need of STA concepts when the STA tool can do everything. So in today's episode, we will cover all these points, and let's begin. Series skeleton. This series is tailored in a very specific way. Let me explain how. First, we will discuss about the fundamental difference between dynamic and static timing analysis. During this, I will explain how dynamic timing analysis acts as a precursor to the static timing analysis. Next, we will discuss about the various STA concepts. These are much needed when you analyze the industry standard STA tool output. These outputs are text only, and you have to analyze them keeping all the concepts packed into your mind. Next, we will discuss the way to deal with the standard STA tool output. What are the things that we can analytically derive or infer from the plain text outputs? We will be doing this in a very generic way and not a specific way. Next, we will dive into the text report analysis of OpenTimer STA tool. This is a free and open source STA tool that you can install in your home PC with a Linux operating system in it. I have already created a video to install this in Ubuntu Linux. The link of this installation video is given in the description. Also, I have shown a demo using this OpenTimer STA. I am also providing the link of this video in the description. We are done with this particular slide, so let's move on. STA introduction. In this slide, we will give you a brief introduction to the STA in VLSI. The basic STA algorithm can handle up to 10 million instances, that is 10 million gates. STA does not require input vectors and has a runtime that is linear with the size of the circuit. So like other analysis, we have to create any vector set of input signals have to be written in a such variable way that the input toggles or something like that. But in STA, there is no such thing as input vectors. This is the very beauty of STA. STA overestimate the delay of the long paths. Long means they're physically or delay-wise long path. So STA actually estimates these paths in a more pessimistic way. STA underestimate the delay of the short path. If there is any short path, STA will ignore them. This makes the analysis safe, guaranteeing that the design will function at least as fast as predicted and will not suffer from the hold time violation. So here, in a nutshell, we have just get the picture of STA and why it is used. So we are done with this slide. Let's move on. Types of timing analysis in VLSI. In this slide, you will be introduced to the two types of timing analysis practice used over the varied landscape of VLSI. Now, we start with a chart. Timing analysis. It can be divided into dynamic and static. Now, the word dynamic means the time is involved during the analysis or simulation process. That is, we actively include time by hand in the simulation setup for dynamic analysis. That could be any dynamic analysis. Now we are specific to the dynamic timing analysis. So we are mentioning that we actively include time by hand. That means at the input, somewhere you have to run a sweep or something of time, and you will get an output where the time is also be there. On the contrary, the word static means that the analysis is done in a standstill condition and no time is involved. So this is the very basic difference. So the word static means that there is no time involved, neither in the input files by hand nor in the output files. So there is no time-wise sweep or something inside that. So that's why it is called static. The dynamic timing analysis can analyze the same very thing as per the static analysis, but for a very small design like an IP or a design block. So IP is from the IP vendor, or it could be a design block that in-house has been developed. Sometimes these two words means the same, but as we get these things either from outside, when we are getting it from outside, we call it IP. When we develop it inside, we call it block, or it could be a sub block of a large design block. Okay, so there dynamic timing analysis is used. In contrast, the static timing analysis is performed on a huge circuit such as system on chip, ASIC design, or FPGA. So these are usually very large circuits. So this is the basic difference of dynamic and static scenarios with respect to the timing analysis. We are done with this particular slide, so let's move on. Dynamic timing analysis. Let us take a short tour of the dynamic timing analysis. The dynamic timing analysis is performed using industry standard pure SPICE or fast SPICE or accelerated SPICE, starting from small design block up to the test chip level. In recent days, analog and mixed signal or co-simulation is also coming into the picture. So let's start. Advantages of dynamic timing analysis. It is very accurate. It can check asynchronous interfaces. There is no need to specify false or multi-cycle path. So all these concepts will come into the HTA concept episodes. It can be very accurate through SPICE simulation. It also has disadvantages. Analysis quality depends on the stimulus vectors. That means you have to carefully choose the input vectors, that is the toggling of all the set of the inputs and all the fixed input nodes. So sometimes some input nodes will be fixed value voltages. So all these things have to be carefully chosen. So your analysis will be very much tedious in terms of the stimulus vectors. So this is the very disadvantage of the dynamic timing analysis. Non-exhaustive and virtually impossible to check every path. So this is another, because this is not a topological way. This is a very normal circuit way of analyzing. So it is not exhaustive. It may detect, may not detect, because the vectors that is already defined by the human being, and there is no basically computer intelligence or any software intelligence is used to exhaust all the paths. So that's why it creates a block to check every possible path. It requires long run times because it involves either the true SPICE or the fast SPICE or the accelerated SPICE, but the range of the runtime varies from days to weeks. So it is very much time consuming. After one analysis is over, for the next iteration, you have to again wait for a long time. This can be done only up to the IP or the block level. So whether you are designing a block for that block, or when you club multiple blocks into a larger block, so in that case you can do this. Or if you are having an IP from outside, so in that case you can have the dynamic timing analysis, and all the previous mentioned points will be there. Test chip level needs fast spice or accelerated spice. As I mentioned that the test chip nowadays, for you are doing a design, and many of the design houses have a test chip unit, and they design a test chip to check the functionality of the design block, the functionality that the design block is intended to perform. So for that, the test chips are defined, all the test vectors are defined, and for such large block to run the spice simulation, we need fast spice or accelerated spice. These are the industry only, and I like to emphasize here that these are industry only spice. That means you cannot get them outside the industry. So these are very, very much staying inside the industry, this kind of spice. The next point is the SoC level analysis cannot be done. So that is the roadblock or bottleneck, whatever you call. The dynamic timing analysis cannot be used for the millions of instances, the SoC level or the ASIC level. Because if you look into this slide, there are several points that will eat up, because you cannot write so many test vectors for so many millions of instances. You cannot run them for week after week or month after month. Okay, you cannot, then you will not finish your analysis on time and you cannot tape out. So that's why you cannot apply this on the SoC level. So we are done with this particular slide. Let's move on. Static timing analysis. We have came across the advantage and the disadvantage of dynamic timing analysis. Now let us look into the same details for the static timing analysis. Advantages. Fast design is analyzed in one pass for one clock cycle. This is very, very much fast. Exhaustive and checks all the topological paths in the design. So basically inside the static timing engine, the computational intelligence is used to cover all the possible paths, that is timing paths in the design. From one source point to another end point, the time traversing inside these points, all those paths are exhaustively covered. Does not require the verification environment. So here we are talking about the verification environment, means the previous one. In dynamic, we need a verification environment. There we have to use a kind of set of input vectors defined for everything and blah, blah, blah. All those things, initializing lot of things, all these things. So all these verification environment is not needed. This is very, very much advantageous. Disadvantage. It is less accurate. Must define timing requirements or exceptions. So this is another thing. Although here we do not have to define the test vectors, but we have to define the arrival time and the required arrival time of the signals. So these things we have to define. We will come across all these terms and terminologies and their meanings in their upcoming episodes. Difficulty handling asynchronous designs and false paths. So this is one thing that gives a pain a lot, because static timing analysis cannot be done for the paths which do not involve a clock or a time traversing of a signal. So all these asynchronous paths and false paths, they cannot be analyzed using static timing analysis. So we have seen both the advantages and the disadvantages of static timing analysis. We have made a contrast with the dynamic timing analysis. So we are done with this particular slide. So let's move on. Why STA is preferred for ASIC or SoC? Now let us do the side-by-side comparison of dynamic versus static timing analysis to understand the advantages of STA in SoC or ASIC. So here we go. So let me bring my mouse pointer. Dynamic one, it checks the functionality of the design, whereas static checks the static delay requirements of the design. It is fully spice simulation based and static is fully formula based. That means it involves the computational intelligence. Highly accurate. So this is very, very much accurate because pure spice or fast spice with high accuracy is used, and it is more pessimistic and critical path analysis. So critical path means the pessimistic paths. Okay, this is much more kind of topological. The dynamic one has very slow runtime, whereas the static has very fast runtime. Because why this has a slow runtime? Because it will compute the actual of node by node calculation through SPICE, and hence it is having a large runtime, where in STA we are using a computational intelligence to check all the possible delays and the time traversing inside a circuit. The dynamic is applicable at the IP block level, whereas the static is applicable for the full chip or the SoC level. Some of the industry standard tools like HSPICE, Spectre, Eldo, SPASPICE, all these simulators are used for dynamic timing analysis, whereas for static timing analysis we are using industry standard tools like PrimeTime SI, Tempus, ETS, all these static time analysis tools. Input files. So it requires SPICE models, the circuit file, the SPF or DSPF for the parasitics. Whereas the static timing analysis requires the input files such as Verilog, VHDL, SPEF, SDF, Liberty timing file, that is .lib. Here we can see the side-by-side comparison of the dynamic and the static timing analysis. So they are altogether different, their inputs are different, the tools are different. That by name there is a relation, that is dynamic and static timing analysis, but you can see they are altogether different if we compare side by side and point by point. So the purpose of this slide is done. Let's move on. How STA works first. Now this is very much good question. Let us see how. So far we have seen why STA is preferred. Now you may be wondering how STA works so fast for such a big design such as ASIC or SoC. Let me explain. The IP blocks are characterized by characterization tools such as Liberate. This process of dot-lib generation takes at least a month for any IP vendor for all the standard cells, including all the PVT variants. However, this may take more than a month also if there is some shortage of the tool license. So you have just got an idea how much time does it takes for the characterization data to get generated. Now this creates the skew load delay for each standard cell, that is .lib. Thus, with the manpower and effort spent over multiples of a month, slew, load and various kind of delays are pre-characterized and put into a text format called .lib, which is also known as Liberty file. This file also contains basic information of each standard cell. This is read by ST engine, which also read the design data, that is Verilog, VHDL, system Verilog, timing constraints, that is SDC, user-defined delays, RCCC parasitics through SPEF file are read by ST engine. All these inputs are processed by the STA engine in less than an hour. Finally, the STA tool hands over the text report to us and we have to analyze the same using the STA concept. So guys, you have seen the entire flowchart of the basic data generation and using of the data for static timing analysis. Now, from this picture, you can see that the very much pre-characterized data comes from the .lib. Rest of the data which are of the design comes from the Verilog, the VHDL, system Verilog, then SDC, then user-defined delays, RCCC from SPEF. All these things are ready. Means all these things are ready for the analysis of the ST engine. The ST engine uses its computational intelligence to exhaustively search for all the paths, all the combination of the paths, and from there it reports the timing violation. And these timing violations are very much important for the chip to be qualified for tape out. That means before the tape out, we have to clear out all these violations. So we are done with this slide. Let's move on to the next slide. Need of STA concept. In this slide, we will explain the need of STA concepts. We have to analyze the STA violation through various STA concepts such as first, the critical path analysis. Critical means the pessimistic paths here in terms of time traversing in the circuit. Next is the clock to queue delay. So these are pretty common thing in delay analysis, that is clock to queue delay. The next one is register to register delay, reg to reg delay. The next one is AT versus RAT. AT means arrival time, that is actual arrival time of the data for various gates and nets, and required arrival time means which is defined by the designer. So this is the required arrival time and we are comparing it with the actual arrival time. We'll come up later on this series about the details. The next is on-chip variation, OCV. So OCV nowadays is very much important because of the process variations and all. So these data usually stays inside the dot clip as a OCV variation, and we need to analyze these OCV variations also in the output. And there are many more things. So all these concepts come as a text output, and you have to use your human intelligence to go to the root cause analysis of which particular category of failure is happening and from where it is happening and how we can prevent that. So that is the main goal of a static timing analysis engineer. Thus, we point out the problem zone of a ASIC chip and rectify the timing violations before signing off or tape out. So we are done with this particular slide. So let's move on. Hey guys, welcome to the second episode of static timing analysis in VLSI. In last episode, we have seen how STA works so fast with respect to the dynamic timing analysis. In this episode, we will broadly focus on the input-output of STA and the timing calculation of the STA engine. So today's menu is STA in the design flow in ASIC or SoC, STA engine input-output at a glance, STA output terminologies, timing expectation versus reality check, what is a timing analysis path, types of path under STA scanner, directed acyclic graph DAG concept and example, maximum and minimum path concept. So without any further delay, let's begin. STA is used only in digital design. There could be pre-layout STA, but the most significant is the post-layout STA. With the help of a flowchart, we will understand the position of STA in the chip design flow. First, we have our design specification, and in this direction the flow will go. Next, we do the RTL coding as per the design specification. Next, we do the verification of the RTL code that we have written. Next goes the synthesis, then the floor planning. Next, power routing. Here we enter in the backend part in the floor planning and power routing stage. Then comes the global placement. Next comes the detailed placement. Next to it comes the clock tree synthesis. Now our flowchart will move on the right hand side with the arrow, and the next step is global and detailed routing. The flowchart will now move upwards. Layout generation or changes. Next comes the DRC and the LVS. At next stage, once the layout is done, we do the parasitic extraction for a DRC and LVS clean layout. Next, when our parasitic extraction is ready, we do the static timing analysis. And do remember guys, this is the backend or post-layout static timing analysis. Now at this stage, if we find a violation, then we go back to the place and route stage. If we do not have a violation, then the design is ready for tape out. So from this chart, you can see that static timing analysis appears at a very crucial level, and this is very much important for the tape out. So many times you will see that in many of the books or online literature, this is called as a sign-off process. So sign-off means the design by the designer and the verification team, they are signing it off for the tape-out process. So that's why the static timing analysis is a sign-off process. We are done with this particular slide. So let's move on. STA engine input-output at a glance. In this slide, we will get familiar with all the inputs and outputs of static timing analysis engine. These are very important for your knowledge base. Here we have infographics for you. This is the static timing engine, and you can see its direction goes shorter in the below direction. So above it will be all the inputs and below it will be all the outputs. Our first input is synthesis tech library. So guys, basically this comes from the foundry and inside the PDK, and this tech library has all the foundry definition of the gates. Next input is gate level netlist. This is designed by the designer team who are designing it at the pre-layout level, that is in the RTL level. This is basically from the front end part. Next input is SDF. So it contains the delay and it is also a file extension. So it contains all the designer defined delays. The next input file is design constraints in Tickle. Okay, it is also called a SDC file, and here we give all the timing constraints for the STA engine. Next, we have all the pre-characterized data for all the logic gates in the standard cell library. This is the timing model library, also called the .lib or the liberty file. So in this, all the pre-characterized data for the entire set of standard cells are there. Next, we have the output. The first output is AT or RAT. AT means arrival time, RAT means required arrival time. We'll see some slides later about this AT and RAT with a detail. Next output is report or histogram. So STA engine do a huge amount of text reporting. Also, it gives us the histogram. So we will count what all the types of outputs in this report later on. The last one you can say is the design data. Now, this design data comes through the Tickle interface. And in case you have not seen the first episode of Tickle in this channel, the link is given in the description. So you can go there and see the episode. I have explained there with vivid detail how this type of design data is processed through the STA engine APIs. So here we have the entire picture of what are the state of inputs and what are the outputs of a STA engine. We are done with this particular slide. So let's move on. STA outputs in detail. We have just seen all the input and output of STA. Now we will discuss about all the types of timing violation that comes in the output report of STA engine. So these are register to register delays, setup time check of all external synchronous inputs, hold time check of synchronous outputs, clock to Q, that is clock to output delay, pin to pin combinational delay, different analysis modes such as best, worst, typical, on-chip variation, that is OCV. The list has not exhausted yet. To continue, here we go. Data to data checks, case analysis, multiple clocks per register, minimum pulse width checks, derived clocks, clock gating checks, netlist editing, report clock timing, clock reconvergence pessimism, worst arrival skew propagation, path-based analysis, debugging delay calculation, and many more. So we are done with this particular slide, and this is a kind of exhaustive list what all things we can expect in our text output of the STA engine. So let's move on to the next slide. Timing expectation versus reality check. What we mean? We'll discuss about the expectation versus reality check process for STA delay estimation versus verification. The designer designs a circuit keeping some predefined delays as estimation so that the design operates at desired gigahertz speed. In STA, we use a method called directed acyclic graph to serve this purpose. Let us see how. So we have estimated delay by a designer that we are just picking, and we have to compare it with the calculated delay, that is the actual delay coming from the STA engine. To do this, we have to superimpose the two things by some method. This is called directed acyclic graph. Now, this directed acyclic graph is a timing path or a set of timing paths. So this graph is realized on the timing path. We will see how. So this is the concept here. We are done with this particular slide. Timing analysis path. Path means reaching from one point to another point to net by going through logic gates, flip-flop, etc. But there is a catch. Not all such paths are called timing paths. So let us see which paths are called timing paths among all the paths in a design. So here we have a picture of a timing path, and in this picture we start from the left. Our path starts from a clock, goes through a flip-flop which is yellow color. Let me bring my mouse. So here starts from the clock, it goes through a flip-flop, then it crosses the AND gate, then a OR gate, then a MUX, then a XOR gate, and ends up in the data pin of another flip-flop. Any path subject to the timing analysis which start at a source of the clock, ends at the D pin or data pin of the flip-flop. This is called typical timing path. So we are done with this particular slide. Let's move on. Types of path under STA scanner. We have a clear concept of timing path now. We move forward in this slide to get familiarized with 4 types of timing paths that a STA engine considers during its analysis. Here goes our graphics of a chip. Now let me one by one define the 4 types of timing path. First, input to register. You can see the label in the right hand side graphics of the chip. Next is register to register path. Also the label comes up on the right hand side. Next comes the register to the output path. The label is also shown there. And the 4th one is input to output. These are the 4 types of paths. So here, let me do a clear demarcation. From here to here is 1. From here to here is 2. From here to here is 3. And from here to here is 4. For rest of our STA series, we will deal with timing violation of these 4 types of timing paths. Remember it. Now, if you focus here, each path has a start point, a end point. There will be a calculated value of the delay. So guys, we'll see in further slides the actual example of such path. We are done with this particular slide, so let's move on. What is directed acyclic graph? As of now, we are familiar with the timing paths. Now let us superimpose the directed acyclic graph on it. We will use the below graphics for this purpose. So here our graphics is come on the screen. This graphic shows 2 starting point at the extreme left, this, and one end point at the extreme right. So this is that point. In between, we have multiple logic gates connected as per the design. Here the gates are treated as nodes and nets. These are nets. This is a net. This is a net. This is a net. Nets are treated as links of the graph. So basically, when we draw a graph, we constitute a graph with nodes and links. The nodes are here the gate and the links are here the net for this directed acyclic graph. So let me bring up this text. Netlist is represented in form of directed acyclic graph, also known as DAG or DAG. Delay values are associated with nodes, cells and links. That is, nodes are cells and links are nets, as I have shown in the graph. Total path delay is the sum of the path delay values. We'll see in an example. First, all the possible topological paths are extracted. Next, for each path, calculates its delay and compare it with the endpoints values, that is the required values. So this is how our comparing is done. So we are done with this slide. Let's move on to the next slide. Directed acyclic graph example. Let us now take one example to understand the directed acyclic graph. Here goes our graphics, and before that we have AT, which is arrival time, and RAT is required arrival time. These are abbreviation. I keep the full expression of them here. Here goes our graphics. This is same as before, but we will add delay to each element now. Let me bring up the delay. So before delay, AT is equal to 2. Here AT is equal to 5. These are the arrival time delays. Here we have 2 inputs. One has 3, another has 1. For this one, we also have 2 inputs. They have 2 and 1. Here we have 3 and 1 for the 2 inputs. In the final gate, we have T and 2 for the two input nodes. Now we define RAT, that is required arrival time, is equal to 10. So now let us calculate the total values. This is how we calculate. 2 plus 2 plus 3 equal to 7. So here is the first one. 2 plus 2 plus 3 is equal to 7. So this is okay because here it is within the RAT range. Okay, what you have specified as RAT, it is within that specific range. The next one we bring up is 2 plus 3 plus 1 plus 3 equal to 9. So 2 plus 3 plus 1 plus 3 is equal to 9. So this is again within the required arrival time. So it is okay. This path is okay. Next we have 2 plus 3 plus 3 plus 2. 2 plus 3 plus 3 plus 2. So this is equal to 10. And this is also okay because it meets the RAT. The next one is 5 plus 1 plus 1 plus 3. Now here 5 plus 1 plus 1 plus 3. This path is not okay. The next one is 5 plus 1 plus 2 is equal to 8, and this path is okay. So here we have shown the example of a directed acyclic graph, and we have seen how the calculations are done on this graph for the AT or the delays that have been defined and the versus the RAT. So we do the AT versus RAT comparison and we point out the path which has problem. That is which is not okay for the timing. So we are done with this particular slide and the example. Let's move on. Maximum and minimum path concept. So far we are clear enough with timing path, its representation as directed acyclic graph. Now we will get familiar with the concept of max path and min path. We will take the help of this graphics for our understanding. So I have bring up the graphics. Here you can see from the left what we have. Here we have a flip-flop, then here we have a OR gate, here we have a NAND gate, here we have a NAND, we have a NOT, here we have a OR, here we have a XOR gate, here we have a flip-flop. So here in the graphics we can see that it is highlighted as the minimum path and here it is the maximum path. Now let me bring up the text. A max path is not the physical maximum length path. So physical length means how much long the path is. It is not like that. It is with respect to the delay. So here it is the maximum path. In red we have written this. This is the maximum path. A minimum path is the path with the smallest delay. So here we can see the minimum path. So here, since in this path most number of gates are there, so it considered as a maximum path, and here we have the least number of gates and the delay, we call this a minimum path. So guys, we are done with this particular slide. Hey guys, welcome to the third episode of static timing analysis. In last episode, we have talked about the directed acyclic graph, which deals with the AT and RAT. In this episode, we will discuss about various delays which affect these AT-RAT check in actual circuit. So here goes our menu for today. First, we talk about STA delays. Next, we will talk about propagation path delay. We will explore physical path delay. We will talk about pre-layout net delay calculation. We will talk about designer defined delay. We will talk about post-layout net delay. Next, we will talk about cell delay calculation. Next, we will discuss rise and fall skew concept and example from .lib file. So this is the menu for today. Let's begin without any further delay. STA delays. So let us get familiar with the delays in STA. In static timing analysis, STA, static delays such as gate delay and net delays are considered. In each path, these delays are compared against their required RAT, maximum and minimum values. The actual path delay is the sum of the net delay and the cell delay along with the timing path. Don't worry, we'll explore these things in subsequent slides. Net delay is the total time for charging or discharging all the parasitic. It is a function of parasitic R and P or coupling capacitor. Next, cell delay is the delay arc corresponding to the input and output ports of the cell. It is the function of skew, load, and process parameters. Where load models, WLM, are fetched from the technology file. We are done with this particular slide, the introduction to the all ST delays and their different kinds. In subsequent slides, we will explore them one by one. Propagation path delay. In this slide, we will discuss graphically the basics of delay calculation. In any and every type of delay are defined or measured using this method at the bottom. Then they are put into some text format to feed the STA engine. So let me bring up the graphics. Here goes our graphics. This is input waveform, this is output waveform, and this is a 50% cut. This is the 50% cut. This is TF and this is TR. Here you can see that there are two waveforms. The above one is input waveform, which is generally called the reference waveform. The below one, which can be output of a logic gate or an IP or simply a design block. Whatever it is, the delay is measured on it. We can see in both the cases that there is a horizontal dotted line. See, this is the horizontal dotted line which cuts the waveform at 50% height. So if I consider this is the height from here to here, it cuts at the 50%. In both cases, it is the same. The y-axis, that means in this direction, is the voltage, and in the x direction, this is the x direction. X-axis is horizontal direction, is time. So we have voltage in this direction and time in this direction. So when we drop a perpendicular line from these cut points, say this is a cut point and we are dropping the line here in the x-axis, we get intersection points. So these are intersection points. 1, 2, 3, 4. As I have mentioned earlier that the delay is calculated at the output waveform. Hence, this is called the fall time delay. So you can see here is the first cut and the second cut is dropped in the x-axis. We can measure it because due to the circuit operation, this waveform has just flipped vertically, and we are considering the 50% of this point and 50% of this point and dropping on the time axis so that we can measure the time shift. So this is called the fall time delay. And similarly, if we drop here at the x-axis and again here we drop, so here it is also got flipped, but from 50% to the 50% we are measuring here, and this is called the rise time delay. Now you may be wondering why we need both. In general, the slope of the rising and the falling edges are not same for a single waveform due to the design or the presence of the parasitic resistor, capacitor or coupling capacitor. So guys, here I have drawn the picture very much identical in real circuitry, these two slopes. So that means this slope and this slope will be different, and again this, when it passes through a block, this slope and this slope also will be different. So expect this thing in real cases. We are done with this particular slide, so let's move on. Physical path delay. In this slide, we will zoom into the delay a bit further to understand from where physically it is coming from. Here is our total delay. It can be divided into two parts. One is the net delay. Net means the interconnects which connect all the logic gates in the circuit. And the cell delay. Cell delay means the logic gates. They have their intrinsic delays. The net delay is caused by the interconnecting net or metal or via routing at the layout level. It can be subdivided by the delay caused by the individual existence of a capacitor or coupling capacitor and a resistor or a resistor. That means both can be there. So P and R or C or R, all these combinations are possible for the net delay. The cell delay comes from the physical standard cells which have a circuit component as well as the metal 1 and metal 2 routing in it. So these cells are pre-characterized by the Liberty characterization tool to calculate input slope, output load, for various PVT corners. The cell delay varies from one type of the cell to another type of the cell. Also for the same cell, it varies when we change the cell height. As an example, I can say 60, 70, 90 and 12T. Here T means the metal track width. So when you deal with the standard cell, you come to know about the cell height, which is measured in terms of track. So these are different track and height. So even a single cell is there, it's all the delay values for it will be different for different track, and these cells are also packaged in different files. So the all possible permutation and combination of the cell height, process, temperature, and operating voltage, etc., gives birth to a huge amount of data mining, which is captured into the .lib file for any standard cell library. So guys, I think we have talked enough on this slide. So let's move on to the next slide. Pre-layout net delay calculation. Before reaching to the layout, verification is done at the front end. Here, the designer needs to define the delay to check the AT versus RAT at even synthesis stage. The designer defined or hand calculated delay is called the wear load model. In this slide, we will talk about this. Wear load model. The net length is a function of the net fan out and chip area. So fan out, you know how many output it can drive, and the chip area is the physical area. For a given area, averages of R and C are estimated for different fan out. Then net delay is calculated simply as the product of R and C. This is how the wear load model is generated. Now let us look into an example here. Let me bring my mouse pointer. Here I have given fan out in the first column, P value in the second column, R value in the third, and finally the product, that is the wear load model, is in the fourth column. So delay is equal to R multiplied by C. So if the fan out is 1, we have the C value is 0.015 and the R value comes as 0.012. Now the wear load model predicts the delay as 0.00018. If you multiply these two things, and you will get this result. Similarly, if the fan out is 2, the C value is 0.030, R value is 0.016. If you multiply them, this result, that is 0.00048, will come. So this is the delay in this case. The third case, here the fan out is 3. The C value is estimated as 0.046. The R value is here the 0.020. Now if we multiply these two, the outcome is 0.00092. So this is the wear load delay modeling. So I have given the theoretical as well as an example to understand the wear load model. So we are done with this particular slide. Let's move on. Designer defined delay. In last slide, we have talked about the wear load model. Now let us see how and where a designer can put these delays to feed them into the STA engine. So designer defined delay here, it can be filled into first the design constraint file, second in the SDF file. We have already talked about the all input outputs in STA. And there I have touch base these two files as the input. Here, these two are text file, and the designer can include his defined delay into these two files. So manually, these can be entered also. We will have a series coming up next after this particular STA series, which is currently going on, where we will deep dive into the technical details of these files formats used in STA analysis. So stay tuned, stay focused. You're done with this particular slide. Let's move on. Post layout, net delay, RC back annotation. So far we have talked about all the pre-layout delays. In this slide, we will enter into the junction point where the front end meets back end. Through infographics, we will explain how designer designed netlist catches the tough and cold of parasitic RC when its layout is realized. So here we go. This is our pre-layout circuit. When we realize the post-layout circuit after the layout and we extract the SPEF, DSPF, SPF, SBPF, etc., whatever you call, the post-layout netlist comes as like this. Can you spot the difference? Yes, the difference is here and here. So these are the parasitic resistors that have been added. I have not complicated the structure with parasitic capacitors, but they will be still there. So it is just to exemplify you. So you can see that, let me bring my mouse pointer. In such circuits, what happens when there is a post-layout netlist, the SPEF is created. These nodes, this is a node, this is a node, this is a node. So such nodes will generate multiple subnodes. These subnodes will be connected to the parasitic resistor, capacitor, and coupling capacitors, because These are metal routes in actual practice, and there will be the coupling capacitor will show the neighboring effect. So here I think the picture speaks for itself, and this picture also. In ST only, the SPEF or SBPF is used as these contain the information about nets only, as cell delay are picked up from .net. So just for your information, I have dumped all the formats of the parasitic files, but in case of STA, SPEF or SBPF, SBPF is the binary format. It cannot be read by human. SPEF is the text file, so it can be read by any human being. So either SPEF or SBPF is used in STA. So these are not used, but just for your knowledge purpose, I have put it there. So we are done with this particular slide. Let's move on. Cell delay calculation. SPEF is for the net, and for the cells, the design, we have the .lib that will contain the delays. Now, the delay modeling inside the .lib file is done using these three different ways. Here goes our cell delay modeling, which is done through the .lib characterization, and there are three different delay models are there. NLDM. NLDM means non-linear delay model. Here we use lookup table and interpolation method to find out the required delay. The next one is CCSM. CCSM means composite current source model. Here we use driver and receiver model to define the delays. The next one is ECSM, which means the effective current source model. This is the first and only open standard current source model which is well accepted in the industry. So we are done with this particular slide. So let's move on. Skew, rise and fall. In this particular slide, we will discuss about the most important element in STA, that is skew. We will take the help of an infographics to understand it properly. So here, this is our graphics. Now, let me bring my mouse pointer. So here you can see the waveform is rising. Here it is flat, and then it is again decreasing. So I have intentionally kept the two inclination different just to show you that in real life, they may be different. And I have also exemplified the different kind of threshold, right? Here 10%, here 90%, here 20%, and 80%. So these kind of threshold, that is lower threshold, upper threshold. Again, here it is upper threshold and lower threshold. So these type of various threshold values are kept in the industry and in different files as per the design, and many other factors are there controlling them. Now, if we cut a waveform here at 10% and here at 90%, why we are cutting? The reason is that here this is not straight and then bends directly, because it is a capacitive action, so there will be a continuous bend. So we have to cut it somewhere. So just to get a flat inclination. Okay, this one. So this is called the rise sleeve. So here our threshold at 10% to 90%, our rise sleeve is measured like that, and our fall sleeve, again here it will be capacitive action and it will be a bending. Instead of a sharp bend, it will be a continuous bending, and to accommodate a direct slope here like this, we have to cut it at 80% and 20%. And here in the time axis, we measure the fall sleeve like that. So this axis Y, it is voltage, and this axis, this is time. So here we measure the rise sleeve, and here we measure the fall sleeve. So although I have hard coded the 10 and 90% and 80 and 20%, it is not the thumb rule that this is for rise and this is for fall. So any combination can come out. So both can have 80-20 values here, both can have 10-90 and 10-90 here, and they can be different, or 80-20 in the rise sleeve or 10-90 in the fall sleeve. So there could be multiple combinations. So don't just have this only picture, but try to understand the concept where these sleeves are meant. In STA, the rising or falling waveforms are measured in terms of whether the transition is slow or fast. So this sleeve means that how much fast the transition is, that is from 0 to 1 or 1 to 0. The sleeve typically measured in terms of the transition time, that is the time it takes for a signal to transition between two specific levels, that is the 1 to 0 or 0 to 1. In the .lib file, the sleeve thresholds are defined in the particular fashion. Let us see an example. The falling edge threshold is defined as sleeve lower threshold PCT fall, that is then colon, then 20.0, and this line ends with the semicolon. Similarly, for skew upper threshold PCT pol. So this is pol skew. Let me bring my mouse pointer here. We are talking about pol skew, and this lower threshold is 20% and upper threshold is 80%. So here what we have depicted in the picture, the same thing you can read in text format in the .lib file. Now rising edge thresholds, skew lower threshold PCT rise. So here this end. So you can see here our threshold is cut point is at 10%. Now skew upper threshold PCT rise is 90. So this is at the 90%. So this is the way of representation inside the .lib file, and this may similar commands may be there within the STA tool also. So they may be exact or they may be a bit different, but this is the way of representation of the skew cut point. So we are done with this slide. Let's move on. Rise skew versus delay from the .lib. In this slide, we will exemplify the lookup table for rise skew versus delay in NLDM model of .lib. Here you can visualize the 2D lookup table LUT from which the STA engine picks up the delay. In case an exact value of the index is not found, then the STA engine does the interpolation technique to find it out. Here the computational intelligence of STA engine can be observed. So let me bring up the details. Here we are using the NLDM model, so I have highlighted. So first there will be a template. Template means this is a kind of prototype where we define the shorthand of the things. Variable 1 total output net capacitance. Variable 2 is the input net transition. So this is the first one is generally the row variable and the second variable is the column variable. Now index 1. So this is a 5 by 5. So we have defined 5 indexes here, and index 2 we have defined 5 indexes there, and we close the template. So this template will be way up in the .lib file, and the next table, which is the actual table, that may come inside a particular cell. So this particular LU table template is common for all, but the actual template or the actual data for each cell will be different, and that will be in the inside each cell's definition inside the .lib. So let us see such example also. Rise transition, this will be definitely inside a cell. Then delay template 5 by 5. So we have a 5 by 5 table here. Index 1. Now you can see that index 1 has again 5 values, but they are different from the initial values. So these are actual values of the cell. So these overrides the initial template values. Index 2, which is the column index, and index 1 is the row index, again has a 5 different values than the template values. So this overrides the template values whichever earlier was defined. Now we start the table. This is our first row. Here goes our second row. Each has 5 candidates. Third row, fourth row, and fifth row. And here we close it. Let me bring my mouse pointer in to make you understand the things. So here our first row index is there, 5 values is there, 1, 2, 3, 4, 5. So they will keep just above here, 1, 2, 3, 4, 5. You can do an imagination, and the column values are the 1, 2, 3, 4, 5. So they will be here 1, 2, 3, 4, 5. So if we have to pick the value for this combination, this and this combination, that will be the first one. And similarly, we can move ahead and find a value. It's like you find a point in XY graph, right? You move to some X values, then you have some Y values like Cartesian coordinate, which has a X and Y kind of thing. So this is very similar. This table is very similar to that kind of interpretation. And now the question is, if there is a value lying in between here. So index 1, so we have actual case in actual simulation time, we have some values lying in between the first value and the second value, and there is another value which will be in between these and these values. So how to get that? The STA engine will use a numerical method called interpolation to find that value out, and it will find out. So these values are characterized keeping in mind that well extreme values, okay, so that it covers the entire spectrum. So there is an entire spectrum is covered here and entire spectrum covers here. So anything will come in between all these values. So if it is on the point, so this point and this point, the ST engine will find out the exact value. So this one, and if it is there some intermediate value, it will do the interpolation. Now the things are very much clear that first the template is defined, it is way up in the .lib file, it is common for all the cells. But when we have a particular cell definition, we have this kind of table. So the name is common here, delay template 5x5, delay template 5x5, and the case is here the rise transition. So we are done with this particular example or slide. And let's move on. False view versus delay from the .lib. In this slide, we will describe the 2D lookup table, that is LUT, of false view versus delay from the .lib file. This will engrave the 2D LUT concept totally into your mind. Let me bring up the text. So again, I am highlighting that we are using NNDM model here. And here the template begins. LU table template, delay template 5x5. So we have 5 rows and 5 columns. Variable 1 is the row variable, that is total output net capacitance. Variable 2 is the column variable, is the input net transition. So here the first set of indexes, these are initial values. And again, these are 5 set of index values for index 2. And now just again I emphasize here, variable 1, the value variation is index 1, and for variable 2, the value variation is index 2 variation. Now we close the template here. In actual cell, we will find the fault transition table, that is 2D LUT, which will be like that. The name is common, the delay template 5x5, and the name is fault transition. And here we will see that index 1 has its actual or local values, which is for that particular cell, and this will override whatever we have defined in that table template. Now again, here we have the second index, that is column index, and here we also have 5 values. And here we start table. Here goes our first row, second row, third row, fourth row, and fifth row, and we close the entire block. So here again, these values will sit here, 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 and here, and these values will sit here, 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 and here. So this is a kind of table that helps you to get the delay values, not you actually, the STA engine. The STA engine will calculate the delay values either from the fixed point values for the XY coordinate kind of stuff. It will find the exact value. If it doesn't find the exact value, it will do the interpolation. So guys, I think we are done example here, and now the 2D LUT concept has engraved into your mind. Now you know how STA engine picks up the cell delay values. So we are done with this slide. Let's move on. Hey guys, welcome to the 4th episode of STA. In previous episode, we have talked about various delays. In this episode, we will talk about multiple timing concept, which will help you to understand debug and root cause analysis in the STA report analysis. So today's menu is, first we talk about clock latency and skew, then setup and hold time concept, setup constraints from timing.lib. Next, we cover hold constraints from timing.lib. We talk about setup equation concept. We talk about hold equation concept. We talk about multi-cycle path concept. And finally, we talk about half cycle path concept. So this is the menu for today. Without any further delay, let's begin. Clock latency and skew. When we work with any STA engine, we need to provide some initial constraint to be used during the STA engine run. Clock latency is such a factor which we need to initialize. Often, the clock skew concept is entangled with the clock latency to strike out the difference between the two. Hence, we will talk about both side by side in this particular slide. Here comes our graphic. Now, let me bring up the mouse to describe the graphic. Here, it is our clock source. Here, clock tree is there. Generally, this is done at the clock tree synthesis stage. Now, you can see these are buffers. I have colored them to just for the distinctiveness. And here you can see there are the 3 different flip-flops, 1, 2, and 3. These are also colored in different colors to become very much distinctive. Now, let me bring up the text. Clock latency is the clock traversing time between source and endpoint. The latency in STA engine can be fine-tuned for the clock source various conditioning such as rise, fall, min, max, and early or late. So for all these conditions, the latency can be fine-tuned for the clock source. Now, if you see in this picture, here the clock starts and it reaches to the different branches to different flip-flops, and our clock latency is measured from the clock till the same point of each of these branches. So this is the clock latency. So this is basically the time that the clock takes to traverse from its source point to any of the branch. Clock skew is the difference in arrival time in between two endpoints of the clock tree. It is the outcome of the clock tree synthesis. This is how we define it. In actual practice, in the STA tools, we define the clock latency with this particular command. Now, all the texts are there. Let me again point to the clock skew. So, the clock skew is the difference in arrival time in different branches. So, from branch 1 to branch 2, from branch 2 to branch 3, or we can calculate from branch 1 to branch 3. So, if there are many more branches, so we can calculate in between any of the two branches the difference in the arrival time. Because here it is very simplistic figure, but when we actually deal with a circuit which has millions of gates, this clock tree branching will not be very much simple, and there could be clock gating also. This is the definition and simplistic figure just to keep a snapshot in your mind. So this is clock latency and these are the clock skew. So we are done with this particular slide. So let's move on. Setup and hold time concept. The setup and hold time is the key factor in STA. These two can be found in violation report of STA engine output. So you must have the concept to debug and root cause analysis. So let me bring up the infographics for the concept. As you can see, the graphics contain two flip-flops. These are called launch flip-flop and capture flip-flop. So I have distinctly colored them. The launch flip-flop is green and the capture one is pink. In between these two, there is a blue colored symbol, which is basically a symbol of a cloud. This represents the combinational circuitry through which the data traverses from launch flip-flop to capture flip-flop. Below, there is a timing diagram to visualize the data and clock transition side by side. So this diagram, we have clock here and we have the data transition. And if you look carefully, we have placed the hold and the setup markers here for this hold and setup time nearest to the respective flip-flop in the definition. Setup time. This is the cushioning time for which the data must be stable before a capture clock transition happens in the capture flip-flop. Now guys, let me bring the mouse pointer. Here we are talking about the setup time. You can see the capture flip-flop must get a time cushion as I am pointing with my mouse before the capture edge of the clock hits the capture flip-flop. This is the capture edge at the capture flip-flop. So this cushioning time lets the capture flip-flop to set it up for the capture of the arrived data. So data, you can see data is arriving through this path, and this particular capture flip-flop will make itself ready to receive the data. Hence, we call it the setup time. That means the capture flip-flop is setting itself up for the data. So hence, this particular time cushion which we are providing is termed as setup time. Any change in the data inside the cushioning time termed as violation. So you can see the data variation is happening here and not inside this particular cushioning time. If this data transition, this data is getting transition here. If this happens within this time cushion, in actual circuit, the STA engine will catch it as a setup violation. Hold time. Cushioning time for which the data must be stable after a launch clock transition happens in the launch flip-flop. So now let us come to the launch flip-flop and we are talking about hold time here. So here you can see that this cushioning time, this particular cushioning time after the launch edge of the clock has arrived. So this means here this is the launch edge of the clock and we are providing additional cushion here, which is the hold time, helps the data from flip-flop, this particular flip-flop means launch flip-flop, helps the data from the launch flip-flop to jump and run into the data bus properly. So this is basically the data bus. This time cushion for which we are holding the data stable helps the data to jump into the data bus and run stable. Thus, the data is held stable for the cushioning time for successful launch. After this cushioning time, we can see the data gets changed in the input data bus. This change is okay. The change in the data inside the cushioning area is flagged as the hold violation. So we can see that we are holding this data line stable for this particular time cushion and the data jumps into the data bus properly. And after a certain time, this much time, the data start to change, which is okay. But if this transition is happening within this particular cushioning time here, the STI engine will catch it as a hold violation. So we are done with this particular slide. Let's move on. Setup constraints from timing lead. In last slide, we have talked about the setup and hold time. In a design, there will be millions of logic gates, flip-flop, and other various standard cells. Now that for all these cells, where does the setup and hold constraints come from? How do STA engine gets all the data? In this and the next slide, we will discover. In this particular slide, we will talk about the setup constraints that a STA engine reads from the timing.lib file. So let me bring up the text. LU table template, setup template. The name is setup template and the dimension is 3 by 5. Variable 1, related pin transition. Variable 2, constrained pin transition. First index, that is index 1, which is corresponding to the variable 1, has 3 values. You can see 1, 2 and 3 values. Next comes the index 2, which is having 5 values. So you can see the 3 by 5 table, the row and columns will contain 3 versus 5 values as the row and column indexes. And we close it here. I'd like to emphasize here, this is a particular template that is a prototype. This arrives at the very early or the top of the .lib file. And when we have a definition of a particular standard cell, inside that we will have the exact table. So let me show it to you. Inside each cell, there will be a timing block, inside which there will be first the pin, which is a related pin, will be marked as related pin clock. Then timing type is setup calling. Rise constraint, setup template 3 by 5. Now you can see the actual table, the lookup table comes here. Here are the index values of the row index, that is P values 0.06, 0.3 and 0.6. Next is the index 2. It has 5 values 0.06, 0.18, 0.42, 0.6 and 1.2. So these 3 correspond to the 3 index values here and 5 index values are here. So let us have the table now. Values like that is this comes the first row, second row, third row, and we close it. Now you can see, let me bring my mouse pointer. 1, 2, 3. These values will be in the row 1, 2, 3 and 5 values 1, 2, 3, 4, 5. These will be column indexes. Now let me tell you that what this thing is all about. We can see the related pin transition and the constraint pin transition. So here generally we are talking about the related pin, right? So related pin is clock and this table comes under a particular cell and for a particular pin will be there. So that will be the constraint pin. Now, we also have a similar table for the fall constraints. So we have a rise and fall constraint. Similarly, here the 3 indexes for the rows are 0.06, 0.3 and 0.6 and there are 5 column indexes here. And next comes our table, first row, second row, third row, and we close the table. And we finally close the timing block. So this timing block will appear inside the .lib file deep down. for each particular standard cell. Now, you know that any particular standard cell means it could be a logic gate or it could be some other particular standard cell. So when the ST engine reads the dot lib, it gathers all this data and it have a mapping of this timing will count for a particular pin of a particular cell and with respect to the pin clock. So if we say this is for Q, right, the clock to Q transition. So clock to Q delay values, we will have the transition values. So we know that these are related pin transition, means these are clock transitions, and say if it is Q, so for Q transition. So we have the clock transitions here and we have the Q transitions here. And for each combination, there could be one value coming. The ST engine will manage the calculation. How? Now, if these indexes are exact values, then they will find the direct values. If some value is in between, so if there is a value between this and this and this and this, some value here and here, what the ST engine will do? It will use a numerical method called interpolation and find out the value. So here when this table is characterized during the Liberty file characterization, all the extreme values, so from here to here if we come diagonally, all the extreme values are covered in this table so that we have all the extreme values. And as you know, any particular dot lib is generated for various PVT conditions. So definitely for each PVT there will be a different dot lib. Thus we get all the combination for all the kind of PVT variations. Now the ST engine have all these data inside, and when it dynamically calculates, right, the delay for different paths and all for the AT, RAT factors that we have explained already in previous episodes. All these factors the ST engine judge from the data that reads from the dot lib. So that is a very important factor to have all this data in the dot lib, and this is how we are relating the setup and hold concept and the corresponding constraint that is coming from the dot lib. This will be used in the actual ST engine when it runs, but whenever this run is happening, it will happen in a blink of an eye. We are done with this particular slide, so let's move on. Hold constraints. In this slide, we will explore the hold timing constraints from the timing dot lib. Now here again, we have first the LU table template, and it is 3x5. So first variable is related pin transition. Variable 2 is a constraint pin transition. And here comes our the row index. And here comes our 5 column index, because the table is 3x5. As you can see here, 3x5. So 3 and 5 values are there. And here we close our table template. Again, I am mentioning this will be way up at the very beginning of the dot lib where you find all these templates. You can also have a similar word prototype of a table. Here we get the prototype for the row and column values. But in actual practice for each cell, the actual data will come into the timing paragraph, you can say. So, or the timing block. And these hold constraints are like this. This is a one example. Related pin is clock. Timing type is hold calling. Rise constraint hold template 3x5. So this is rise constraint. And this will contain a 3x5 table. Row indexes. These are actual index values and these actually overrides. So these three values are actually overriding these three values for that particular cell for which we are having this data. Next, we have 5 column values here and we start the table. So first row, second row and third row, and we have 5 corresponding columns. So our 3 values, 1, 2, 3, they sit here, 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 and these 5 will sit here, 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 here. So there will be 5 values. 1, 2, 3, 4, 5 here. Again, we close this particular rise constraint table, this lookup table, and next we have the fall constraint. Index 1, index 2, we have row and the column index values, and we have the first row, second row, third row, and we finally close it, and finally close the timing paragraph or the timing block. Here we have the hold constraints from the dot lib. Again, I will say that this will be for each and every standard cell, and they will be present in the .lib file. And for this reason, you can see the .lib file will be very, very huge in text format. If you open up with editor like GVim or something, it will take some time to load, even though it's a text file. Another point is here, we both have rise and fall constraints. So means that for a rising or a falling condition, we have the both constraints. So because we don't know what is happening, so whether rise is happening or the fall is happening, so these are pre-characterized. And again, I am mentioning from going diagonally from here to here, all the possible values, all the extreme values are characterized, and any value coming in between the values will be found out by the numerical method called the interpolation, and the ST engine will do that with its intelligence. So this is all the whole constraints from the .lib file. We are done with this particular slide, so let's move on. Setup equation concept. In this slide, we will discuss about the setup equation. This is a must know for all of you. To realize the equation, we will take up help of the infographic. Let me bring it on the screen. Here. Now in this picture, there are two flip-flops. First one is the launch flip-flop colored in green, and the another is the capture flip-flop on the right hand side colored in pink. Now there is a blue cloud symbol used for the combinational path that the data passes through before reaching to the capture flip-flop. Our first path is from clock pin of the launch flip-flop to the D pin of the capture flip-flop. So this is our first path. This path is used for the data transmission. This path is used for the data transmission. The second path starts from the clock pin of the launch flip-flop and goes up to the clock pin of the capture flip-flop, passing through two buffers, buffer 1, buffer 2, or buffer 1, buffer 2. They have distinct colors. Now in this whole diagram, we can see there are several red dots here. These red dots denotes the delay caused by their respective label. This dot has the label TCQ, this has the label TComp, this dot has the T setup, and this dot has T skew, and this dot is labeled with T. TCQ is the clock to Q delay for the internal elements in the launch flip-flop. This delay is caused by the circuitry inside the launch flip-flop in between the path of clock and Q. The next red dot is called as TComp, which represent the delay of the blue colored combinational path. So here there could be any combinational path, and the wholesome delay of this combinational path is referred as TComp. The next red dot is T setup, which is the time cushion at the data pin of the capture flip-flop. So here the data pin of this capture flip-flop is, this is the time cushion T setup. In the second path, T is the time period of the clock propagation, which has a red dot associated with it. The next dot is for the TQ, which is the skew due to the buffers around the red dots. Now, as per the definition of the setup time, the data should reach the D pin and stay stable. So for the cushioning time, the data must reach a D pin and stay stable, very much stable. To make this reality, the below equation must be satisfied. Now let me bring my mouse pointer here. So you can see TCQ plus TComp plus T setup. Now one thing here, the capture clock will come here and all the delays are before that, and we have the time cushion which is before that, so all are having the plus symbol. So this must be less than T plus T skew, and thus we can say the total time of traversing which is in the LHS must be less than or equal to the time of equation in the RHS of this equation. So the data in the path 1 must reach early than the clock propagation in path 2. So we are done with this particular slide. Hold equation concept. In this slide, we will discuss about hold equation. This is also a must know for you. We will take the help of an infographics to understand this equation. Let me bring the graphics. In this graphics, we have a launch flip-flop colored in green, a capture flip-flop colored in pink. We have multiple red dots along with their labels. These are either delay or the time cushion. The first from the left is TCQ, which is clock to Q transition delay. The next is T-hold, which is the time cushion for the hold time at the Q pin of the launch flip-flop. The next one is the T-comp, which is the delay due to the blue cloud representing a combinational path, and this T-comp the delay for this entire combinational path. The next one is the red dot in between two buffers. This represents the TQ. Now you can see that there are two paths in the infographic. Since this is for launching of the data, we do not involve the time period. Let me bring up the fold equation. In this equation, the minus sign is because T hold is the time cushion is appearing after the launch clock H has already appeared. In other words, this equation can also be rewritten as like this. So here done with the hold equation concept. So let's move on. Multi-cycle path concept. In this slide, we will get familiar with multi-cycle path concept. Now, let me bring up the infographics for this. In this picture, there are two flip-flops. The data is traversing from the green one to the pink one. In between, we have an orange color cloud which represents some combinational circuits which contribute to delay. Now, in the label, you can see that the delay is a multiple of the time period t. Here, it is 7 times of t. This could be any number. I mean, the 7 instead of 7, it could be any number. But I would like to also emphasize these are real numbers and not imaginary numbers. So, the path from the clock pin of flip-flop 1 to the data pin of flip-flop 2, this path is called a multi-cycle path. Let me bring up the definition. For a multi-cycle path, the combinational delay between the propagation from launch flip-flop to capture flip-flop is multiple of the clock time period. So this is the concept of the multi-cycle path, and we are done with this particular slide. So let's move on. Half-cycle path. In this slide, we will get familiar with the half-cycle path. This is not the same as the last slide, so don't jump into conclusion. Let me bring up the graphics to understand the concept. Now in this picture, the launch flip-flop, that is the green one, is negative edge triggered as it can be observed by its symbol. Here we have the symbol. There is a bubble at the clock pin. On the other hand, the captured flip-flop, means this pink one, is positive edge triggered flip-flop as it do not have a bubble at the clock pin. Now, in the case of a square wave where on time is equal to off time, the data has to traverse in between these two flip-flops within a half cycle. This is because one rising edge followed by one falling edge at the beginning and middle of the entire time period. Undoubtedly, if we exchange the rising or falling edge for the beginning or middle of a square wave, the data traversing conditions remains the same. Let me bring up the definition. A half-cycle path lies between two positive and negative edge-triggered flip-flops. In the design, if there is such path where there are two flip-flops in between the data traversing is taking place, so one is positive edge-triggered and another one is negative edge-triggered, then that particular path of data transmission will be termed as half-cycle path. So we are done with the concept and we're done with this slide. Hey guys, welcome to the 5th episode of Static Timing Analysis. So far, we have discussed the legitimate STA violation types in the last couple of episodes. In this episode, we will discover some non-legit violations. Thus, we can use the process of elimination during the STA result analysis to narrow down the legit errors. Also, we will cover process and on-chip variation. So, today's menu is types of false path in STA analysis, asynchronous false path in STA, static false path in STA, recovery and removal time, non-functional path in STA, clock uncertainty concept, process temperature voltage corners and delay, setup and hold violation in them. And finally, we'll talk on-chip variation, also known as OCV. So here is the menu for today. So without any further delay, let's begin. Types of false path. As I have mentioned in the beginning, there will be non-legit violations inside the STA output. If we cannot segregate them, we cannot rectify the legit STA violations. Hence, the sign-off will be delayed and consequently, the tape-out will be impacted. These non-legit violations come from various false paths. The false path is not a valid path for timing analysis. No need to worry to meet the setup or hold constraint for such paths. This is we have to keep in our mind. Set false path from the start pin to the destination pins. This particular STA command will take care of the false path, which we are going to discuss in upcoming slides. We have broadly categorized the false paths into 3 sections. These are: first one is asynchronous, next one is static, and the final one is the non-functional. So when we talk about the false path is a general category, and inside this we have 3 different buckets. The first one is asynchronous, the second one is static, and the third one is non-functional. These 3 types of false path we have to deal with. Now all these types of false path can be waved off using proper timing constraints by the design team. We are done with this particular slide, so let's move on. Asynchronous false path. In this slide, we will discuss the asynchronous false path. Many times in a digital design, we have more than one clock source to feed different blocks in a design. Consequently, we will have interclock domain paths inevitably present in the design. We will take the help of the infographics to understand such scenario. Here comes our graphics. In the graphics, we can see that flip-flop 1 is driven by clock 1. Here, I am pointing the mouse. The flip-flop 2 is driven by clock 2. Here, these two have a path from the Q pin of flip-flop 1 to the D pin of flip-flop 2. In between the path, there is a green color cloud of combinational circuitry. Here, the 2 clocks have different frequency, this clock and this clock. Hence, they are termed as different clock domains. So these clocks coming from 2 different clock domains. Let me bring up the text. If clock 1 and clock 2 are independent of each other, then they are asynchronous. This is the definition. All paths in between 2 asynchronous clock domains are called false paths. So we are done with the slide. Let's move on. Static false path. In this slide, we will discuss about the static false path. The word static means that we do not have any dynamic time variation involvement. In circuitry, the time is nothing but the time period of a clock. So the paths are non-clock paths. Here goes our graphics for understanding. In this graphics, you can see that there are 4 flip-flops which are identical in nature. So 1, 2, 3, 4. Numbering wise, this is 3, and numbering wise 4. This is 4. All 4 of them have a common reset pin here in the graphics. I'm pointing with the mouse, and this goes to all of the flip-flop. This pin is independent of the clock pin and can override the functionality of the flip-flop suddenly during the clock operation. So as you can see from the graphics, these are 2 independent pins. So if we give a signal in the reset, it can reset all the flops during our ongoing operation. All paths starting at the reset pin are static false path. I am again emphasizing static means here the time period is not involved. The reset signal can come anytime. It doesn't have to do anything with the clock signal. With respect to the asynchronous pin, we have 2 different time cushions. Here in the graphics, the reset pin is the asynchronous pin. Let me bring the timing diagram. Now in the timing diagram, this is clock pulse and this is our reset signal. Okay, so here it is changing and it is changing here. The recovery time is the time cushion before the arrival of the clock edge. So here I am pointing in the graphics. This is the recovery time. This is the time cushion before the clock edge. The removal time is the time cushion after the clock edge has appeared. So this is the removal time and this is the length of the time cushion. In both cases, the asynchronous input must be stable as shown in the diagram. So guys, you can see in both of the time cushion, our reset signal is stable. So this is the condition for the recovery and the removal time. We are done with this particular slide. So let's move on. Non-functional false path. When there is a multiplexer present in the data path, there could be n number of data path combination where n is the number of possible select signal values. Now, if we have more than one mark in the timing path, then due to the permutation and combination of the multiple select signals, many such possible timing paths will be generated. To depict the situation, here goes our graphics. In the graphics, we can see that there are 4 flip-flops marked in different colors. So here is our flip-flop 1, 2, 3 and 4. Each of them have their respective data pin input. But in the graphics, these are not shown for the simplicity of the diagram. So here is the data pin, here is the data pin, here is the data pin and here is the data pin. Only this is receiving the data from the mux. Others do have their data pin, but that is not shown in the picture for simplicity. The 2 muxes, that is red and green one, are 2 to 1 mux. Here we have provided the complemented select signal to reduce the number of paths. The first one, the select signal does directly go, and in the second one we have this buffer to which the select signal goes. So these and these 2 select signals are complementary in nature. So if one goes here, then the 0 goes here and vice versa. These 2 muxes are in cascading manner. That means the data path has to go through both of them. So here you can see there is a just dotted path here, and it could be anyone, but it has to go cascading in both of them. Let me bring up the text. Due to the select signal, tool does not see the exclusiveness. In such cases, explicit declaration of such non-functional path is necessary. If you remember guys, I have already shown the st_tool command. So there I have shown how you can define this path. So generically, the path going through the 2 muxes without any exclusiveness are considered as non-functional false path. In general, this is marked with the dotted line. So here we have a dotted line. This means the dotted line would have been started from the green flip-flop, this one, rather than the yellow one from which it is already going. As mentioned in the beginning, all the false paths are specified using the set false path command in the st_tool. So we are done with this slide. Let's move on. Clock uncertainty concept. When we deal with the asynchronous clock path overlap, the first thing we deal with is clock uncertainty. You can visualize the clock uncertainty as the Q due to the asynchronous clock domain crossing. Here goes our graphics. We mainly deal with the setup uncertainty and hold certainty as shown in the figure. The uncertainty gets added to the RAT, that is required arrival time, for hold uncertainty, whereas the setup uncertainty gets subtracted from the RAT, that is required arrival time. Let me bring up the text. The clock uncertainty can reduce the effective clock period. These factors reasonable for clock uncertainty are clock jitter, clock skew, margin, and any other possible pessimism that one may want to include for timing analysis. All timing analysis are done using worst case scenario. Now, this is a very good point because the uncertainty is coming from pessimism, and in all the cases we are adding pessimism that is contributing to the uncertainty. For setup uncertainty, we use slow corner. For hold uncertainty, we use fast corner. These are kind of the thumb rules. The clock uncertainty value is used to increase these pessimism in each respective cases. Here comes our command with an example. It's fictitious, but you can learn from it. Set clock uncertainty 0.19 setup, then get clocks AKCLK. The AKCLK is a kind of clock, so we get all the clocks under this clock domain, and we set the uncertainty as 0.19 for the setup. Here comes our hold example. So here we are setting uncertainty value 0.12 for all the hold transitions or the hold cases. Now, the uncertainty can exist for 2 types of crossings, that is inter-clock and intra-clock type of crossing. Both can be managed by the ACA tool. We are done with this particular slide, so let's move on. Clock uncertainty quantification. The clock uncertainty can be quantified in the SDA tool in various ways and commands. We will classify them in 2 broad categories. We will take the help of the infographics to do this. Here is our clock uncertainty. The first one is before CTS. The second quantification comes after CTS. So before CTS, what we have? Q, jitter, and margin, whereas after the CTS, that means clock tree synthesis, we have jitter, and margin. So this is the basically quantification where we have seen what. The clock uncertainty can be specified in the STA tool using specific command. The jitter and margin can be specified explicitly using the STA commands. The Q comes in the STA report analysis. We are done with the particular slide, so let's move on. PVT variation and delay. So far, we have discussed the timing errors and checks that are either due to the circuit design or due to the use of user-specified pessimism. Now, when a design goes for fabrication in the foundry and gets fabricated on the silicon, at that time, due to the non-uniformity of the fabrication environment, a more inevitable delay and consequent violations are added. These cannot be predicted by the RTL designer who have made the design. In such case, we take the collaborative help from the foundry to get some process related data to predict such violation in well advance before the tape out. We get process voltage and temperature variation parameters from the foundry to analyze and do the prediction. This is significance of the PVT variations. Let me help with the infographics, the impact of the PVT variation. So here our PV, that is process voltage and temperature. Now each can be slitted out. Here comes our process. Process variation include random, systematic, inter-die variation. So the process does the non-uniformity, which can be classified as random, systematic, and inter-die variation. Inter-die means for different batches. So some silicon is getting fabricated today and some silicons are getting fabricated tomorrow. So these are two batches. So the variation is evident in these two. So these are inter-die variations that is coming from different batches. Next, we have the temperature. Delay is directly proportional with the temperature. Next comes the voltage. Delay is inversely proportional with the voltage. Now guys, this PVT sometimes is referred to as PTV in many companies. So instead of PVT, you are hearing PTV. So don't panic because it is the same thing. So people just combine these three initials in different combinations. That is why it is termed as different. So PVT can be PTV, but the inner meaning stays the same. The PVT variation data we get from the different fabrication batches, that is inter-die variation. So you're done with this particular slide. So let's move on. PVT corners and setup and fold violation. We can have a broad classification of PVT as slow, typical, and fast corners. However, there could be combinations such as PT, FF, SS, FS, etc. and many more. These you will notice when you receive your standard cell timing library. All these variations will be present there. Now, let us see the broader classification and its impact. So here goes our PVT. The basic broad corners is slow, typical, and fast. So these are typical, but I said already that there could be many combinations which you receive in actual timing library in your standard cell package. Now, the corners which is slow, it is more prone to the setup violation. Whereas if we go to the fast corner, it is more prone to the hold violation. So this is a kind of thumb rule. So we are done with this particular slide. So let's move on. On-chip variation, OCV. In last slide, we have talked about inter-die PVT variations. In this slide, we will discuss about intra-die variation, that is on-chip variation. The intra-die variation may come due to the fabrication non-uniformity on a single wafer. So here comes our text. PVT variation is inter-die, that is wafer batch variations, whereas the inter-die, that is single wafer variation, is termed as OCV variation. The OCV effect is predominant on longer physical paths inside a chip. So if you have a path that is going from one side of the wafer to the another side, obviously I'm not talking about the entire wafer, the tip that is inside the wafer, but direction wise from one side to the another side, and traversing a long distance. So in those paths, the OCV effect will be much more. The OCV variation impacted by temperature variation by 10 to 20 degrees centigrade. Hence, more OCV specific corners come into the picture than slow, typical, fast. So all these OCV specific data will come inside your standard cell package. If you go into the standard cell library, you can visualize them. The SDA incorporate the OCB effect by derating the delays of the specific path. So derating is related to the concept where we have already defined the Skew, right? The 10-90 and the 80-20 ratios that I have already discussed in initial episodes. So the derating acts at that point from 90 to 100%. Okay, how much that could be derated? Both cell and net delay are subject to the derating effect. So this derating affects all of the kind of delays, whether it is a cell or net, because this is coming as a on-chip variation, non-uniformity of the process across one single die. OCV can be implemented in the STA tool using the following command. Set timing derate early, there could be some value XX, and if it is late, then some YY value. So either of them will be specified to take the derating into the effect. Apart from this, one thing I would like to mention, there will be OCV timing libraries which comes inside the standard cell package. There will be OCV related data inside the timing.lib. So not only this particular command, but that also will be read by the STA tool, and that will be organically implemented in the circuit analysis. So we are done with this particular slide, so let's move on. Hey guys, welcome to the 6th episode of static timing analysis. We have so far talked about the various theoretical concepts. We will be focusing on the STA input files for next couple of episodes, starting from this episode. Today we focus on the very important input file called timing library file. Also, sometimes you call it the .lib file. You can see in the rightmost corner the timing library, that is the Liberty file, is highlighted in green circle. These files have a .lib extension, and these are human readable ASCII file, that is text file in simple language. We are done here, so let's move on. As you already know that we are exploring the timing library file here in this episode. So today's learning breakdown for the episode is how Liberty file is created, Liberty file introduction, Liberty file internal format and sections, internal format, name tokens and their meaning, header, LUT, cell, all this section definition, lookup table, LUT section, various standard cell sections inside the Liberty file with example. We are done with this particular slide, so let's move on. How Liberty file is created. In this slide, we will discuss the Liberty timing library creation in a nutshell. Here are the representation of standard cells logic family. At synthesis level, you first need the gate level netlist for each unit logic gate. These are digital logic gates. We also have the sequential elements such as flip-flop in the standard cell library. Inside the standard cell library, on single cell, we have various views like Verilog, .lib, that is Liberty, layout, DSPF, SPICE, CDL, schematic, EMIR views, etc. In the standard cell characterization, the engine picks up the necessary views for the characterization and runs the dynamic timing analysis, which is already explained in episode 1. In case you have not seen the episode 1, request you to use the chapter facility in the respective video description to quickly navigate and see the relevant section. Now, the characterization process gives birth to the ST, that is the text output file called the .lib file. Now, let us get a bit closely familiar with this file. Let me give you the brief introduction to the .lib file used in the static timing analysis. Timing engine reads a set of tails library files, that is .lib file. So this is meant to say that the timing engine could read more than one .lib file depending on your design in actual VLSI chip making area. The .lib file is a text file containing timing and power parameters associated with any standard cell for a given technology node. Now here one term I would like to explain, that is the technology node. You might have heard it's a 2 nanometer chip, or it's a 5 nanometer chip, or it's a 10 nanometer chip. So this nanometer number that you are getting nowadays on the chip is the technology node. However, each company has their own method to describe this technology node. You can take the ITRS technology roadmap for a standard where they define that the technology node, that is the nanometer that we speak for any of the chip, is the DRAM half pitch. So the distance between the DRAM half pitch is called technology node as per the ITRS guidelines. Now the .lib file contains not only timing but it also contains the power parameters. That is one more thing you getting to know here. And this .lib for a technology node will contain the exhaustive list for the timing and power parameters for all the logic gates, sequential cells, etc. And there will be a couple of special cells also. Those special cells I have explained in the UPF video. You can go there and see. Also, I will put the link in the description. It contains the data for all standard cells available in the design in the specified technology node. I have just mentioned it. So each instance in the Verilog VHDL or system Verilog netlist must have a corresponding cell found in the .lib library. So guys, whenever you are reading the files inside your timing engine, there you load your Verilog file, then you load your .lib file. So that loading of these files will go to the temporary live database, that is the design database that is with the timing shell, that will automatically map the corresponding Verilog and its corresponding cell sections from the .lib file. It will do with its intelligence. The .lib file contains pre-characterized timing models and data to calculate IO path delay, timing check values and interconnect delays. So whatever data we have in the .lib file, they can calculate all these things. To compensate the PVT and OCV variation, derating factors are also included. I have already explained in some of the previous episodes about this PVT and OCV variation separately in detail. So all those derating factors means when this variation happens, we include derating factor so that we can actualize the PVT and OCV variation inside the static timing analysis. We are done with this particular slide, so let's move on. Liberty internal format. Let's look into the internal structure of the Liberty file. If you directly open the .lib file with any text editor such as gvim or gedit, etc., what you will see, the vastness of the data mining inside the file. The data mining is done in a very efficient structural format. We can broadly classify the content inside a .liberty file in 3 broad sections and their subsections. So the sections are like this. There will be a header section, the LUT, that is lookup table section, and third, the cell definition. So these are major sections inside the .lib file. And in this presentation, I will go to the definition plus example of all of these sections in upcoming slides. So you are done with this particular slide. So let's move on. Name tokens and their meaning. Before jumping into each section and analyze them in detail, let us get familiar with few frequently used name tokens and their meaning. These have very straightforward meaning. Some of them I have already explained theoretically in some of the previous episodes. So here we go. Norm temperature and norm voltage. These two name token specifies the temperature and voltage reference points, that is operating condition. Slew and delay threshold points. Low and high threshold values for slew calculation, 10% to 90%, and the threshold for delay calculation, that is 50%. I have pictorially made these things clear in previous episodes. These name tokens will be there in the .lib file to specify these 1090 or 8020 threshold, and the delay threshold will be 50%. Default values for fan-out capacitance slew specifies the limits of maximum input slew on an input pin, input in-out pin capacitance, and the maximum output capacitance on any output pin units. So these name tokens also be there, and from there you can interpret the values. So we are done with this slide. So let's move on. In this slide, we continue further for some more frequently used name tokens and their meaning. operating conditions, derating factors, limits, and units. 3 different values are usually required, that is typical, worst, and best case. These tokens will be also there, but their values will be typically P values, typical, worst, and best. However, to accurately get these 3 values, process parameters and transistor models for the entire process are required, which is only available through foundry provided PDK or TIC files and used during the pre-characterization stage. So a couple of slides back, I have mentioned that you get the PDK and the TIC files from where the relevant files are picked up automatically during the characterization stage. Here we are re-emphasizing on this point. Library and delay model. Provide a library name and delay model through the table lookup, that is non-linear delay model. So some of the LUT I have already explained in couple of previous episodes, but since I am explaining the .lib or the timing library in general in this slide, so here I re-specify or re-emphasize these details. Non-process property. Specify the reference points for process scaling used for the characterization of the cells. So these will give the scaling factors of the process. So these are very straightforward, so I'm not going in detail, and you will come across in the example all of these name tokens. Why we call them name tokens? The reason is that these will be fixed text in the .lib file, and these text will be fixed across multiple .lib files, and they will have a value which may vary from one .lib file to another .lib file, but these name tokens will be fixed text phrases. I have already explained all of the common type of name tokens in the last 2 slides, so we are done here. Let's move on. Header section definition. The header section of the timing library file is important for both the ACA tool as well as the engineer who is doing the STA. Now, let us see the header section in generalized prototype. We start with the library name. In the angle bracket, the library name will be there. Then starts the header section. Here you can see the slash star, and the star slash acts like a comment in the .lib file. There will be delay model. The delay model is table lookup, that is LUT. Time unit, it will be given the time unit in second or nanosecond or something like that. Voltage unit, it will contain the voltage unit. There will be current unit. There will be capacitive load unit. Sometimes we called the load, which also means the capacitance. That will have its unit here. It has 2 parts. One is the float, another one is the unit. Leakage power unit, pulling resistive unit will also contain the resistance unit. Then there will be non-process. There will be some double here. It is, you can say, the double real int, that double here we are mentioning. Non-temperature double, non-voltage double. Operating condition, in the angle bracket there will be actual instance name. Process double, temperature double, voltage will be double. We close the operating conditions here, and default operating conditions, there will be an instance name. So this is the kind of detail of a header section that will what the details it will contain. Sometimes in the library file, there could be some additional name tokens. In that case, you have to interpret by the name and the meaning. I am done with this particular slide, so let's move on. LUT definition. LUT is lookup table. The body of the Liberty timing library contains lookup table and cell definition. The lookup table or the LUT has a prototype defined in the topmost sections in the Liberty file and just after the header section. So here we define the prototype and later on we use it. You must remember the variable values are subject to change in the data populated LUT inside timing block of each cell definition section. So here we are starting the LUT prototype definition. Lookup table template definition. This is a comment. LUT table template, and there will be the table label or the name. Variable 1, then variable name. This will be a text. Index 1, string of the data points for variable 1. So if this variable have 5 different values, then there will be 5 values mentioned inside this index 1 values section.
variable 2, the variable name, and similarly it will have the index 2 and set of data points for variable 2. And here we close the LU table template. And further, such more template definition will follow. Such multiple LUTs are defined for each particular dataset at the beginning of the library file. Just for example, I can say that you are having multiple LU template. One thing could be for delay, one thing could be for rise, one thing could be for fall. We'll come and see the examples later on today's episode. We're done with this particular slide, so let's move on. Standard cell definition. For each standard cell, we have a standard data structure for its data mining purpose. In this slide, you will get familiar with this general structure. Here goes our comment, cell definition, then cell, then cell type, pin name, direction. So here just I would like to emphasize cell type means whether it will contain the name. From that you can check whether it's a logic family or it's a sequential or it's a latch, etc. or it's a special cell. Now we continue again. Clock, that will be Boolean. Max capacitance will be there, that will be a double value. Mean capacitance, that will also again have double value. So these are the upper and lower cap. Then starts the timing block, related pin, then it will be pin name. So this is very much important. Now if you look here, we already started with a pin. Pin means the cell pin on which we are having all this data. And timing is always between two pins. Whatever AT, RAT we define, that is between the two pins. And here the pin and the related pin are the 2 points in between which we are having the timing data. So these two are very important. Combinational or sequential definitions will come in the next section depending upon the cell is a combinational type or a sequential type. Then we close the timing. There could be more timing definitions. As per the number of pins, the more pin sections will follow. Here goes our more pin definitions that I was talking about, and the more timing definition will contain the details of the timing. From here we close curly bracket, we have closed the cell, and the next we have more cell definitions now, and then we totally close here. So this is the kind of cell type definition, and this is a typical structure you will have inside the LUT. Whatever the cell type is, whether it's a logic family or it is a sequential or it's a latch or it's a special cell, there will be cell section. This is must. One more thing not shown here is the functionality. This is a section that contains the truth table representation for combinational cells and present state versus next state table for the sequential cell. This is well understood by any human eyes. We're done with this particular slide, so let's move on. Flip-flop and latch definition. Now, let us have a quick look into the flip-flops and latch structures. The same structure is applicable for all general flip-flops. Flip-flop, state of non-inverting output and state of inverting output. Clocked on, then there will be a clock pin name. Next state, input combination that produces the next state. This is typically looks like a equation. Clear, active value of the clear input. Preset, active value of the preset input. Clear preset variable 1, value of non-inverting output when both are active. Clear preset variable 2, value of the inverting output when both active. Here we close the flip-flop. Latch is very similar structure but requires enable and data instead of the clock and the next state. So this is a kind of general structure for the flip-flop and latches. We're done with this particular slide. Let's move on. Scan chain cell definition. Apart from the regular cells, special cells which are used in the DFT purpose are included in the library file or the timing library file. These are termed as scan chain cells. We also have scan flip-flop in the timing library file. Let us see the scan chain cell structure. Requires a test cell group to be defined. So this is about the structuring of the .lib file. Two flip-flop groups need to be defined, one in the cell function defined with testing features and one inside the test cell group without the testing feature. So there will be two
sections where we have the presence. Test cell. Then come test scan in. Scan input pin name here host. Test scan inverted. Inverted can input. Test scan out. Can output pin. Test scan output inverted, that is inverted scan output. Test scan enable. High on this pin puts in the test mode. Scan and shift. Test scan enable inverted. Same as above but inverted. Test scan clock. The test scan clock for clock can. And here we close the test cell. So there will be two instances, one inside the test cell group, another in the regular section. So thus the scan chains are defined. One thing we mention here that the scan flip-flop have the similar structure as regular flip-flop mentioned in the last slide, and these are used in the testing purpose of the chip. So we are done with this particular slide, so let's move on. Let's see some example. We came across all the definition blocks so far. Now let us plunge into the examples to fortify our knowledge gained so far with example. Header section. In this and next slide we will exemplify the header section. So here we start the library simple. Here you are getting the example. So actual names and values will be there. Delay model table lookup. Time unit 1 PS. Voltage unit 1 V. There is 1 volt. Current unit 1 milliampere. Leakage power unit 1 microwatt. Capacitive load unit. It has two parts if you remember. First one is 1 and second one is FF. Cooling resistance unit 1 kilo ohm. Default fan out load 1.0. Default in-out pin capacitance 0.0. Default input pin capacitance 0.0. Default output pin capacitance 0.0. We continue again. Slew load threshold PCT rise 20.0. Slew lower threshold PCT fall 20.0. Slew upper threshold PCT rise 80.0. Slew upper threshold PCT fall 80.0. So here in these 4 lines we have just explained the thresholds, that is 20, 80 in the slew. Input threshold PCT rise 50.0. Input threshold PCT fall 50.0. Output threshold PCT rise 50.0. Output threshold PCT fall 50.0. Norm voltage 0.7. Norm temperature 70.0. Norm process 1.0. So I would like to mention one thing. Here you can see that in the right hand section, you can see rise, fall, rise, fall, rise, fall for all of these thresholds. This is because in actual transitions, the inclination of the rise or the slew transition may not be same. So explicitly we define here both of them. So we are done with this example of the header section here, and we have it continued in this slide. Operating condition typical underscore 1.0. Process 1.00. Temperature 70.0. Voltage 0.7. Pre-type balance tree. We close the operating conditions. So here you can see the operating conditions as process temperature voltage, that is PVT values. Default operating conditions typical 1.0. LU table template delay output slew template 7/8. Variable 1 total output net capacitance. Variable 2 is input net transition. Then comes the variation of the variable 1, that is index 1, means the total output net capacitance. These will be the values on which we have done the variation. Index 2 have a set of variation values here. and we close the LU table template. In upcoming sections, this particular LU table template will not be mentioned. Only the explicit table will be there. So there only index 1, index 2 or variable 1, variable 2 will be mentioned, but these names will not be there. I emphasize the names will not be there in the example in upcoming slides. And another thing in the above section, in the operating conditions, we have kept 1. There could be more than 1, and the default one will be picked up by the default operating conditions. We are done with this particular slide, so let's move on. Cell begin and end. Each cell contains huge amount of data that varies from one cell to another. So we will segregate each section and look into them separately. Here in this slide, we will look into the beginning and end block of any cell because this part will be common. So the begin section of the cell, here goes our example. Begin cell is a comment inverter X1. So it's an instance name X1 and the type is inverter. Cell inverter underscore X1. Then pin O, direction output, capacitance 0.0, max capacitance 12.80. Now here we define the capacitance values and the capacitance unit already we have defined in the header section. Mean capacitance is 0.0. Start timing. After these definitions, the timing section inside the cell will begin. Now we see the end part of the cell. Related pin A. This is very important. I have already mentioned because when you talk about one particular pin O, we just kept in the left hand section. The timing always required 2 pins from and to. So these are those 2 pins. One is the pin which we are having the definition for, and the timing is related with respect to the pin A. Here we close the timing, end of the timing. We go here, end pin, the pin is closed. Next, the next pin comes, pin A, because it's an inverter. There are only 2 pins, one is O and another one is A. It has capacitance 1.0, direction input, and we close pin A. We end pin here. So these are comments. The star slash star and then the star slash defines the comment. We close it and then we close the entire cell, end cell inverter underscore X1. So thus the beginning and the end of each cell will be there. Inside the timing block, there will be relevant timing data. Since we cannot show in one single slide everything here, so that's why I have made the split into 2. One is the begin and end section of a cell, and the respective timing section I will describe in the subsequent slides. As you can see that we describe each pin separately of a cell. The token related pin at every LUT section will connect the timing path between the 2 pins. We will see in upcoming slides. We are done with this particular slide, so let's move on. Before beginning, I would like to mention that here index 1 and index 2 we have described already in the header section. Index 1 is the total output net capacitance and index is the input net transition. These two are also called the output load and the input Q respectively. And here we start our cell output rise delay, the LUT lookup table. Cell rise delay output slew template 7/8. 7/8 gives the number of the row versus column of the table. Here goes our actual index values for index 1. I have mentioned already the index 1 and the index 2 just few minutes back. Index 2 has these all variations, and here goes our table. First row, second row, and we keep on adding the rows and the columns. Here our table gets closed and you can see. So let me bring my mouse. Here goes our row values and here goes our column values. That means index 1 and index 2. Here we close the entire cell rise, the delay output slew template. LUT section we have closed. Cell output rise delay of pin O with respect to pin A. Here related pin is A. This is a kind of I have emphasized here. I have already told, but I have emphasized here just to knock into your mind that the timing is always in between 2 pins, and we just started to describe the O. We left the timing section blank there. We have just kept beginning of a cell and end of a cell. And here now we are defining the timings inside each cell. Cell output fall delay, LUT. Starts the timing. Cell fall delay outputs you template 7/8. We have index 1 variation, index 2 variation, and here starts our table. Here starts our row, and we keep on adding the rows and corresponding columns, and here we close the table. Now why I am showing all these explicit examples? Because in our actual .lib file, that is Liberty timing file, all these kind of various lookup tables will be present. So I'm kind of knocking into your mind and with the example, so that you remember when you open and read a .lib file and you don't feel lost in the data. Yes, this all type of LUTs will be there. We close it here, and again re-emphasizing the point that this is the cell output fall delay for pin with respect to pin A, which we denote with the related pin name token, and the value is A. So we are done with this example. So let's move on. Cell output rise slew, LUT. Rise transition, delay output slew 7/8. Here goes our index 1 variations. Here goes our index 2 variations. Values, start our row, and we keep on adding the rows and corresponding columns. And here we close the table. And here we close the rise transition block. So this is the LUT for rise transition, that is rise slew. Cell output rise time of pin O. We are done. I've not talked much because I've already talked and explained in previous examples. So you can understand by your own about these names. And I have also mentioned earlier that rise and fall will be there because the slanting of the rise and fall transitions are not same in actual transitions, and hence explicit data for rise and fall will be there. We're done with this slide. Let's move on. Cell output fall stream LUT. Fall transition, delay output table template 7/8. Now here goes our index variation, index 2 variation. We start the table values, first row, and then we keep on adding the rows, and the corresponding columns are automatically added. And here we close the table, and here we close the fall transition block. Again emphasizing till output fall time of pin O. We are done with this slide, so let's move on. Hey guys, welcome to the 7th episode of Static Timing Analysis. In today's episode, we will discuss about the design constraint file. This is a very important file because here we define the AT and RAT, which we have discussed in episode 1. Constraints are first defined in the synthesis stage, then they are reused in the pre-layout and post-layout SEA. The constraints make a realistic periphery of the ideal netlist. Let me introduce the constraints to you to today's menu. First, we talk about why we write constraints. Then, design constraint file introduction will be there. Frequently used design constraint commands will be introduced to you. We will recall the directed acyclic graph concept, arrival time, input delay, required arrival time, output delay. Everything is in terms of the constraints. Rise or fall slew design constraint. So this is the menu for today. So without any further delay, let's begin. Why we write constraints? Theoretically, I have already explained that the constraints make a realistic boundary to the ideal netlist during the simulation. We do this in bits and pieces. Let me walk you through such cases as an introduction. By default, in your design, the signal arrives at the input port at time equal to 0. In realistic cases, input signals arrive with a delay added to it. We can do such case by set input delay. We give a value here 2.5. Then we mention for which clock, that is dash clock, CLK, and for all inputs. The overall delay will be 2 nanoseconds relative to the system clock. Thus, you can see first your system was very much ideal. Then we have given this command with a particular delay value to the input, and that makes the system perform like a real case. How to control the output delay? Well, we can do that. Let's see how. Assume that your design is driving a flip-flop. We want to add an output delay on the output pins of 1.5 nanosecond relative to the system clock. So how we do it? We can do such by the command set output delay, and we mention the value 1.5, and we mention for which clock, that is CLK, and for all outputs. So this is how we can define the delay that is for input and as well as for the output. The purpose of this slide is just to touch base the basic concept of constraints and how the constraints transform an ideal case to a realistic case. I think that is being imprinted into your mind with this particular slide. So let's move on. Design constraint file. We have understood what is constraint and what purpose it is used for through small examples in last slide. In this slide, let me give you a compact introduction to the design constraint file. So here we go. Design constraint file, also known as SDC files, to impose initial timing conditions on the design. Adding constraint to the design is a process to make your design perform like a realistic situation, which I have been telling you for last few minutes. Design constraint file have an .sdc file extension. Design constraint is a tickle-based format to specify the design intent and the surrounding constraints for synthesis, clocking, timing, power, test, and area. This is a very important point. All the design constraint commands are nothing but tickle procedures. In the tickle series, I have already explained how the tickle works for VLSI. In case you have not watched that episode, I'll provide the link in the description. So guys, all these tickle commands are custom-made tickle procedures, and they are very much intended application so that one particular command will do one thing. If you know tickle, you will be very easily write the tickle constraints based on the definitions that are provided in the manual. So guys, I think in upcoming examples, your mind will be very much clear that these are tickle commands and how we are using them. It can be generated during the synthesis stage using the tickle command. Write SDC, then the path, and then the name of the file .sdc. So this is a very widely used command, and this command is used at the synthesis stage to dump all the constraint into a file. We can write the constraint as well as we can dump the constraint. All depends upon the tool which you are using. So don't think I'm making a global comment, but generally tools have this capability to read the SDC and write the SDC at synthesis stage, and it may vary from one vendor to another vendor. But just for your knowledge purpose, we are adding a fact that apart from writing it by hand, you can dump it also. Also, one can create the .sdc file manually in a text editor such as Gvin, gedit, Nano, Notepad++. So I don't know which of text editor you are preferring. You can write down in the comment below which text editor you are very much comfortable with. And generally all these text editors nowadays have the highlighting capability. That means if you are using tickle, they will highlight the tickle proper names and keywords etc. in a different color and your normal values in a different color. So at least what I can say that you can write the commands manually and give it as an input to the tool, or you can dump it using the command just mentioned above. So I think we are done with this slide. Let's move on. Frequently used commands. Let me share a few design constraint commands that a designer very frequently have to use. You may consider this slide as your handbook. So here is our table. So let me bring my mouse. Set input delay. So this is a timing constraint, and it sets the input delay of an input port relative to the clock signal. It's very straightforward in meaning, so I am not going any further explanation. Set output delay. This is also a timing constraint. It sets the output delay of an output port relative to a clock signal. So you have a clock in both the cases, and with these two commands, you can set the input delay as well as the output delay. One thing I'd like to mention here, whichever tool you are using, just consult the manual for the rest of the arguments of this command. That does make a sense, and that is very much needed because when you are writing this file, those you have to write in a correct way so that whatever your thought process is to implement the constraint, that should be well reflected in the command. Now,
The third one, create clock. This is also a timing constraint. Creates a clock and defines its waveform in the current design. Set input transition. This is a system interface. Sets a fixed transition time on an input port. So this is basically a transition time, means that the slant, that means the rising or the falling. Set input transition, I think sets the load capacitance value on the output port. Here I think I have done some typo. I'll provide some more corrections in the description. So basically there is another command which is used for the load capacitance value for the output port. So I think the command would be something like that, set output load or something like that. These all commands are kind of frequently used command, and you can take them as for your handbook or something like that. You can write it somewhere in your notebook where all these commands and their arguments, so that you can easily use them whenever you are dealing with your actual design. Let me go to the next slide. Some more commands. So far we have discussed the most frequent commands. Now in this slide I will share some names of the commands which self-explanatory nomenclature. Some of these commands you may connect back with the ACA theories that I have covered in all of the previous episodes so far. So here we go for the list. Set clock, set clock delay, set current design, set false path, set input delay, set IO standard, set multi-cycle path, set output delay, set path delay, set range input delay, set range output delay. So all these names are kind of self-explanatory. You can easily understand and consult the manual whenever needed. The tickle commands are nothing but tickle procedures. So in different vendor tools, they can have a little bit difference in their names. Let me describe it to you. Generally, the commands are set underscore then do something. If you look at the left side list, these are all like that. But in some other simulator, they can be like this. In some simulator, the commands may start with define, then underscore, then do some. So instead of set, it could be define. It may vary from one simulator to another simulator, but the purpose remains the same. If you are encountering a different simulator, not only the name, the arguments may have been a bit different. So be careful and consult the manual every time. We are done with this particular slide. So let's move on. Recall the directed acyclic graph. So these are numbers, just don't panic. This slide is to give you a quick recall of the AT-RAT concept. Here goes our diagram, and you can see the numbers and everything has been well fitted inside it. Here goes our definition. Here goes our AT-RAT calculation, which we have discussed in episode 1. In case you have not seen or want to refresh your knowledge, use the chapter facility provided in the episode 1 description to quickly navigate to the respective slide. Link of episode 1 is provided in the description. So let's move on to the next slide. Arrival time, that is input delay. We just pictorially touch based the AT-RAT concept which was discussed in detail in episode 1. Now let me show you how you can define the arrival time, that is input delay. Here goes our example. Create a clock. First thing, create clock, then we specify the period 50, then name my clock, and then we use rectangular bracket as we use in tickle. Get ports my clock. So we get all the ports, and onto that we apply the period and everything. This is how we define create clock. Again, I am emphasizing from one simulator to another simulator, this particular command may be a bit different, so don't panic. Always consult the manual. Defining input arrival time, that is AT. Set input delay 0 minimum, then rise for the ports, get ports my clock. So here we set the rise time delay. Clock is my clock. Here the delay is 0. Set input delay 25, that is minimum, that is dash fall for falling edges. Get ports my clock, to get all the ports of this clock, and then clock name is my clock. Set input delay 0 max, that is rise. This is for rise transition. Get ports my clock, and clock name is my clock. Again, we have set input delay 25 max for fall, and get ports all the ports of my clock, and the clock name is my clock. So here you can say, let me bring my mouse. You can see that we have first defined the two minimums, and then we have defined the maximum of rise and fall, rise and fall. So all these rise and fall transition, we have defined the mean and max, the mean and max transitions. So this is how we create a realistic boundary that I have just spoke in the first slide. So we are done with this particular slide. So let's move on.
required arrival time, that is output delay. In this slide, I will exemplify command to define the required arrival time, that is output delay. Here goes our example. Define the output required arrival time, that is RAT. Set output delay 10, then we use the dash min for minimum and rise, and then we use the gate ports of out and clock name my clock. So here we are getting on the ports with out name and applying the delay of 10 for rise transition. Set output delay 10 minimum, and for fall transitions gate ports we get all the ports here through this command for out, and we set clock as my clock. Now we going for the max. Okay, yeah, set output delay 30 max, then for rise transition, and we use the gate ports and clock is my clock. Set output delay 30 max, and then for fall transition and gate ports for out and clock on my clock. So let me bring my mouse pointer again. If you compare, this remains static, this remains static. Only the changes here it is static and here it is static. Only changes is here and here. So we have couple of combinations just to declare the minimum and maximum of the delays for rise and fall type. So we have 4 total commands to define the realistic boundary for RAT, that is required arrival time. Here we are done with this particular slide. So let's move on. Rise, fall, skew design constraint. In this slide, we are going to exemplify the rise and fall skew constraints through commands. Here goes our example. Define the input transition time. Set input transition 10, then minimum, then rise, then get ports of input and clock is my clock. Set input transition 15 minimum for fall type transition, get ports for input and then clock my clock. Set input transition 20 max, rise, get ports for input and clock is my clock. And we define the set input transition 25 max, and for fall transition get all the ports input and then clock is my clock. So again, let me bring my mouse pointer. You can see the values are different, each value is different from one another, and here 2 are mean, these are 2 static, these are 2 static, but this is varying, here this is varying. So rise, fall, and here it is static, here it is static. So this is how we are defining the constraint for the input transition time. One more thing here I would like to add. Here we have defined with 1, but for your case you have to write multiple times for multiple cases. So it depends from one design to another design. So guys, we are done with this particular slide. So let's move on. Some more applications. Apart from the timing, we can do something with the design constraints commands. Let me show you how. Set realistic loads on each output pin. Set load 0.15 to all my outputs. This is how we can also add a load value. Set fan in and fan out for the input or output pins of your design. Set max fan out 1 to all of my outputs. So this rectangular bracket is a tickle concept. Now let us define the corresponding load. Set fan out load 8 for all of my outputs. So this way we can use the design constraint. Apart from the timing things, we can define the load, fan out, fan in. You can consult the manual for all these types of other things that you can play around with the constraints. We are done with this slide, so let's move on. Hello and welcome to the 8th episode of Static Timing Analysis. In today's episode, we will discuss about SPEF file. This file contains the details of the parasitics such as resistor, capacitor, and coupling capacitor due to the metal or via interconnection during the place and route stage. These parasitics contribute to RC delay, which in turn can affect the AT-RAT calculations. Thus, the SPEF file is very much important for the STA analysis. Here is our menu for today. First, we discuss the introduction to the SPEF. Next, post-layout parasitics visualization, extraction, position in the ASIC design flow, SPEF and the entire design, various sections of a SPEF file, details of each section of a SPEF file with example. Overall, standard parasitic extraction format snippet. This is basically a short and sweet example of an entire SPEF. So we are done with this particular slide, so let's move on. Introduction to SPEF. Now, let us have a general introduction to the SPEF file. Standard parasitic exchange format
SPEF is an IEEE standard for representing parasitic data of wires or nets in a chip in ASCII format. That means it's a human readable format. Metal or via in routing have parasitic resistance, capacitance, coupling capacitance associated that are captured by SPEF. These nets also have inductance that is excluded in SPEF. SPEF is used for delay calculation, signal integrity check, crosstalk analysis, EMIR analysis of a chip, which eventually determines its speed of operation. This file cannot be hand created. So this is a very important point. We cannot write a SPEF file by our own hand. This file is created using industry standard extraction engine. This is very much important in the design flow where we are placing the extraction. You will see that at what stage this extraction is done and how critical that stage is. So we cannot write the SPEF file by hand. So we are done with this particular slide. So let's move on. Post layout parasitic visualization. In this slide, you are going to visualize the difference that the SPEF file makes on top of the actual design. In this slide, we will overlay the content of a SPEF file over our design. This slide is for educational explanation purpose. Hence, the circuit diagram are kept oversimplified format so that you can grab the meaning quickly and easily. This is our pre-layout synthesized netlist. You can see that these are several logic gates and their interconnection. Now, this is the post-layout parasitic RC annotated netlist. Can you spot the difference? Yes. This and this. These are parasitic resistors which are contributed by the SPEF file. Now you can see that the number of nodes have increased in the circuit. This increment is due to the addition of the parasitics. For simplicity of the diagram, we have not shown the parasitic capacitors. The added nodes are often called subnodes because these expands the existing node into many more new nodes. One another avatar of the SPEF file is SBPF, which is binary file and hence cannot be read by human being. This is for the STA tool consumption only. For very large design, SBPF is useful because of its faster loading time. Now, one thing I would like to say before concluding, this annotation is done by some of the EDA tools. The SPEF file contains the information of these additional parasitic R and Cs. Those are highlighted in this diagram. So we are done with this particular slide. So let's move on. Extraction ASIC design flow. Since already I have mentioned that the SPEF file cannot be hand created, you must know at which stage of the VLSI ASIC design the SPEF file is generated. I will describe the ASIC flow and point out the stage where the SPEF file is generated. This will make things clear for you into your mind. Here we start. First, we have the design specification, and in this direction the flow is going forward. Next, we have the RTL coding, which you know, that is HDL coding. Next comes the verification. Next comes the synthesis stage. Next to it, we are entering into the backend stage, that is power routing, and sometimes there could be a pre-layout STA just between these synthesis and power routing. Next comes the global placement. Next to it comes the detailed placement. Next, we have the clock tree synthesis. We have covered this column, so we'll move on to the right hand side. The next is global and detailed routing. We will proceed in the upward direction now. The next is layout generation or changes. Next to it, we do the DRC and LBS of the generated layout. Next, we have the parasitic extraction, that is PEX. At this stage, we extract the SPEF file. Next, we have the static timing analysis, that is post-layout static timing analysis. Next, we go for the EM and IR verification or EM/IR analysis. Next, we do the AEC and final tape out checks. And finally, the design is ready for tape out. So folks, you have noticed that, let me bring my mouse pointer here. So these are the front end stage, and here it is entering the back end, and after so many steps comes the parasitic extraction stage. Here we extract the SPEF file. So it is so many level down. So at this stage it is very critical, because now you have all the previous steps done, and sometimes each of these steps may iterate one more time because to eliminate the errors. So multiple times these steps can iterate and or reiterate, and finally when we come up to this stage, we have consumed a huge time. So at this stage we extract the parasitic extraction. So at this stage, this is very crucial design turnaround time, and at this stage we extract the SPEF. This guides you one more thing, that the SPEF, if we try to hand create, we cannot, because there are a lot of dependency here, so many steps before this, so we cannot create it by hand. Whatever we create by hand is at the very beginning, when we are at here, okay, something at this stage, maybe in front end something we can hand create, but after crossing so many steps, we cannot do anything by hand creation. Everything has to be as per the design flow and through the proper tools, that is EDA tools. So guys, we are done with this particular slide, so let's move on. SPEF and the entire design. You may wonder that we have taken care of the parasitics of the metal via interconnection through SPEFs. An obvious question comes, what is about the interconnection inside each standard cells? Here goes our diagram. As you can see that the standard cells are interconnected by nets. The PEX file, that is SPEF file for net, is called PEF. Similarly, the PEX file for the cells are extracted in DSPF format. These are used during the standard cell characterization to calculate the internal delay. The delay and timing data for these cells are captured in the timing library file, that is .lib file. We have covered this file in detail in one of the previous episodes of this series. I'll provide the link in the description. So guys, if I bring my mouse pointer here, all these nets which are interconnecting the standard cells in the design, they will go to the SPEF. So when they go to the SPEF, each net will have its R and C, the parasitic R and C, all those data will go to SPEF. And the design have the standard cells, all those cells have their respective DSPF file where they have their parasitic data. But whenever we use the static timing analysis, we are concerned about these nets, because these cells have already characterized and their data for timing is already captured in the .lib file. So we are done with this particular slide, so let's move on. Various sections of a SPEF file. The SPEF file is a very large file with huge amount of data. However, it is divided into 4 distinct sections for clear interpretation of the huge amount of data. Here are the 4 sections. The first section is a header. The next section is name map. The next section to it is the port section. And finally, we contain all the parasitic information of resistor, capacitor and coupling capacitor in the RCCC section. In upcoming slides, we will describe each of these sections with definition and example. We will append one more optional section called layer map in the last slide of this video. The purpose of this slide is to imprint the 4 sections before we plunge into the detail. We are done with this particular slide, so let's move on. Header section. As the name suggests, this section resides at the top of the SPEF file. However, we do not have a footer section in SPEF file. Header section is a kind of identity card of the SPEF file. Let us see in detail. The header section contains information about design name, the parasitic extraction engine name, naming convention, and units. So let us see the thing with an example. First, it goes the first line of the header, that is SPEF, and it gives the IEEE version. Next goes the design name, Here it is XA5017. By the way, all these data are imaginary data. These are not from any actual data or design. So date is something here, the date on which this file was generated. Vendor is ABC Imaginary Corporation. Program is the parasitic generator. Here the name of the parasitic extraction engine will come. Version 0.0. Design flow netlist type Verilog. This has a specific set of values. You can consult the respective extraction engines manual for this particular field. Next comes the divider. Divider means it's a hierarchy separator. If the design is a hierarchical design, the text will be separated for each hierarchy with this particular delimiter. Next comes the delimiter. That is a usual text delimiter. Bus delimiter is the rectangular brackets. Time unit is 1 picosecond. Capacitor unit is 1 femtofarad. Resistance unit is 1 kilo ohm. And L unit, that is inductance unit, is 1 microhenry. Although we have kept it here, but generally in practice the inductor is not present. So we are done with this particular slide. So let's move on. Name map section. For multi-million gate design, the SPEF file will contain huge number of nets interconnecting them. Thus, the SPEF will be very bulky. The name map section provides a way to use shorthand method for net names, which are usually very long for a hierarchical design. Thus, to reduce the overall file size. Let us see how. To reduce the overall file size, SPEF convention is to convert long name of the nets to be mapped to a shorter numbers preceded by an asterisk. The mapping or lookup table is defined in the name map section. Here goes our example. Start the star, then in all caps the name underscore map starts the section. Next comes the 509 is the mapping number, and the actual net name is here is F underscore C underscore EP2. Similar way, we have the other mapping numbers for all the subsequent nets like this. So let me just bring my mouse pointer. So these are shorthands and these will be used in the entire SPEF instead of the full net names. And here you can see this is a hierarchical net name. So when all these long text or alphabets, you can count how many alphabets are there. They are replaced by only 3 digits and 1 asterisk. So that will help the reduction of the entire file size. So if you have to know in a resistor or capacitor about this particular net, you have to come back to the name map section and you have to follow this lookup table to know what is the corresponding net name. Later, these shorthand are used instead of the large net names as like star:509:16538 means an internal node of the net F underscore C underscore EP2. So guys, we are done with this particular slide. So let's move on. Port map section. The chip talks with the outer world with its pins, which act as ports to exchange the signal between the internal circuitry and external world. These are captured in the port section. Let us have a look to the port section. The port section is simply a list of top-level ports in a design. The direction of the ports are marked with I, O or B for input, output or bidirectional respectively. So these will be always in upper caps, this I, O or B. Now let us see one short and sweet example of the port section. The section start with start then ports, it will be on all caps. Next we have star1 then I, star2 as I. So all these are ports. And we have star3, the value is O. The star4 has value O. Star5 has value O. Star6 has value O. Star7 has value O. Star8 has value B.
and star 9 has value B. So please don't confuse this I and O with 1 and 0. So these are I and O. Whatever you have in the port section, those are I and O on the right hand column, and don't confuse them with 1 or 0. So let's move on. The DNet section. The largest part of the SPEF file is the RCCC section, which is subdivided into DNet, that is D_NET, then CON, CONN, RES, and CAP sections. In this slide, we will talk about the DNet section. DNet means the distributed detailed net. Sometimes in RSPF format, there can be a similar section of RNet, that is R_net, meaning the reduced net. Let's now focus on the DNet section. Each extracted net will have a DNet section. This will contain a DNet line that start with R, then in all caps D_net, a CON section, a CAP section, a RES section, finally an star end line to end the concerned net section block. So the DNet starts with star D_net and ends with a star end. In between it will contain the CON, CAP and RES sections. Single pin nets will not have a RES section. Nets connected by abutting pins will not have a CAP section. The DNet line tells the net name and the net's total capacitance. So when this DNet line is there, the last field will contain the total lumped capacitance of this particular net. The capacitance will be the sum of the all capacitances present in the star cap section. So this lumped capacitance is the sum of the all capacitors present in the cap section. The CON section, the connectivity of a net specified in detail in the CON section. This section is very important for the STA as well as the EMIR tool. So let us get familiar with the CON section. The CON section lists the pins connected to the net. A connection to a cell instance starts with a star I. A connection to a top level port starts with a star P. The syntax of CON entries is star I, then we have the field pin name, then we have the field direction, then we have star C, which follows next two values, that is X and Y coordinate, and finally we have the loading or driving information. So it could be either loading or driving, cannot be both at the same time. Where the pin name is the name of the pin as per the design. The directions could be I, O or B as per input, output or bidirectional signals respectively. The XY coordinate will be the location of the pin in the physical layout. For an input, the loading information will be star L and the pin's capacitance. For an output, the driving information will be star D and then the driving cells type. So we have the short and sweet description of the CON section here. Now we are done with this particular slide, so let's move on. The RES section. This section have resistor details. Resistor due to the metal or via both come under this section. During extraction, if you turn on the tail command to be dumped, then you can identify a metal or a via simply by its layer number from the additional layer map section coming just after the name map section. We will talk about the layer map in the last slide of this presentation. Now let us focus on the RES section. The RES section provides resistance network for the net. Entire entries in the RES section contain below fields: an identifying integer, two node names of the resistor terminals, resistance value between these two nodes,
So one single race line will contain these things: an identifying integer, two terminal node names, and finally the resistance value. The race section is very much important section for the EMIR analysis. For EMIR analysis, the tail comment is a must. For STA, it does not matter whether we keep or remove the tail comment. We are done with this particular slide, so let's move on. The cap section. The cap section contains the simple capacitors and coupling capacitors. This coupling capacitor is very much important in signal integrity and crosstalk analysis. For STA, this section contributes the RC delay calculation of the metal or via interconnection routing. Let us take a tour of the cap section. The cap section provides detailed capacitance information of the net. Entries in the cap section come in two forms: capacitor lumped to the ground and a coupling capacitor. A capacitor lumped to the ground has these below fields: an identifying integer, a node name, and the capacitance value of this node. A coupling capacitor has four fields: an identifying integer, two node names of the two end terminals, and the value of the coupling capacitor between these two nodes. So we will discuss this through an example. All of these sections, all these things will then come clear into your mind. We are done with this particular slide, so let's move on. RCCC section example. We have discussed the theory so far. Now let us dig into the example. Here is our DNet line. There are three fields. The first field of the DNet denotes that this is the beginning of a denote block. So here it is the beginning of the denote block. The next field is the net name, including the hierarchy. The hierarchy separator is / here. So this is the hierarchy separator and this is the node name final. This field can also be a number if the number is mapped with this net name in the name map section. So if we have a mapping of this particular net, so it could be a number instead of the name, and then there will be the node name. This last field denotes the total lumped capacitance of this net. Unit of this capacitance have to be obtained from the header section. This line starts the con section, that is connectivity section. This line gives the first connectivity information of the concerned net. Here, this I refers to the internal pin. The pin E and the total hierarchy up to E is also included in the name. The next field I, here you can see the I, means it's a input pin. The next field *C means that the next two fields are X and Y coordinates. So this is X coordinate and this is Y coordinate. The *L means we have a loading value. The next numerical value is the load value of the P. This is the input load of this particular P. This next line is very similar to the previous line we have just discussed, and this is for pin A. And here you can see that up to this the hierarchy is, and here it is I, and here the X and Y coordinates, and here is the load capacitance value. In this next line, we see a bit of difference. Let me explain. The pin name is Z. We can see the hierarchy down to Z. Here we go down hierarchy to Z. The next field O means it is an output pin. Then *C denotes the next two fields are X and Y coordinate. This is X coordinate and this is Y coordinate. These are coordinates in actual layout. The next field is *D. This gives the driving cell name of this pin as the next field. Here the driving cell name is OR2M1P. So this is the driving cell. The next line starts the capacitor section. This means the *cap starts the capacitor section. In this section, we will encounter capacitance and coupling capacitances. The normal capacitances has only one net name followed by its capacitance value. The coupling capacitance has two net names in between which the coupling capacitance is connected and calculated. The coupling capacitance numerical value will be the last field of the line.
The first capacitance of the cap section is a simple capacitance. The first field is the capacitance count number, which here starts with 1 and it is incremented by 1 for any subsequent capacitors. You will see as the example proceeds. The next field in the line is the net name, including the pin name with a colon separated at the last. This field is a number, then it will denote an internal node instead of a pin, which is usually a alphabet. So here, instead of a alphabet, if we have a number, it will denote an internal node. The next field is the capacitance value for pin or node, whichever is applicable. This is the capacitance value. This is the lumped capacitance value or the capacitance with respect to the ground, because this is a simple capacitor expression. The next capacitance, we can see the first field is incremented by 1 and it has become 2, as I just mentioned. Here we have two net names. One has a pin name A, another one has the pin name Z. If we had numbers instead of A or Z, that would mean these are internal nodes. The last field gives the numerical value of the coupling capacitance. So this is the coupling capacitance in between these two nodes, or pins here rather. And the example before, it was the lumped capacitance with respect to the ground. So here is the difference of the two kind of capacitance expression. This next capacitance again is a simple capacitance to the ground. You can interpret this as same as before. The next line, that is star res, denotes the beginning of the resistor section. Here in this line, the first field is the identifier, also known as the counter, which increments by the value 1 for any further subsequent resistors. The next two fields are two nodes in between the resistor is connected. So this is node 1 and this is node 2. Here in this case, these are two pins. In case these E and Z are integers or alphanumeric value, they will denote a node instead of pin. The last field here is the resistor's numerical value. The unit can be found in the header section. So the resistance section is very much simple, and it has only one particular format, that is two nodes in between the resistor is connected, and the last field is the resistance value. The next resistor has the same format as just we have discussed. And again, this has the same format too. Here comes the star end, which ends the dnet block that we started with the dnet text. Here we started the dnet block with this d_net, and here we end this particular dnet block for this particular net with the star end. So this is the opening and this is the closing of the dnet block. Before concluding here, few more things I would like to mention. When a metal routing is breaking into several pieces, it creates multiple resistors. Now, this breaking into is done by the extraction engine. No designer does this, but the extraction engine, for its calculation purpose and the algorithm, it breaks it down for a long metal piece into multiple shorter metal pieces, which are also represented as resistors. Such two neighboring resistors will have one node common in between them. Their order may be anywhere in the entire res section or the block, but the common thing will be they will have a particular node common. So if you see such resistors inside a single res block, you will understand this is the two section of the same metal routing piece. For EMIR, we dump additional tail comments of all the R, P or CC, that is resistor capacitance and coupling capacitors. From this tail comment, we also get the XY coordinates in the actual layout. For resistors, we get the metal or via layer number also. We are done with this particular example and we can move on to the next slide. Standard parasitic extraction format snippet. Here we will go through a miniature version of a SPEF file. Okay guys, one thing to be very frank here, we cannot squeeze an entire SPEF file in a single slide. I have tailored it and removed the bulges and make it oversimplistic for you just to grasp the entire SPEF in one single shot into your mind. Here is our total SPEF file. This is a snippet. This is not a real SPEF file. This is just for your understanding and educational purpose. Here is the snippet we included in the layer map and the tail comment, which are interdependent. Here you can see that we have the header section,
Then we have the name map section. Then we have ports, and this clear map section is contributed by these tail comments. Whenever we put tail comments, we get this clear map. Then we have a DNet section, which has the con, cap, and the rest section we have just described sometimes back. The purpose of this slide is just to imprint the SPEF file structure into your mind. Let me rephrase again. Here goes our header section, then comes our name map section, then comes our port section. The layer map section comes the next. This is associated with the tail comment. Whenever the tail comment is there, we need the layer map, otherwise we don't. Next comes the DNet section, in which we have subsections as con, cap, and res. And here you can see that if there is a LVL, it is 23, means here if we go back to layer map, it will point out that here 23 is metal 2. So this register is a metal 2. Such tail comments, and again I have trimmed it down. There will be XY coordinate values from which you can actually go to the layout. And since this is a metal piece, there will be W and L, that is, it will be a rectangular piece. So length and width, this is length and this is width. So if it is a via, then instead of W and L, here will be A equal to some value, that is the area. For vias we have area because vias are square generally. I think I have given enough details about this snippet. Hello and welcome to the 9th episode of Static Timing Analysis. In today's episode, we will discuss about the SDF file in a nutshell. The full name of SDF is Standard Delay Format. We have seen other files to contain the delay information of various kinds. All other files contain delay as a whole for the entire standard cell library or the entire sea of interconnect. They may have surplus information with respect to the design under consideration. SDF contains all sort of delay information in a compact fashion specific only and only to the design. Another beauty of SDF is that this is a file that can be generated in multiple stages of the ASIC design. We can take a SDF generated at synthesis stage to PNR, and opposite direction is also true. Even we can take SDF generated at post-layout STA back into the pre-layout STA. So in a nutshell, SDF file can move back and forth in the entire ASIC design flow. So here goes our today's menu. Introduction to the SDF file. Next is what is inside the SDF file. Limitation of SDF file. SDF file structure, that is header, tail, and timing sections. Next is SDF file description of each section. Next, example of SDF file, a snippet. Finally, we talk about another file, that is TWF file in a nutshell. So here is our menu for today. So let's begin. SDF introduction. Now let us have the biodata of the SDF file. Standard Delay Format SDF is an IEEE standard for the representation and interpretation of timing data. It was born with OBI standard, later ported into the IEEE standard from version 4.0 onwards. It is an ASCII format, that is human readable file. It creates a bridge between dynamic and static timing analysis. SDF file includes path delays, timing constraint values, interconnect delays, and high-level technology parameters. It has usually two sections, one for the interconnect delays and the other for cell delays. SDF is compatible for both back annotation and forward annotation. So we are done with this particular slide, so let's move on. We continue here. Let's complete the biodata of SDF file in this slide. Throughout the design process, you may use several different SDF files, because the reason already I have said that many EDA tools can generate the SDF. So one may be generated at the synthesis level, another may be generated at the STA, another may be generated at the PNR by different tools. They may be from the same vendor or maybe from a different vendor. And the beauty of SDF is that it can be done a backward annotation and a forward annotation. So that means you can take a SDF from the PNR stage and come back to the synthesis stage. So that's why you will face a different SDF files. And another thing also, when there is a big company, there will be multiple design teams. One design team is working at the synthesis level, another may be working at the static timing analysis, another team may be working for the PNR level, and so on. So each team may be using also a different software, maybe from different EDA vendors. That is the reason you may face various SDF files in the entire ASIC design flow. The data in the SDF file is represented in tool independent way. It can be well understood. Just now I have said that SDF file is generated by multiple tools and they are from various vendors. That's why the SDF is tool independent format, and it is basically right now in a IEEE format. Some of these files can contain pre-layout timing data. As I've already mentioned that maybe it is generated from the synthesis stage or maybe from the pre-layout STA. Then obviously it will contain the pre-layout data. If it is generated from the post-layout STA or PNR stage, then it will contain the post-layout data. While others can contain path, constraint, or post-layout timing data. So this is basically the fact from which stage the SDF is getting generated. So at that stage, whatever the data is unique from the any other stage will come to the SDF. The name of each SDF file is determined by the EDA tool. So each EDA tool may create the SDF file with a different name. Generally, there must be a thumb rule that if you are working at the STA level, the name may contain the text STA. If it is generated by the PNR, it may contain the text PNR. The conventions are different from one company to another company. There is no naming convention for the SDF files. In general, there is no thumb rule how you name a SDF file. This may be from a convention specific to a company, or you may write the name as you like or as you can identify. So we are done with the SDF introduction, so let's move on. What is inside the SDF file? To describe the SDF in vivid detail will cause multiple episodes. So in this episode, we will have a compact idea of the SDF file. In this slide, we are having a bird's eye view of the SDF file. So here we go. A SDF file may include any or all of the below things. Delays of module path, device, interconnect, and port, incremental and absolute delays. That's all the kinds of delays can be inside the SDF file. Next comes the timing checks: setup, hold, recovery, removal, skew, wait period, and no change. So all these types of timing checks can be included inside the SDF. Timing constraints: path, skew, period, sum, and diff. So all these type of timing constraints can be included in the SDF file. Timing environment: intended operating timing environment. Scaling, environmental, and technology parameters. The scaling, environment, and technology parameters may come from the PDK and other things. All this other data can come inside the SDF. We are done with this particular slide, so let's move on. Limitation of SDF file. In this slide, we will discuss the boundary conditions with which the SDF file have to operate. This will give us the realistic picture of the SDF file. Here we go. An SDF file contains timing data for a specific design. This is very important because SDF is not for the entire standard cell library. It is not for any other designs, and to be very precise to the point, a SDF is specific to the design on which you are working. Other design, if you go, the SDF file will be completely different. For one particular design, one SDF will be there. Now, this SDF for in the ASIC design flow can be generated at different stages, but they will have some common things and there will be some uncommon things as per the stage where they are designed. The contents of the file is very much specific to a region of the design or specific to a whole design. Now this another point should be taken carefully, that SDF may be for a region. That means it could be for a design block. Already we have spoken for the whole design. The SDF annotator cannot annotate if there is mismatch between a design description and its corresponding SDF. the naming of the objects must be consistent in these two places. So the naming convention must be consistent, otherwise there will be a mismatch. Therefore, changes to the design generally require the rerun of a timing calculator to generate the SDF file. Inside the design, if you have changed something, maybe its hierarchy, maybe something addition, some subtraction, anything, or maybe renaming of any port or anything like that. So those all things cannot automatically come inside the SDF. SDF has to be manually generated by the user. During annotation, inconsistencies between the SDF file and the design description are considered as error. So the annotator tool checks between the design, maybe it's a Verilog description, synthesized netlist, or maybe I've already done a PNR version of the design. So if there is inconsistency between the SDF and that particular design or any format, the annotator will flag out an error. So these are the realistic boundary condition of the SDF file. We are done with this particular slide, so let's move on. SDF file structure. As we have already mentioned that the SDF have the design specific data only. Now let us look into how this is organized inside the SDF file. Here we go. First, there is a header section. We continue downwards. Then there will be cell 1, cell 2, cell 3, all the cells that are picked up from the standard cell library for this particular disk. Those picked up cells will be here. We'll explain all of these things upcoming slide with definition plus example. So we are done with this particular slide. So let's move on. SDF file, the header section. The SDF file have a header section and it do not have a footer section. So let's get familiar with the header section now. The header section of an SDF file contains information that relates to the file as a whole. This header section is a kind of identity card for the whole file. Most sections are documentation purpose only and do not affect the interpretation of the data in the rest of the file. So these are basically maybe comments and for the end user to read it, just for the identification purpose. Key sections that impact interpretation are hierarchy divider and timescale. So here, this hierarchy divider and the timescale, these will have some impact on the tool and the design. So this is in a nutshell what is the impact of the header section. So let us move on. We have some further details for the header section remaining. Let's cover it up. In this and the next slide, we will have a short and sweet description of the header section using tabular data. Here we go with our table. So let me bring my mouse pointer here. It has come. So SDF version is here. There will be a tag of SDF version. What it means, the SDF version is the entry identifies the version of the standard delay format specification for which the file conforms. So it will contain the SDF version, then Q string. Q string is nothing but a string, that is text. Design name. The design name entry keeps the record of the respective design to which it belongs to. So you have a design, probably as per your company, you have given it a name. So that name will be here. So design and then Q string. Q string means, again I am saying, it's a text. Date entry records the date of creation of the SDF file and it is also date and Q string, the format. So this is a very important entry because when we are going through the entire ASIC flow, sometimes you have to multiple time iterate and multiple time you have to generate, right? In case you face the same name of the file in two different locations, how do you identify they are same or different or they were generated on the same day? So this field will help you. Other than that, you can do a GVMD for TKD to find out the content difference. That is fine. But how do you know that which date it was generated? Date entry will help you to get that. Vendor entry. This keeps the record of the manufacturing company. It's also the format of vendor and Q string. So the company in which you are working, that name will come here. Program name keeps the record of the parent software program which creates the SDF file. So as I said, the SDF can be generated by any step of the ASIC flow. That tool which is generating the SDF file, that name will be kept here. Format is program then Q string. Q string is nothing but a text. This will help you to identify at what stage this particular SDF is done. So if it is generated in the synthesis stage, the name of the synthesis tool will be here. It is generated in the pre-layout SDF, then the tool name will be there. If it is generated in the PNR, then the PNR tool name will be there. Like this, whatever program has generated the SDF, the name will be there. We are complete with this table and we are having another table like this in next slide. We continue the table in this slide. Here we go. So let me bring my mouse pointer. So here is the program version that keeps the record of the parent software program version. So yes, maybe a design cycle is taking 7-8 months. Generally after each 3 months, EDA tool vendor releases a new version of the program. In case you need to confirm which version of the same program you have used, so this field will help you. So syntax is version then QString. Hierarchy divider. This records the hierarchy separator. Limit is 2 characters. So syntax is divider then hchar. This is nothing but alphabets. 2 alphabets will be there. It may be slash or colon, whatever. So this hierarchy separator is nothing but if you have a hierarchical design from going from the top level to the block level, you need to go through a lot of hierarchy down to the last smallest block. So all those hierarchy are separated by the hierarchy separator. Voltage entry. This records the voltages for which the SDF data generation has taken place. So here the format could be voltage then R triple. At some later slide we will describe about this R triple. It is nothing but 3 real number separated by colon. Then another syntax could be voltage then R number. Process entry. This records the process for which the SDF data generation has taken place. It is the process and the QString. Temperature entry. This records the temperature for which the SDF data generation has been taken place. So as we know that I am talking about these 3 things: voltage, process and temperature. If you can see, generally we have different PVT corners for which we optimize the design. Those PVT data will come through this process, voltage and temperature entry inside the SDF file. You can identify at which PVT corner this SDF is generated. Then we have the timescale entry. This specifies the timescale entry which is globally applicable to any time entry in the entire SDF file. So here the format is timescale then TS value. So here will be the timescale value. So if you remember that in Verilog file you have a backtick timescale where you define the timescale, right? The same thing will come here. We are done with this particular slide, so let's move on. SDF file, cell and its type. So the design is synthesized using standard cells. The library of standard cells is huge, but a subset of the entire library used in the design comes into the SDF. We can get the delay of these cells in the cell section. Let us see how this data is organized in the cell section. Cell entry represents either a region or a scope within a design. For example, a 2-input NAND gate or a flip-flop. So these could be the instances of the cells from the actual standard cell library. Hence, they can be region. Physically, if you look into the layout, any cell is basically a region. And programming or coding wise, it could be called as a scope. So I explained these 2 lines. Now let's move on to the third one. Data is applied to such library specific regions in the design. The data will be very much specific to the region. This is the property of SDF or limitation of SDF or boundary of SDF, whatever you call. The syntax is cell, then cell type, then it could be a cell instance or could be timing spec. So they are marked in bold. So this is the syntax. We will see some examples later. Cell type. The cell type indicates the name of the cell. Why then we call cell type? Why not name? Because the cell type means, say in standard cell library, there will be different types of cells. It could be a combinational or sequential or special cells. So that's why it is called cell type and not a cell name. So it's more generic in that sense. Syntax, cell type, then QString. That means a text. QString, I think it's maybe the quoted string. That means within the quotes it's the string. That means it's basically a text. The examples like cell type, then DFF, D flip-flop, cell type top, it could be top of the design, cell type buff could be the buffer. So this way, these are the examples. We are done with this particular slide. Let's move on. Cell instance. A single standard cell can be instantiated in multiple zones of the design. According to the placement, we may or may not have the same data of a single cell. To deal with such cases, we have the cell instance section. Let us see how this is defined in SDF. The cell instance targets the specific instance or wildcard instances on which the timing data is to be applied. Syntax is like instance then path or instance then wildcard. Okay, we'll see with the examples, we'll understand how. And instance means it's at the down the hierarchy up to a block or inside, even go inside a block. So path comes from that factor. Example, cell, then we have cell type DFF, then we have instance, then A1.B1.C1 and we go on. Here the dot is the hierarchy separator. A1 is the topmost block and C1 is the instance.
then again cell, then cell type DFF, then instance, then tar. So in the first case, the SDF data, annotation data will be specific to the instance C1. So it is very much specific to that instance. And in the second case, here when we are using the wildcard, the SDF annotation data is generic. That means the same data can be applied anywhere with the cell type DFF. So we have done the explanation and let's move on. Now we plunge further down inside a cell for the timing related data. In this and upcoming slides, we will unfold the timing section inside a cell or cell instance. Here we start. Timing specification. Each cell has three types of timing information such as delay, timing check, and timing environment keywords. Syntax is for delay we have del type, for timing check we have timing check definition, and for timing environment we have timing environment definition. Delay keywords represents the associated delay values of input to output paths, input ports, interconnects, and device outputs. All of these are considered under the delay keyword. We are done with this particular slide, so let's move on. Timing section, the path pulse. When a signal passes through a cell instance, we have a checkpoint depending on the pulse width. This is path pulse. Here we have two pulse width thresholds which a signal has to satisfy to cross the cell. These thresholds have unit equal to the time unit of the simulation. So let's start. The path pulse entry represents the narrow pulse propagation limits associated with a legal path traced between an input port and an output port of a device. These limits determine whether a pulse or a certain width can pass through the device and appear at the output. So this is basically having two threshold criteria for one particular cell where there is an input port and there is an output port. If the pulse satisfies the two thresholds, it will pass through it. So here goes our example, instance, and then we have delay, then we have path pulse, I1, 01, then 13 and 21. So here let me bring my mouse. Instance, I have marked a generic X here. Okay, it could be any instance, and the path pulse is between the input port I1 and between the output port 01. The first threshold for I1 is 13 into the time units as per the header section. And for output, the threshold is 21 multiplied by the time unit, and the time unit can be found in the header section. So thus, the path pulse is defined. Now, let us see some more examples. Instance X and then delay and then absolute, IO path, close. Okay, we come again to the path pulse statement. We are not discussing about the delay, absolute delay or everything. We will discuss it later. So, the path pulse here again between A and Y, and the two thresholds are 13 and 24. Each can be multiplied with the time unit and the final value will be the threshold. Path pulse of BY is 15 and 21. So the path pulse between the input node V1 and output node Y is the two thresholds are 15 and 21. And here we close it. So this is in short and sweet description of the path pulse. Here we come to the next slide, path pulse percent. The path pulse percent is another type of representation in forms of percentage. The rest of the idea from the previous slides remain the same, except here it is the percentage. Let us see. The path pulse percent is an entry is same as the path pulse, but the values are expressed as percentage of the cell path delay from input to the output. There goes our example, instance X and delay, and then we have absolute delay, IO path, cross, and now we come to the path pulse percent, that is between A and Y is 25 and 35. Format I have already explained, so let's move on to timing section, absolute delay. Now let us see how absolute delay values are organized inside the SDF file. So last couple of slides we are seeing the absolute and the delay. Okay, now let us discuss about this one. Here there are two placeholders. Let's start. The absolute keyword introduces delay data that represents existing delay values in the design during annotation. Cell type, here goes our example. Cell type is DFF. Then instance is A.B.C. Then we have delay, and then we have absolute, and then we have IO path, then posage and clock, and then Q. Then we have two R triple format, that is trivial number separated by colon, and such two set of data is there. So for port CLR, we have again two RTTL format, and here we close and close and close. So this is the absolute delay. So this IO path and the port, these are the values of the delay. Now just pause here. This RTTL format needs to be described in detail. So wait for that. First, you see how this is written inside the DFF. Next, we go for the explanation. So here we have another instance, delay, and then we have absolute, then we have port R1.A, and then we again have the RTTL format. And then again we have another port that is R2.A, and we again have the RTTL format. So difference is between that, in the left one case, in the yellow box, we have from one particular pin to another particular pin, and like passage of clock to Q. And here in the right hand side, we have a single particular port. We also have a port in that left and yellow box, CLR. For that we have RTTL format, but here also you can see that here only the things are two ports. We close it. We will explain the RTTL format in the next slide. So let us move on. RTTL format, let us discuss. We have just seen the examples where there were t numerical values separated by colon and packed together using a pair of parentheses. Now let us see how the interpretation comes for these ones. When a single value is used, it specifies the delay value. When two values in parentheses are used, the first value specifies the delay as if a single value were given. The second specified both the pulse rejection limit and E limit associated with this particular delay. When three values are there, the first specifies the delay, the second specifies the pulse rejection limit, and the third specifies the E limit. So if there is a RTTL, the first one is delay, second one is the pulse rejection limit, and third one is the E limit. If there are two values, then the second bullet will be applicable. And if there is one value, the first bullet here in this page will be applicable. Each value is either a single real number or a RTTL containing three real numbers separated by colons in parentheses. Just I have explained. So I think we are done with the RTTL format in this particular slide. So let's move on. Increment delay. Here we will talk about the delay values which are appended to the existing delay values upon the annotation. This means here we are talking about such delay which will sit on top of the existing delay when we annotate. The increment keyword introduces delay data that is added to the existing delay values in the design during the annotation. Here we go with our example. Instance is A.B.C. Then we have delay, and then we have increment, and here we have the IO path. Then we have passage of clock to Q, then 4::2, then -7::5. And here we have port, one particular port, CLR 2:3:4 and 5:6:7. We close it. Close and close. So here you can see this increment keyword. Let me bring my mouse on. Yes. So here everything is same here as with the previous example, except this difference. This increment keyword is here. This means whatever the delays coming out of these expressions will sit on top when these are annotated with existing delay at that particular stage where we are injecting this SDF. So I think we are very much clear on the incremental delay. So let's move on. Example of SDF file, a snippet. Since we cannot squeeze a whole SDF into single slide, hence we have trimmed it down in this particular slide. Hence we call it a snippet. Here is our left box and here is our right box. In these two, we will try to stuff one single SDF in a very miniature version. So here goes our header section, delay file, then SDF version, then design top, then date, then time, vendor, program, which program we are using to generate it. Here we have version, and here we have divider, and here goes our voltage, process, temperature. So the last three entries are PVT entries: process, temperature, and voltage. Also here the hierarchy divider, just above that, that is dot. Time scale is 1 nanosecond. This is same as the backtick time scale. So cell, and then cell type XOR2. Here starts our cell, and instance top.x1, and here we go for its delay, and we have the increment, and we come with our statement inside it. On this condition, So come to here and we go continue, and finally we continue, and here we close. Here we have just tried to keep a snippet of the entire SDF file in a short and sweet fashion. So conditions we have not, it's like a if else then condition. That's all with this particular snippet. I have nothing more to say on this. So let's move on to the next slide. So this slide is not from the SDF, but here we talk about TWF file in a nutshell. One of our viewer requested to put the TWF file in STS series. Now let us see the TWF file in a nutshell. Some of the STA tool can generate a TWF file which contain information about switching window and transition times, both of which have a large impact on dynamic power. So this TWF file will contain about the switching window and transition data. Pickle command to write out the TWF file is write_TWF then file name. So this is basically, it may be a vendor specific. When I was looking for TWF file, I came across that it is a very vendor specific file, and in that particular vendor you can write it with the write_TWF. TWF contains timing window and slew data. Tool finds the earliest and the latest arrival times for each victim net and aggressor net. The range of switching times between from the earliest to the latest arrival defines a timing window for victim net and defines another timing window for the aggressor net. So all of this data you can find inside the TWF file. Crosstalk effects occur when the victim and aggressor windows overlap. So this is the outcome of the data that you can interpret from the TWF file. So that's all folks. We're done with this particular slide. Let's move on.
Hey guys, welcome to the 17th episode of Q&A. Viewer Swati Kulkarni has asked in the 5th episode of Static Timing Analysis series, Sir, can we do STA for gated clock circuit? I am not getting what to consider. She was designing a PUF circuit at her end. In the theoretical episodes of the STA in this channel, the clock gating topic was not covered. Hence, in this episode, we will go through the fundamentals of clock gating first and then immediately after provide the answer to Swati's question. Stay tuned till the end of this episode to know the basic know-how of clock gating concept in STA.
Today's episode is split around in the below topics. What is clock gating? How clock gating impacts the circuit? How clock gating is implemented in the design? How does STA detect clock gating? What happens after the detection? And finally, we summarize everything. We are done with the menu. Let's move on to the topic. What is clock gating? Clock gating is a popular VLSI technique used in many synchronous circuits for reducing dynamic power dissipation. By using clock gating, the clock signal is removed when the clock is not in use. Cutting away the clock disables the portion of the circuitry so that the flip-flops in them do not have to switch states. So till these 3 points, it's a bit clear to you, right? That this clock gating is meant for power management. That means power saving. And where do we do the most of the power saving nowadays? Yes, it's the handheld devices like a mobile phone or a smartwatch or any other wearable devices. Will come shortly. Switch state consumes power. When not being switched, the switching power consumption goes to 0 and only the leakage currents are incurred. So this way we can optimize the power of any battery powered device. Thus, clock gating saves power by cutting away the clock tree at the cost of adding some more logic to a circuit. Now, when you try to optimize something, obviously some cost you have to pay. Here, it is nothing but adding a bit more circuitry into the main design. Clock gating works by taking the enable condition attached to the registers and uses them to gate clocks. This is one way. The design must contain these enable condition in order to use them and benefit from the clock gating. So shortly we will see there are some other ways of the clock gating too, but basically this is the main fundamental thing that happens in a clock gating. So all these bullets and the points and the informations in these bullets are very clear and straightforward. So without any further explanation, let's move on to the next slide. How clock gating impacts the circuit. Clock gating removes large number of multiplexers and replaces them with clock gating logic. This is what is done at the gate level, that is at the logic gate level by the clock gating methodology. Thus, clock gating process saves significant die area as well as power. Now you get the benefit. This clock gating logic is in the form of integrated clock gating cells, also known as ICG cells. These are part of the standard cell library. The clock gating logic will change the clock tree structure since the clock gating logic will sit in the clock tree. So thus, the clock gating impacts the entire circuit. We are done with this particular slide. Let's move on to the next slide. How clock gating is implemented in the design. Now this comes the real question. How it is implemented? Let's see. Coded into the register transfer level code as enable conditions that can automatically translate it into the clock gating logic by the synthesis tool. So this is one way that you can do it at the very beginning at the RTL code level and encode it in such a way that the clock gating logic is automatically implemented by the synthesis tool. That means where the Verilog or VHDL code is transferred into the actual gates. Inserted into the design manually by the RTL designers, typically as the module level clock gating by instantiating library specific ICG cells to get the clocks of specific modules or registers. Now, this is another way. First is the RTL modification, second using the ICG cells. Semi-automatically inserted into the RTL by automated clock gating tools. These tools either insert ICG cells into the RTL or add enable condition into the RTL code. This could be the third option where either the RTL modification or the ICG cell insertion can be judiciously done by the clock gating tool in an automated way. So the next point is chips used in the mobile devices, not only mobile devices, wearable devices also, such as mobile devices, that is mobile phones, wearable devices, etc. would implement several forms of clock gating combined together. So, as we have the mobile devices, the battery power is very low and it has to sustain for a long time. Say you are using a smartwatch, it has to run long, at least half of the day, or best is the full of the day. So the power saving must be done, and that can be done with the judicious distribution of the multiple methods as discussed in this slide for the clock gating. However, there are several other power optimizations are there. I am not going to those because in today's episode we are focusing only on the clock gating. We are done with this particular slide. Let's move on. How does STA detects the clock gating? This is a very crucial question. You are thinking how the engine can grab the clock gating clock or the code or both from the design. Let us see. First, we have to trigger the clock gating check in the ST engine by using the command set clock gating check. First, we have to trigger clock gating check in the ST engine by the command set clock gating check, then dash setup, then asval, and then dash hold, and then ageval. So this is the compact command. Now asval is the amount of setup time cushion needed. Ageval is the amount of hold time cushion needed. If you don't know these two terms, I would request you to go through the ST playlist in this channel and find out the setup and hold analysis discussed in one of the episodes. The thumbnail speaks by itself, so you can find it out. Reading our input through this command, STA tool recognizes the latch in the clock gating circuit and assumes that this is a latch path. So now what we are going through, that how the tool detects this particular clock gating and what it does with after it finds it. So the ST tool further divides the path into two parts. Front path. This is the path in front of the latch. Back path. This is the path in the back of the latch. What happens after the detection? We come here very fast immediately after the last slide. This is the continuation of the last slide. STA algorithm will first analyze the front path. It will borrow time across the latch so that the front path can meet timing.
Then it analyzes the back path given the amount of borrowing it did on the front path. Thus, it leaves the violations on the back path even though the front path appears to be meeting timing. Next, the tool recognizes that a failure in the back path can be improved by optimizing the front path. With STA, we have actual net delays, and so we can correct the time borrowing for each latch individually with high accuracy. To do so, we use set max time borrow command to allow the just enough time on the back path for glitch free operation while forcing all available slack to the front path. So these all things happen the post detection part, and this command at the last bullet we manually have to enter. We are done with this particular slide, so let's move on. Summary. STA does not have the analysis problem associated with the ideal clocks as long as the STA is run with detailed actual clock network analysis. Generally, when we reach up to the stage STA, you can find out. I have already displayed the flowchart in this particular static timing analysis series, first or second episode of this series. When the flow comes up to the STA, this actual clock network is ready. STA does incorrectly divide the clock path into two separate paths, thus obscuring potential critical paths. There could be critical paths where it does the algorithm for the clock gating. Some critical paths will get adopted. However, for up-to-date algorithm and methodology, please consult your respective STA tools' latest manual so that you do not miss out any up-to-date command or methodology that can cure the usual way of dealing with the clock gating paths. So folks, we are done with this particular slide. Let's move on. Hey guys, welcome to the 18th episode of Q&A. Viewer Mansoor Ali has asked in the third episode of Static Timing Analysis, what is POCV in STA? He is a fresher and hence looking for the fundamentals to understand POCV. In the theoretical episodes of STA in this channel, the statistical STA was not covered. Hence, in this episode, we will go through the fundamentals of statistical STA in dealing with the on-chip variation first, and then we will discuss its practical implementation as POCV. Stay tuned till the end of this episode to cover the basic know-how of parametric on-chip variation in statistical STA. Today in this episode, we will cover the below topics. First, we will discuss what is on-chip variation. Next, we will discuss the STA limitation, and from that point, the statistical STA begins. The statistical STA basic algorithm is the next thing that we are going to discuss. Then we will discuss what is POCV. Next, we will discuss the basic delay equation in POCV. We will understand how the POCV input files are different from the regular static timing analysis input files. And at the last, we will discuss the command that you need to invoke the POCV in the STA tool. So folks, this is the menu for today, and let's begin. What is on-chip variation? Now, before going any further, I would like to say that the POCV, the last P alphabet is OCV. So I have kept this slide. Although similar slide was already there in the STA series, I have kept specifically here to reiterate the facts on OCV. Now, what is on-chip variation? On-chip variation is a recognition of intrinsic variability of semiconductor processes and their impact on the factors such as logic timing. So this is a kind of dictionary definition of the on-chip variation. Next, PVT variation is inter-die, also known as global variation. We have already discussed about the PVT variation in the ST episode. Now, why I kept this? Because there is a striking difference between the PVT variation versus the on-chip variation. Now, intra-die, that is single wafer variation, is termed as the OCV variation, also known as the local variation. The on-chip variation is intra-die, that is within a single wafer, and all about the spatial distribution of the variant.
The OCV effect is predominant on longer physical path in a chip. So there are start point and end point of very many timing paths which are very long in nature and going from one end to the another end of a single wafer. Although every chip size is much smaller than the whole wafer, however, in direction wise, this path can run from one end to another. So on those paths, the OCV effect is very much important. OCV variation impacted by temperature variation by 10 to 20 degrees centigrade. Hence, more OCV specific corners come into the picture than though typical first. I would like to mention here one thing. If you open up any standard cell library distribution, right, you will find typical, slow, fast, and there are many combinations of all these PVT corners. Now, those are PVT corners. That is PVT variation. That is inter-die variation. But for OCV, generally we have a kind of format in the timing.lib that is called LVF. Come to that later words. However, this is much more important in sub-nanometer region chips, the OCV factor, and we proceed to the next bullet. The STA incorporate OCV effect by derating delays of the specific path. Both cell and net delay are subject to derating effect. So derating is nothing but a method of manipulation or to the existing delay with a particular mathematical expression. So that is derating, and that actually can replicate the OCV delays. There is no on-chip variation. That is the single wafer variation. OCV effect can be implemented in the STA tool using the following command. Let timing derate early or late, whatever value you give, you can specify there. So folks, we are done with this particular slide. So let's move on to the next slide. STA limitations and statistical STA. Now, so far we have discussed about the STA. Inside that we have discussed the OCV, and at some point this get a roadblock. Let us look into that particular area. Conventional STA cannot easily handle intra-die correlation, especially if the spatial correlation is included. I mentioned this word spatial distribution few slides back already. Now here you can see it. For intra-die variation, STA needs many corners to handle all possible cases. This is achieved at the cost of more standard cell characterization, time and resource budget that has an effect on the manpower who are generating the library, the standard cell library, the timing library, and all the dependent files and folders, whatever they are. Next. This motivated semiconductor research and development bodies to look for a more into a modern practical approach to perform static timing analysis. So this roadblock that for intra-die variation we have to create much more number of corners that will cause the standard cell characterization in a massive scale, and we get the corners after that, and then we do the STA for the intra-die variation. So this roadblock pushed all the research and development bodies in latest semiconductor industry to think for a much more modern approach. They borrowed the concept of statistics. That is, likely you are familiar with the word probability, standard deviation, etc. Yes, those comes from the statistics. They brought this statistics into the STA in a more realistic approach. Statistical STA replaces the regular STA timing of gates and interconnects, that is gates and nets, by the introduction of probability-based distribution. So here the statistics enters into the static timing analysis. Hence, the analysis report gives a set of all possible circuit output combination rather than a single situation. This is much more practical approach in sub-nanometer era. Now, when we have our conventional STA, we get the output, one single output for one particular path, about whatever we are looking for there. That is what we are considering right now. However, when we use the statistical STA, we get a statistical distribution, and the result is also containing the statistical result, which will contain much more possible output combination rather than a single particular situation. So this is much more acceptable, because when all the things are varying inside a single die, that is a single wafer, we do not know what is happening where, and better to consider all of them before our chip actually goes on to silicon and fails. The silicon failure is not at all welcome by any of the chip designing houses, because if the chip fails at silicon, they will have to face a huge market loss. So to stop that, in a sub-nanometer era, the statistical approach, the statistical way of analysis and the output interpretation and taking actions accordingly will help lesser number of silicon failures. So this is the significance where the boundary line of STA stops. On the other side of the boundary, the statistical STA starts acting. Folks, we are done with this particular slide. Let's move on. Statistical STA basic algorithms. This slide is kept for your basic know-how. When you are going through any particular tool manual, you might across come of one or both of the algorithms. That is why we are touch basing this slide. It's not mandatory to know. However, if you know this particular fundamental, it may help you in real-time work. There are two main categories of statistical ST algorithm, that is path-based and block-based. By the name, you can guess path means there is a path related and block means there is a design block. So let us see what are they. A path-based algorithm sums gate and where delays on specific path. The statistical calculation is simple, but the path of interest must be identified prior to running the analysis. There is the potential that some other paths may be relevant but not analyzed. So path selection is very, very important. So here done with the path-based algorithm. Next point is the block-based algorithm. A block-based algorithm generates the arrival time and required time for each node and work forward and backward from the blocked elements. The advantage is completeness and there is no need of path selection. So these are algorithms that happens inside a tool, and the way the tool handles the mathematical computations and playing with the statistical rules there. So that's why all these algorithms are displayed to you, just to have an idea and a kind of virtual visualization what is happening inside your STA tool. The biggest challenge in the algorithm is that a statistical max or mean operation that is also considered. Correlation is needed, which is a hard technical problem. So folks, we are done with this particular slide, and I think a virtual impression of the algorithm has already printed in your mind. So let's move on to the next slide. What is POCV? Now, finally, we come to the slide of our concern of today's episode. POCV stands for parametric on-chip variation, which uses a statistical approach. Up to this point, you have already known that we are dealing with the statistical ST, and POCV is somewhere in this picture. POCV handles the local random variation without requiring the statistical library characterization. POCV works based on statistical Gaussian distribution of cell or net delay instead of adding digit values. It calculates delay variation by modeling intrinsic cell or gate delay and parasitic R and C to determine both statistical mean and sigma variation. So far up to these points, you might have visualized that it is statistical STA. However, there is some plus thing onto it. So that is POCV, what we are discussing right now and what is displayed here. The cell delay is further broken down into N-channel components and P-channel components. You understand what are these two things. Then assume that all the cells along a path have the same mean and sigma. Next, in POCV, cell delay gets calculated from either library or POCV table. We'll come to this. Since POCV is statistics based, it can't slide into just any STA tool. Rather, it needs a statistical STA engine in order to be used. What we mean by that? That all the statistical mathematics have to be enabled in the engine, and that engine is not same as that our conventional STA. We know it theoretically, it is different. The statistics mathematics related to it is very much different than our regular mathematics. So this engine must have all the statistical necessary mathematics and algorithms enabled so that the POCV can run onto it. So here comes the plus factor that I was talking about the POCV. Next, we are discussing the basic delay equation in POCV. Why we need this thing, the basic delay equation? It is again, the tool is doing its calculation. You don't have to bother. However, you need a virtual visualization of what is happening inside. That is the necessity of this equation. Right now, it is getting displayed to you. The new cell delay after the POCV can be defined as delay new is equal to delay original plus delay variable into param. So what are all these things? delay original is the original delay of the cell without applying any delete. Next, delay var is one standard deviation value of the delay distribution of the cell. Param is the standard random variable, that is n. So these are all statistical terms. This way you can visualize the new delay that has been defined inside POCV engine. We are done with this particular slide in a short and sweet manner. Let's move on to the next one. POCV specific input files. So this is the thing that I was mentioning that few slides ago. We will talk about how the input files are different. Mostly the POCV specific files we are talking about here. Rest of the files, whatever we have discussed for STA, they will be there. However, we need some additional files, and these additional files can be provided to the POCV engine in two ways. The first way is POCV liberty variation file. So I just talked about few slides back about this also. It is also called POCV LVF, which is, I think, comes in the timing library. And the second way is we combine two type of files together. The first one is POCV distance delete files, and next one is the POCV coefficient file. So we have two different approach of giving the POCV input files. One is the LVF file, which is on your left side, and on the right hand side there is a combination of distance delete file and coefficient file, which have to be provided together to the POCV engine. So once you deal with the tool, you will come across these files. So in a short and sweet manner, this slide is already discussed. Let's move on to the next slide. POCV STA command. You might be wondering up to this point, so far we have discussed all the theories and everything. However, when we want to invoke the POCV inside our statistical STA tool, what command we should use? So the command is variation underscore analysis. It is the command that is the tickle proc, and the arguments are mode. We give the value as POCV, then we give from and to, that is the path starting point to the path end point. And then we mention about the delay type, that is max for data analysis or mean for hold analysis. So this is, in a short and sweet manner, the command to invoke the POCV. Anything happening statistically, it will be taken care by this particular tickle command. One thing I would like to mention here. Always check your latest tool command manual for the command, because the VLSI industry is always changing, even every day, every minute, every second. So whenever you are trying to use any command, check its latest manual. So there might be some changes or updation. You must adhere to these changes or updation to get the full output from that particular command. So with that, I'll conclude this slide. Let's move on to the next slide.
Hey guys, welcome to the 19th episode of Q&A. Viewer Rajshri has asked in the 18th episode of Q&A from Static Timing Analysis series, what is the difference between AOCV and POCV in STA? In last episode, we have discussed about the OCV and parametric OCV, that is POCV. However, AOCV was not covered. Hence, in this episode, we will go through the fundamentals of advanced on-chip variation, that is AOCV in STA. If you watch the last episode and this episode back to back, then you will be able to differentiate OCV, AOCV and POCV. Stay tuned till the end of this episode to cover basic know-how of the AOCV in STA.
In today's episode, we will be discussing about what is AOCV, which is also known by another name LOCV, working principle of AOCV or AOCV, understanding the LOCV or AOCV derating table, timing dot-need data format or AOCV or LOCV, the analysis types of LOCV or AOCV. So that's the main for today. Without any further ado, let's begin. What is AOCV or AOCV? So this AOCV is implemented for intra-die, that is single wafer timing variability analysis. This point is the same as the OCV. However, it is less pessimistic than the traditional OCV, which has a fixed derating value. Means that the derating is a kind of constant everywhere for every gate, and it do not have any kind of distance or path relationship. It's just a static number. So in actual practice, when there is a wafer and the process through which the semiconductor chip is made, all those variations, the process variations happens various parts of a single wafer itself. If we traverse from one end to the another end of a single wafer, there may be difference. The difference can be found even for a single process step. So how can the effect be same or very pessimistic? However, these AOCV things became very prominent around the 65 nanometer node or below. Above 90 nanometer node, there was no need to see about a AOCV or LOCV. But in the sub-nanometer domain, when we went down around or below the 65 nanometer node, that time this AOCV has a great importance. Degating is a function of path or graph in AOCV or LOCV. So as I just mentioned, that if I go from one end to the another end of a single wafer, how we move on top of the wafer, definitely there will be a path. And the graph is another concept in VLSI, especially in timing. So degating here in AOCV is a function that is dependent on path or graph. Hence, the name is appropriate, location-based OCV. Why it is important? Because this location-based OCV, the locations are determined by the path. Hence, the name is much appropriate, the location-based OCV. Or the more popular name of it attached to it is advanced OCV, that is AOCV. In the industry, the less common name is LOCV and the more common name is AOCV. So, we are going to mostly call by the name advanced OCV or AOCV. This is a non-statistical method as compared to the parametric OCV, that is EOCV. With EOCV already we have discussed in the last episode of Q&A, and that was a statistical method. However, this is not a statistical method. It is an advanced version of the Ponzi variation where we take the consideration of the deviating variation depending upon the path in traversing one end of the wafer with another end of the wafer of the single chip. However, in these paths, there will be logic gates. We are not moving randomly. We are done with this particular slide, so let's move on. Working principle of LOCV or EOCV. In this method, the cell or gate deduct varies with logic depth, that is hierarchy, and based on the path or graph. Logic depth, you understand that the gates are connected or the blocks are connected and we go inside a block, we have a sub block. These three have the logic depth or the hierarchy. This path may extend from one end to the other end of the same chip, that is the wafer. Already I have a couple of times mentioned this thing. Such path may not consist only a single type of gate, rather various gates. Obviously, the design will contain multiple types of gates inside the silicon wafer. In this path, equal and opposite kind of degating may partially or fully neutralize each other's effect. This is theoretical. In practical, you can see it may happen, it may not happen. There is all type of possibility. Degating values varies for each cell type, each depth, each location, each slew, and each load. You can understand the degating values are also dependent upon various factors as cell type, depth, distance, slew, and load. Using standard cell characterization to get the minute or accurate data, LOCV or EOCV requires a lot of library characterization manpower and hardware or software computational resources as compared to each ancestor. It is OCV. Now this is a very much important point because we perform the static timing analysis. We have a very much needed input, the timing.lib, which comes to the standard cell characterization. Now, for this LOCV or EOCV, we require a huge amount of manpower and hardware or software resources. Manpower in the term that more man days rather than more people counts more man days, that is work weeks, are spent here on standard cell characterization. This is one fact about the EOCV in the background, not in the SDA tool, but in the background requirement I, that is timing.lib. Worst case degating is picked up across each load or slew pair combination. So this is the part of the method. We have load slew pair, you know from the timing.lib, right? So there we have the load slew pair and we have a LUT, and from there we pick the data. In case you have not watched the timing.lib episode in the STA series, go ahead. You can find it in the STA playlist, and from there you can watch it. So folks, let's move on to the next slide. Understanding AOCV or AOCV derating table. As I mentioned that the AOCV or LOCV is a path or graph dependent entity. So the derating is not fixed here. It varies. How it varies, that is we are going to determine or see here. Here is a kind of representation of the silicon wafer. It's a hand drawing. So here the oval represents a silicon wafer, and the arrow is a path where we have the logic gates in the path, and the numbers there you can see 0, 1, 2, 3, etc. give the logic gate. And how we have the derating table, this picture will help you to understand. Here goes our derating table. First, we have indexes as depth, that is 0, 1, 2, 3. Then we have indexes as 200, 300. The units can be found at the top of the .lib file. I have mentioned in the timing.lib file. We have already explained what is there in the header section. These basic units can be found in the header section. Next comes the table. So you can see there are 1, 2, 3, 4. 4 columns and 2 rows. These 1, 2, 3, 4. So this goes for the columns and these 2 goes for the rows. Thus we create a hidden table to get the corresponding derating. So thus the derating can vary. This is the AOCV table. I have just give you a kind of snapshot on the actual table. I will show you the actual table later on, just for your understanding, just to create the right impression to your mind. This slide is created. Just take a snapshot in the mind. Yes, in upcoming slides we are going to discuss about the actual table. This is the actual data, but the table consists of much more data, but this is the crux of the table where we have the variation of the derating. We're done with this particular slide. Let's move on. Timing.lib data for AOCV or LOCV. So here we are going to come across the actual table. So first there will be a header section of the table where these things are mentioned. The library, OCV lib, then OCV table template, would be OCV template. This is the name. Then variable 1 is path depth. Variable 2 is path distance. Now you can see that we have named it. This is a table prototype. It is declared in the top section of the .lib. And we have dummy indexes 1 and 2. In actual case, these indexes, values and numbers can vary. On here we close it. So this is a template, that is the prototype of the actual table that we find later on inside each cell of the .lib file. Now what we see in the actual cell, inside is every cell definition. Let's look into that. And here the bigger rectangular box will be displaying that. The first we default OCV derate group, that is advanced OCV. Next we have the cell length. Then we have OCV arc depth 2.0. So this OCV arc depth is the effective logic depth at a cell or a timing arc. We have a value here. OCV derate group OCV 1. Then we have OCV derate, where the things OCV derate factors is OCV template. On RF type, it is rise fall type, and here in this particular cell it is rise and fall. However, the valid inputs can be in the right hand side as comments, right? The valid are rise, fall and rise and fall. So these are the types. Next, the derate type is early. This is the type of the arrival time. So it could be early, it could be late. These two values can come to here. Next, the path type. So here the path type is clock and data, and the valid types are clock, data and clock and data. Now here comes the actual indexes. Next, we have the second index. So here you can see from the prototype, the index number and the values have been changed. Next, we have the values. That is the table, actual 2D table, lookup table. So here the table closes. So already you can now correlate. In the previous slide, we have discussed these two things and this thing. We have visualized in actual the timing lib. This is written in this way. First, this template is defined somewhere up in the .lib, and later for each cell, this section comes for the AOCV, and the relevant strings I have kept here. So this is a short and sweet description of the data that can be found in the timing.lib that has to be characterized by the standard cell characterization scheme, and this particular data requires a lot of effort. There could be various variation even for a single so every possible combination has to be logged there inside the .NET. So I have just given you one snapshot. And if you see right here, the values rise, fall, rise and fall. I am moving my mouse, so log data and clock and data. So all these combinations, multiple combination of these variables can be there. Next, analysis types of AOCV or AOCV. There are two basic types of the AOCV or AOCV. In this slide, we will also see the snippet of the commands that are going to use. So first, we enable the AOCV, we use this particular command in the ST tool, timing AOCV enable analysis in the values true. And this invokes the AOCV engine, read the respective AOCV inputs and process the design accordingly. Now, the first type is graph based. As we mentioned, to initiate this particular method, we use report AOCV in this particular command. The first command already invoked that enables AOCV and the second one invokes the graph based method. The second method is path based method, which is invoked by the report timing and then -EDA mode path. With this here, you can invoke the AOCV method inside the Skew tool. Obviously, there will be a lot of other commands, but these are the key commands that we put there. So folks, in a short and sweet manner, we have covered this particular slide. Let's move on.
Hey guys, welcome to the 22nd episode of Q&A. Viewer Subhash has asked in the episode of SDF file from the static timing analysis series, what is pulse rejection limit and E-limit? Today, we will be focusing on the definition and example of both the pulse rejection limit and E-limit. So sit tight and enjoy the learning experience. In today's episode, we will be covering the below topics: SDF delay, SDF path pulse, the pulse rejection limit, that is also called R-limit, and in the same particular path pulse, we also have the X-limit, or which is also called E-limit. And we will see the various case studies for the above two. So that's the menu for today. So without any further delay, let's begin. SDF path pulse, pulse rejection limit, also called the R-limit. The path pulse entry represents narrow pulse propagation limit associated with a legal path stretched between an input port and an output port of a particular device. These limits determine whether a pulse of certain width can pass through the device and appear at the output. Here is the example. I have shown you this example in the main episode, that is episode 9 in the static timing analysis series. In case you have not seen that particular episode, please go ahead and watch that episode. So here we complete the example, and here is the infographics for the pulse rejection limit. So here in the picture you can see that two limits have been defined. Now here, if we compare this particular picture with the values, the first value 13 is in time units, is the pulse rejection limit, also known as R limit. This limit defines the narrowest pulse that can appear at the output port of the specified path. Any narrower pulse does not appear at the output. So you can understand from the picture and the example that if pulse width is less than 13, then it is rejected. That is, this is the pulse rejection limit, and we can set it in the SDF file. So I think this is a very clear and present fact. We are done with this particular slide. So let's move on. Now let us look into the X limit or E limit using the same particular example. And here goes our infographics. The second value 21 in time units is the X limit, also known as the E limit. This limit defines the minimum pulse width necessary to drive the output of the specified path to a known state. A narrower pulse causes the output to enter into the unknown state or is rejected if smaller than the pulse rejection limit. Note that the X limit, also known as E limit, must be greater than the pulse rejection limit to carry any significance. So here you can see 21 is greater than 13, which is a very much clear and present fact. This kind of numerical difference should be there when these two limits are set. If you specify only one value, both limits are set to that particular value. That means instead of 13 and 21, if we have used only 13, so that particular 13 would be applicable to both the pulse rejection limit as well as the E limit. So that's all the explanation here. Next point, in all cases, value can be either a single number or a triple, but must not be negative. So this word of caution you must remember in your mind. Now we will look into various case studies. We'll use the same example and we will use this particular infographics here. In the first pulse, being shorter than 13, it is rejected. The second pulse, being at least 13 but shorter than 21, appears in the output as X. The third pulse, that being at least 21, is passed to the output. You can see that bullets and the infographics are side by side. So this way, this particular limits, that is pulse rejection limit and the E limit. Also, I have given the other aliases to you. These actually defines the transmission of a pulse from an input port to an output port. So here, we are done with this particular slide. Let's move on.
Hey guys, in today's episode, we are installing one particular free and open source static timing analysis engine. Its name is OpenTimer. You can see in the screen, here is the URL github.com OpenTimer/OpenTimer. So all these links will be provided in the description of this video. And at present, this particular software is available in Linux platform only. So we will install this. I have a Ubuntu system with me and I will install it. So here, before going to give me a short introduction, what is OpenTimer? OpenTimer is a static timing analysis tool and it's an open source tool. So if you are a software developer, you can contribute, or in case you are a VLSI engineer, you can use it after you install in your Linux system. This OpenTimer is a kind of tool which is very much look alike in operation. It's also very much look alike with the industry standard static timing analysis tools. Here the shell looks like this. Once we install, we can see that how this will come up. Here is the system requirements and the build instructions. Dependency is that you must have TCL/SH. Let me install it for you, and without further delay, let's begin. This is the instruction here, how to install it. This is the URL. So this URL, if you go and visit, you will get all these system requirements and how we can install it to our command line interface. So let's start. I am at my home directory. Let me make one directory here. So I am making a hidden directory .OpenTimer so that there is no visibility of this directory to side by side of the visible directories. Okay, so let me change my directory. Now let me execute the first command here. And by the way, I am online now, so it will be done through. So we cannot find GIT. Install GIT. So what happened that the first command we had the command GIT and we cannot find it. So we are installing it first. So let's see.
So it is ongoing. Git is done now. So let me go back to the command. Before going that, let me check which directory we are in. So we are inside this, so we have to move to .OpenTimer. Okay, so we are inside this directory, and now we'll execute the git command. So we want all the files to be cloned in our .OpenTimer directory. So let me start it. It is starting. You can see that this git is cloning the entire directory here. So as you can see here, the thing is moving with a particular speed, and all the files are getting cloned. You're waiting all the files to be cloned, and then we can go to the next steps. Okay, so cloning is done. So all the files have been copied. So let me do a ls command. Okay, so it has created another directory called OpenTimer inside. So let us go inside that directory. So we are now inside the directory, and we can see here a lot of files are there. So let me go back to the instruction set again. So we have went to the OpenTimer, and here we have to execute this mkdir build. So let me write it. Let me mkdir build. Okay, so it's done. Now what is the next? Say then went to cd build. We have inside the build directory. Next is we have to make cmake dot slash cmake. Now again we face that we do not have cmake. So let me bring up the sudo command to install. Okay, and now here we install cmake. So these are real-time problems where you are installing in Ubuntu and you are trying to install something. There might be some dependencies on the go. I may have to install them. So like that, here we are facing that we do not have the cmake, and here we are installing cmake. So again, yes, okay, fine. So guys, don't get disheartened if you don't see a package, because if you are online in Ubuntu, at that time you can use the sudo apt-get install command directly to install that particular package. Okay, and these are real-time challenges. So may occur these problems where once you try to install something. Now let me see which cmake. Yeah, it's there. Now we can use the cmake command. This, okay. So now it has started compiling. So OpenTimer's request TCLSH to build. VLSH. So here we see another dependency is that we do not find TCLSH here. Let me bring up the sudo command. Again, we have to do TCLSH. This is the basic tickle interpreter. So we can see here, it is asking that it will install tickle 8.6, okay? And as we execute sudo apt-get install TCLSH, the repository is there already inside. If it is not there, we have to go to the particular site here as it is mentioned here, and we have to add the repository. So now I said yes, and it is going on. So let's wait. once the TCL/SH start to install. Yeah, it is installing. Okay, now it's done. Let me execute again CMake. So it is done now. It is done now. Let me check if everything is okay in the log. Okay, I think this step has executed. And then we have to use make. Okay, before executing make, let me check whether make is there. Okay, make is installed there. So I'll execute make. So the make is ongoing here right now, as you can see. So make is basically here, it is doing a local process. So online processes are done. Now in local directory, we have created a build directory. Inside that we are executing the make. So it is building that a particular software, okay, the OpenTimer. Okay, so the process completed. So you can see here it has completed 100%. And now let us see what is the next. So I think this we are at the last step. So after successful build, you can find the binaries. Okay, so let me now shorten this terminal. Okay, cleaned it. Which open. So I have made an alias here, OpenTimer as user bin OT shell. So now let me do which OT shell. Okay. So probably here we need to do a restart. Okay. Let me check. So guys, we are back after the reboot and we have entered the directory where we have done the build. So we are doing a ls here. So you can see here, there is a bin directory, binary. If we enter, here we can see, do the ls, we can see all the binaries have been created here. Okay. So here I have set the alias to this. So let me do a ls and then to user local bin. Okay. The directory is there. We will copy all the binaries. We will use sudo as a super user. We will be copying, copy tar all the binaries here into the user local bin directory. And here it is asking sudo password. And in this directory, okay, there are 4 binaries created. So we will do sudo. I have given the sudo password. So it has copied all the binaries. So let me do ls of that directory. Now all these things are there. Okay. Here what I have done, I have set a alias OpenTimer, which I have done alias. Let me clean the screen and do the, okay, so I have set in my CSHRC file that I have aliased this OpenTimer with user local bin OT shell. So let me start the shell. So when I execute, it opens the OpenTimer shell. So guys, we have successfully installed OpenTimer in our laptop or desktop, whatever PC you are having with you, local. And in this example, we have installed it in Ubuntu. For rest of any other distros, you can install as per the build command, whatever I have shown you. But I think this OpenTimer is not available in Windows. Okay. So at present, you have to have a Linux system like Ubuntu or something at your end to install this. So that's all, guys. See you in the next episode. Bye.
Hello and welcome to the 10th episode of Static Timing Analysis. In today's episode, you will be introduced to all OpenTimer commands and report analysis. Already created a video on OpenTimer installation. Link is given in the description. Here is our menu for today. First, we discuss about STA commands and flowchart with example. Second, we talk about STA report structure and analysis. Next, we talk about OpenTimer license. Next, we talk about exhaustive introduction to OpenTimer commands. Next, we talk about OpenTimer example with commands. Then, we talk about OpenTimer STA report analysis for setup violation. Then we talk about OpenTimer STA report analysis for hold violation. If you want to learn STA tool, then this episode is a must for you. We are done with this particular slide, so let's move on. STA tool flow and usage. In this section, you will be introduced to all kinds of input and output files. All the input files are already covered in detail in previous episodes. You will be introduced to various kind of outputs in this episode. STA engine input-output files at a glance. Before going further, let us have a quick glance at all input and output files of STA. So this is our STA engine. First we have our synthesis tech library. Next we have our gate level netlist. Next we have SDF. We have the design constraint integral. And we have our timing library, that is timing.lib. Now, once the STA engine processes all these input files and we hit the report timing command, it generates AT or RAT report and histogram, and we can access the live design data. In case you are not familiar how to get the design data or how the engine at all accesses the design data, I have given a quick episode link in the description that will clear your mind. We are done with this particular slide, so let's move on. STA commands and flow. You have just seen all the input files. Now, all of these files have to be processed in a specific manner. Here is that flowchart. We will proceed in this direction for the progress of the flow. First, we read all the input files. Next, all the constraints are activated. Then, all the inputs are validated. Next, finally, we generate all kinds of report, histogram or design data access. So, this is our short and sweet flow and we are done with this particular slide. So, let's move on.
STA is command line. Now folks, this is a very important slide. For those who are experiencing the STA tool for the first time, I would like to emphasize that STA tool is a command line tool only. STA tool runs on its own shell, and the shell is always a command line. For OpenTimer, the shell looks like this. So let me bring my mouse pointer here. It is the shell started, and it gives a header printout kind of stuff. OpenTimer you can read. You have probably saw this one in the thumbnail, and it prints all the license and all, and then finally it makes the shell ready for you. So this is how we invoke the OpenTimer shell, and finally after printing out, the shell becomes ready here. Not only OpenTimer, all the industry standard STA tool are command line. They have the same look and feel as OpenTimer. So folks, when you are learning the OpenTimer, you are getting ready for the industry standard STA tools, and you are moving one step forward. We are done with this particular slide. Let's move on. STA command example. You have seen the flowchart few slides back. Now let me exemplify the STA commands according to the flowchart. Here goes our example commands. First, include all the libraries, technology and IP model libraries. We start with a set command, set link path, and then star.db. Then we read all the gate level design files. The read verilog command. So then we have a verilog file here, fullchip.b, which is processed by the read verilog command. Next, we read libraries and link the design with the link design command, and then we give the fullchip, the design name. And then we read the SDF file. So with the read SDF file and the respective arguments, we read the SDF file. Next, we do all sort of reporting. Report design, report clock, report annotated delay, report annotated check, check timing, and etc. This example is from industry standard STA tools. That could be any. Common structure is very same. And we are done with this particular slide. So let's move on. OpenTimer command example. Now let me introduce you to the OpenTimer commands as per the STA flowchart. You will find resemblance with the example in previous slide. So here is our placeholder, and we start. Include all libraries including timing model. Read celllib mycelllib.lib and read all the gate level design files. Read verilog mydesign.v. Then read the SPEF. Read SPEF, then mydesign.spef. This particular SPEF file comes after the post layout. That means once the layout is ready. I have made already an episode on SPEF. In case you have seen, it's good. In case you have not seen, go ahead and see that episode. Next, we read the SDC file. Read SDC, then mydesign sdc.sdc. Then do all kind of reporting. First, we do the report timing. Then we do report leakage power. Then we report AT, that is arrival time. Then we do report RAT, that is required arrival time. Then we do report Skew, then report slack, report area, and so on. So all of these commands mentioned here, you have to source them one by one in the OpenTimer shell. And folks, you have a good opportunity to install the OpenTimer and try this. We are done with this particular slide, so let's move on. Why we do report timing? The report timing command is to get the STA report. This is common to all STA tools including OpenTimer. Let me show you the reasons for using the report timing. Default, it returns the worst path for max analysis for each clock, recovery check, clock getting checks. So all sort of these checks. Next, customize with many different switches. Setup versus hold reports. Increase the significant digits. Focus on specific paths. Increase the number of generated reports. Include net fan out. Expand the calculated clock network delay. So you can see you have the basic kind of reports first, then you can do playing around with multiple commands and fetch multiple other data from the shell. Over time and continuous development, more things may get included in report timing command. So always consult the latest STA tool manual. Only a latest manual can give you the right set of commands that are applicable in the STA shell. We are done with this particular slide. So let's move on. report analysis and you. Any guess why I have kept this slide? Let me tell you with a couple of infographics. Suppose there are 170 violations that have been reported after you run the report timing analysis in actual practice. I'm talking about the real-time designs when you do the reporting. And obviously when we are dealing with the OpenTimer test cases, we don't see this amount of huge violations. In real world and real practice, huge violations will come because the design is a multi-million gate structure. Now, when 170 violations are reported, what we see? What we look for, what else is there apart from violation? Is there any other information? This is case by case and you have to be very observative so that you can pick up things from the report. Are all violations real? Now, why I am pointing this particular question? Because when I have discussed the theories, I have mentioned there are many false errors that are flagged by the STA engine. I'll not repeat the names. I have already explained them in the theoretical episodes. And all these false alarms can come inside this violation. So you have to root out all these kind of false alarm from the actual violation. So first you have to segregate the false alarm and keep the actual violations. So that will reduce some amount of number. Can you explain warnings in the log file? When you run the STA engine, there will be certainly some log files generated, or when you are running in the shell, there will be some amount of logging data thrown in the screen. Does it help you at all? In case you are running a shell and there a log file is not generated, you can use a tcl command to open a file and dump whatever coming out in stdin. So that way you can customly create a log file. How to write file, open file, everything I have already discussed in the tcl episodes. What are the action items for resolution? Now, when you have browsed through the 3 above points, what else is there, what all violations are real or not, you have got any errors and warnings in the log file, and then what are the action items for our resolution? Now you have all the data, everything you have analyzed. Now you are thinking what we should do for the resolution. This can be multiple things, whether you have to do some changes in your RTL or you have to do run some what if analysis so that you can check within the shell. We'll come later on this what if then analysis. We have some feature in OpenTimer. I'll come to that. So all this sort of resolution you have to take. Next is the special situation. What are the issues? Now, why I have kept this part or this question is that there will be certainly design specific and some special error or warnings or violations, rather be more specific. On those cases, you have to think deeply and take action. Timing report, that is the report timing command. The purpose of this slide is to make you familiar with the STA timing report. So let's begin. Once we run the report timing command, after the initial few steps that shown in the flowchart, when we hit the report timing command, this kind of report is generated by any STA tool. So this is a common structure, and here you can see there are different sections. Let me one by one tell you the sections. This is a header section. Here is my mouse pointer. You can see the start point is FF1 and the end point is FF2. Path group is clock and path type is max. So I'll come what is this max analysis later on. So this is the header section. Next, we have the data arrival. So this entire section captures the data arrival, and here you can see this is the data arrival time. This is AT. We have discussed so many times AT RAT. Here it is the AT, and here the AT value is there. So all these arrival times are summed up, and here the total AT is calculated. So this is the data required time. Here this sections gives the data required time, that is RAT. So RAT, whenever we sum up all these things and we get the RAT here, this is the RAT value. Finally, we have the difference between the AT RAT, and that is showed as slack. Later, I will show you the slack equations when I give the explicit example. There I will define the slack equation also. The section here, you will get the slack, where you can see that whether it is met or violated. In general, the STA, the report timing, whenever you run, is a short and sweet version, but the report can be long more than that. But generally, there are 4 sections. First is header, then the arrival, then the required, then the slack. So even there could be multiple such paths are reported, and all these reports will be there one by one after another, reported once you hit the report timing. This structure is more or less same in all the STA tool. Here in the last section, you have visualized the AT RAT in real time. We are done with this particular slide, so let's move on. OpenTimer commands. In the upcoming sections, we will go through all the OpenTimer commands. You have to memorize most of them when playing with the STA report and further analysis in the command line. So fasten your seatbelt and start the high-speed journey in this section. OpenTimer license. OpenTimer is a free and open source software. You can freely use it under the MIT license. So enjoy. Commands to read the input files. These are the must-used command except the update timing. You have to use all others every now and then. Let me bring my mouse to describe these. So here first command is read cell leave. Here we can see min max. These are for respective delay calculation, and here we give the cell leave, the timing library name. So this reads the timing library. Example is read cell leave library.lib. Then the read verilog argument is file name and it reads the verilog netlist. Example is read verilog then design.b. Then comes the read SPEF. Argument is only the file name. It reads the R, C and CC information from the SPEF file. So read SPEF, then design.spef is the usage. Read SDC, and here the argument is only the file name. Read design constraint file, and the usage is read SDC then constraints.sdc. And we have some update timing. So suppose we have updated anything like verilog or SPEF in between the timing engine, and then we have to hit the update timing. So it will update the timing according to the updated file. Or we have done some what if then changes, and accordingly we have to update the timing internally. So for that purpose we have to use the update timing. So this is update timing. Usage is just the command you have to type update_timing. That's all. So we are done with this particular slide. So let's move on. Report timing command. This is the most important command in STA. Without this, you cannot do the analysis. Where is my mouse pointer? The command is report timing. Then we have number of paths. We can put an integer how many paths we want the reports. So it means the number of paths to report. Then we have min, the mean path analysis. The max is the max path analysis. Then we have rise and fall, the rising endpoint and the falling endpoint. So these are all arguments and the purposes. Now let me tell you some more facts about this command. If the num paths is unspecified, the OpenTimer report the most critical path. If both min and max unspecified, OpenTimer report the critical paths across both plates. If both rise and fall are unspecified, OpenTimer report the critical paths across both the transitions. That's all folks. We are done and let's move on. More reporting commands. Let me introduce you to some more important reporting commands. So here it is report TNNs. It do not have any arguments. That's why you have not applicable here. Report the total negative slack, and we directly use this command without any argument. Then report WNS is the report post negative slack. We use the command like report_WNS. And then we have the dump graph, then -o, then file name. Dump the timing graph in a DOT format, and it is dump graph. And then dump timer, then file name, and dump the design statistics, and then the timer. So we will later on show the examples, so don't worry. We are done with this particular slide, so let's move on. Some more reporting commands. The list has not exhausted, folks. Here, these are only commands you have to use. To enable CRPR, enables the common path pessimism removal analysis. This triggers path-based timing update and can increase the runtime. After this enable, if we want to disable it, we use the disable CRPR. Disables the common path pessimism removal analysis and adopts only the graph-based analysis. So report TNS, report WNS we have already covered, but somehow I have kept it in this slide. So again I am telling. So report TNS is report total negative slack, and report WNS is report post negative slack in the design. Report FTP reports the total failing endpoints of the design. And finally the report leakage power reports the aggregate cell leakage power in the design. So these are the commands. You can use them as is, and all these are purposes. As you have come across all these reporting command section, now you are realizing what the power the ST tool has. So we are done with this particular slide, so let's move on. Report slew command. As the name suggests, we can do more with this particular command. Let us see how. So here This is my mouse pointer. This is our command and all these are arguments. So pin name gives the name of the pin for which we are doing the query. So these are kind of query command, and min the minimum transition time, max is the max transition time, rise is the transition time at the rising edge, and fall is the transition time at the falling edge. So this way we can use the report slew command to report the slew of a pin, and this is one of the command which accesses the design database. So when all the database separate files are joined and stick together inside the shell, from there you want to pull out some data. This is one of the command which you can use to pull out some data, report slew command of a particular pin. We're done with this particular slide, so let's move on. Report slack command. We can play with the slack with this particular Swiss Army knife. Let me show you how. Here is my mouse pointer. Report slack is the command and all these are arguments. Pin gives the pin name on which we want to do the query. Min is the minimum slack time, max is the maximum slack time, rise is the slack time at the rising edge, and fall is the slack time at the falling edge. So this way we can do the slack query. We can use it to determine slack at various pins. Okay, we're done with this particular slide, so let's move on. Report and dump commands. We will conclude the report and dump commands with this particular slide, and here we go. So here we can see that there is a report area. This is a command and you can use as is. Report area. This reports the aggregate cell areas in the design. Dump timer. The output shows the summary of the design time, number of pins, number of nets, units, and so on. So this gives a summary. Dump task flow. Dumps the present lineage graph of a DOT format, and dump graph dumps the present timing graph into a dot format. These are two particular commands which gives a output in a DOT file format as output. We can visualize the dumped graph using this online tool. This tool can export the graph in picture format with SVG file extension. The link is also provided in the description so that you can access the online graph visualization tool once you dump some graphs from the OpenTimer shell. We are done with this particular slide, so let's move on. Design manipulation commands. Sometimes we have to do some what if then situation analysis which will reduce some actual design manipulation time, and hence the total turnaround time also be very less. Since the whole design is loaded into the shell, you can manipulate the design live inside the shell without going back to the RTL code. Now, let me go through the commands one by one. First, this command is insert gate, and its argument is gate name and cell name. The names of the gate and name for this insertion command. Remove gate name. The name of the gate to remove from the design. Repower gate name then cell name. The names of the gate and the cell for repower operation. Insert net name. Only the one argument. The names of the net to insert into the design. Remove net name. The name of the net to remove from the design. Then connect pin name then net name. The names of the pin and the net to enable this connection. And disconnect pin name. The names of the pin to enable this disconnection. Now folks, you can see all these are kind of what if then situation analysis commands, and if you remember we have talked about the update timing command, so that will be used in conjunction with all of these commands. Once you do these all kind of changes, you have to update the timing inside your shell. So folks, I am done with this particular slide, and let's move on to the next slide. General config commands. We can configure units using these commands. You can see the command is set units. Here is my mouse pointer. Time then unit. We can play with the time unit. Capacitance then unit. Capacitance unit is farad. So here all the default units are mentioned. Then resistance unit, then voltage then unit, current then unit, and power then unit. So we can change the unit if we want to do. Whatever unit we want to represent the outcoming data, we can change the unit as per this. So all we can play along all the units with this particular command. So we are done with this particular slide. So let's move on. Timing config commands. We can configure arrival time and required arrival time with the help of this command. There is my mouse pointer. The two commands are there. Set AT, that is set arrival time, and set RAT is the set required arrival time. both has the same style of the arguments. Both are applicable. Pin name gives the name of the input port pin. Delay, the arrival time value. Mean, the minimum arrival time. Max is the maximum arrival time. Then rise, the arrival time in rising edge. And fall, the arrival time at the falling edge. Either of these two commands can be used with the same arguments. And the meanings are also same. So these two can be used for playing around with the AT-RAT in the circuit. We are done with this particular slide. Let's move on. Slew config command. We can play with the slew using this command. Let me describe how. Here is my mouse pointer. Here the set slew command is there, and you can see all the arguments are in this column and the purpose is in this column. So here pin, then name, the name of the input port pin on which we are setting the slew, then the slew value, the input transition time value, min, the minimum transition time, max, the maximum transition time, rise, the transition time at the rising edge, fall, the transition time at the falling edge. I think these are very straightforward in meaning. So we are done with this particular slide. So let's move on. Load config command. We can play with the load values with this particular command. This is how we do it. Here is my mouse pointer. This is the command set load. This column gives the all arguments. These are the purposes. So pin name, the name of the input pin. Load, it is the load capacitance value, and min is the minimum load capacitance. Max is the maximum load capacitance. Rise is the load capacitance at the rising edge, and fall is the load capacitance at the falling edge. So these are very straightforward in meaning. And one thing, folks, in timing analysis, when we are dealing with load, by load we mean always the capacitance. We do not mean any other thing. So keep this pinned in your mind. We're done with this particular slide. So let's move on. OpenTimer example. In upcoming section, we will explore one OpenTimer example test case. You will know how to run a STA test case inside the OpenTimer shell. You are now familiar with all of the OpenTimer commands. So this will be very easy going for you for this next section. OpenTimer example. This is the circuit diagram of the design under test. This is a very simple design to understand. We will use the OpenTimer shell to load the design in the following way. Let me bring my mouse pointer to explain. Here you source the OpenTimer shell. This is basically the area where you have compiled the OpenTimer. There you can go and open the shell. So this is the OpenTimer shell. This is the area where you have compiled the OpenTimer. There will be a bin directory. Inside there will be OT shell. So you can use in this way, or you can use in the another way that I have described in the installation video. So once you source the OpenTimer shell, you get this kind of header printout, and then the shell is ready. Once the shell is ready and you are inside the directory where the example is there, what you will see? So you will see differently Verilog SDC file. So these three files will be there. So we use the read lib to read the lib, then the Verilog, read Verilog to read the Verilog, and read SDC to read the SDC. And then we will reheat the report timing to generate the report. So this is a simple example. The test case name is also simple. You can get the test cases in the same GitHub link from where you are downloading the OpenTimer. So there, these examples are there. I think when you download the entire thing, the test case also come. Otherwise, you can download from the GitHub. We are done with this particular slide, so let's move on. I mentioned that at some later time point I'll clarify the max and mean analysis. So here you can see the setup violation comes under the max analysis, and this max, why this is max analysis, you will see. In this slide we will explore how to catch the setup violation in OpenTimer STA. This is our design. We are interested in this path for the setup violation. We run the report timing command with the max option, which is used for detecting the setup violation. You can see the report has how to analyze the setup violation and be sure that this is a setup violation. This is a very good question. To do so, we depend on the slack value. For the setup to be proper, that is, there is no violation, the RAT minus AT must be greater than or equal to 0 as shown in the equation I have just displayed. Now, where is the AT, that is arrival time, in the report? When we add all the delay values from clock pin of the flip-flop up to the output pin of U3 from the diagram, we get the total arrival time. You can relate the path in the rightmost column. Let me bring my mouse pointer. So we are talking about this path, clock, then Q, then U2, U3. You can see this is clock, then Q, then U2, U3, U3, U3. Okay, so this is the path through which the data is coming. So these all adds up to this value. This is the data arrival time. You can see here. And here you can see this is the RAT, that is required arrival time. Here it is reported as data required time. So that means required arrival time. This is RAT. You can see the arrival time is greater than the required arrival time. That is AT is greater than RAT. So the slack is violated as per the equation. You can see here, if we go down right, here we can see that here it is negative and here it directly flags that it is violated. So that's why I have kept all these lines in red so that you can distinguish from others, and here you can see it is violated. And here another thing I would like to mention, this max is there, but this bracket I have kept for you to understand. It doesn't go in the actual command. And here you see that start point and the end point, PLK and the out. Here we derive the final conclusion. Max path analysis refers to setup time analysis. The data arrived at in out much later time. The value is given in bracket, that is 10.724 than expected. Hence, the setup time at clock in, that is F1 colon clock to out, is violated. Here the arrival time is much greater than the required arrival time. One more thing to say here, that this path is a range to output kind of path. If you recall, there are 4 types of paths on which we do the static timing analysis. This is one of them, and this is the range to output path. We are done with this particular slide, so let's move on. Hold violations, mean analysis. In this slide, we will explore how to catch hold violation in OpenTimer SDA. This is our design under consideration. We are interested in this particular path for hold violation. We run the report timing command with mean option to trace the hold violation. You can see that the report has come how to analyze the hold violation and be sure that this is a hold violation. To do so, we depend on the slack value. For hold to be proper, there is no violation. AT, that is arrival time, minus RAT, that is required arrival time, must be greater than or equal to 0 as shown in the equation. Now, where is the AT, that is the arrival time inside the report? When we add all the delay values from input port of E1 up to the D pin of the flip-flop in the diagram, we get the total arrival time. You can relate the path in the rightmost column. Let me bring my mouse pointer to show you. Here is input pin, that is here. Then this is E1, we are crossing E1. Then U4 is here. And finally we reach the point, is the pin D here of the flip-flop. So this is the part that the data is traversing and arriving. This is the data arrival time. And this is the data required time. You can see here, I am pointing my mouse. So the slack is violated as per the equation. You can see the hold failing text has come also here. So in OpenTimer, here we can see it is already reporting the hold failing. This hold failing flag is already there. We see the slack is violated. So this slack is calculated as per this flag. Okay, it don't have a fixed meaning, and this particular slack is calculated this particular equation, and that is linked with this mean or max analysis. Okay, here it is violated. Hold violation is just saying right now. How we derive the final conclusion? Mean path analysis refers to hold time analysis. The data transition at F1 colon D was required to happen after time 26.518, whereas its transition occurred way before at time 2.967. Hence, it causes a hold violation. Here, the arrival time is much less than the required arrival time. This path is of type input to reg. As you know, there are 4 types of path on which we do the SDA analysis. One we have seen in the last slide, that is reg to out, and this is input to reg. We are done with this particular slide. Let's move on. Checking summary and units. When you have a design, you want to have the different counts, right? What are the different counts of nets, gates, etc. This command, the report timer command, this is how we get the gate or net count time summary, and as well as the units, whatever we are using the units. While you are reporting the units here. Sometime back we have seen there is a command with which you can change the unit on the go inside the live shell. Then how will determine what is the unit? So this command will print out the unit. As well as here you can see, let me bring my mouse pointer. Here you can see number of pins, gates, nets, cells, all these are reported. So this gives a short report. You may require it, or unit change you obviously require it, or there is a what if then analysis you are doing, again you will need it. So I think we are done with this particular slide. Let's move on.
Hey guys, welcome to the 11th episode of Static Timing Analysis. Today onwards, we will do hands-on static timing analysis using the OpenTimer STA tool. In VLSI, when you learn any software hands-on, you have to stack the corresponding theories in back of your mind. In last 10 episodes, we have covered all the theories and some amount of SEA commands. So now we are ready to play with the STA tool on VLSI test cases. Stay tuned till the end of this episode for hands-on knowledge using OpenTimer STA tool.
Hey guys, welcome back. We are in our computer now and this is the menu for today's episode. First, we will do the cloning of OpenTimer test case into our local directory. Tour of various files inside the test case. OpenTimer alias creation for easy use. Hands-on design loading in OpenTimer. Hands-on report timing command for various of its switches like min, max, rise, fall. Then hands-on example of report FEP, report TNS, report WNS, etc. Then we'll do the hands-on on report slack command for its various switches like min, max, rise, fall, etc. So this is a very consolidated menu for today. So without any further delay, let's begin the hands-on practice using the OpenTimer STA tool. So folks, as we have discussed that we will clone the OpenTimer test cases from its GitHub link local to our directory. So let's first go to the OpenTimer GitHub URL. So I am typing in Google. So OpenTimer STA. Once I click here, I get the first link as the OpenTimer URL. Now this URL I am providing in the description. You also can pick it up from the description. So here, once you open, right, you can see there is a folder called example. This is clickable. So once we click it, we go up to the subdirectory here, you can see. So we need this particular directory to go inside, and we'll start our hands-on practice using the simple test case. And once we click the simple subdirectory, right, we can see we have gone up to this much of depth. So we want to clone this simple test case and all of these files here in the test case into our local directory. So how we do that? So we go to our terminal and I have created a directory here for OpenTimer test case in my hard drive. So there I am using ghclone. So the installation of the ghclone binary is also given in the description, so you can pick it up from there. It's very easy to use. So what we do here, first we type ghclone and then we give the URL. So URL is here, right? Here we can use the Control A to select all and then Control C to copy, and then we here and click our middle mouse button. So this is the command for copying the simple test case from this particular URL locally to our hard drive. So let me hit the enter. So it started cloning the simple test cases and all the files. It's showing it's done. So let me do a ls. So here I can see the folder simple that has been cloned into my local hard drive. Now this cloning term is very much specific to GitHub. It is similar to copy. The copy, the cp command that you use in your Linux system or Unix system. Since you are downloading from the GitHub repository into your local hard disk, we are using the term cloning, and hence the binary is also named as GH clone. One more thing I would like to tell you that I have given all the description and the install instruction of OpenTimer and all the necessary dependencies even for the GH clone, everything in the description, so you can find it out there. So now let me go inside the directory. I hit the tab and I am here. Let me do a ls. Okay, so here I can see there are a lot of files here. This is how the test case has been created by the OpenTimer team. So let me open one by one. So I am using my gvim alias to G, and hence I am using my alias. So you can see which G gives me the gvim. Okay, so I am using gvim here. Just I am opening the Verilog file. So you can see here, first we have the module here, the module name, and then we have a set of inputs and outputs defined for this particular module, and we have all the nets, that is wire connection here, and here we have the instances. Now you are asking from where they are coming. If I go here and we go to OpenTimer, and there if we scroll down right, here you can see this is a simple test case timing report example on a sequential circuit design. The description is this, and the library is OSU free PDK 45 nanometer. If I hover my mouse pointer over it, you can see the link from where this PDK belongs to. It's a 45 nanometer PDK, and you can also go into the URL if you want to explore it. And we are using this simple test case. So now let's come back to here in the gvim. So all these cells are belonging to this 45 nanometer PDK. So from there we have got all these cells. Now let me close this particular file. Now let me open the next one, that is the SDC file. So here you can see the SDC file have been opened, and you can see that I have already in the SDC file episode, I have described what are the contents inside the SDC file and how these design constraints are written and what they mean. In case you have not watched the episode, please go ahead and see that episode. Here you can see that there is a create clock. Clock is created. Then we have specified the input delay. We have used max and mean branches and rise and fall splits, and we have for ports, so we have used, and we have also used the clock. So we have used the delay and the time unit. We have time unit can be seen when we report all these units inside the OpenTimer shell. You can get the timing units there. And here also, now this is the delay. Now we have set all the transitions here. You can see all the transitions here has been set for the min max and as well as their rise and fall splits. So here are the ports and here are the clocks. Okay. So we have also put the load here, and output delay we also specified. So all these design constraints have been specified in the SDC file. So you can learn more about in the episode where I have discussed about the SDC file. So we are done with this particular file. So let's close it. So next file is the lib file. So this is the timing lib file. Let me turn off the highlight. Here I have closed the highlighting. Otherwise it is very tough to see. And you can see, for going ahead or telling anything, I have also created episode on how to read and how to interpret the timing library for STF and what all the things you get there and what are their meanings. Please watch that episode in case you have not watched. So here is the timing library for that particular PDK. And if we see, here is a particular header section where all these threshold, PCT rise, PCT fall, etc., and norm process, norm voltage, norm temperature, and operating condition, that is PVT, is also defined here. PVT is defined. So you can see here all the LU table template are here. And then once we cross this section, then we have cell. And here if I just go, this is a cell length. Again, in GVim I have is keep 10% for the matching curly braces. So again, here there is another cell, and if I go down, here we can see different pins are there and all the LUTs are there. So you can interpret this particular timing library. Now all these files will be going inside the OpenTimer shell once we invoke it and once we source it. Rest of the files are a couple of configuration files are there, that is internal and maybe specific to the OpenTimer. You can explore them by yourself. In case you have a question, you can put it down. Just one thing I would like to show you here. Here it's the timing file. Here there are some internal formats of OpenTimer by which the AT, RAT, Skew, etc. and the clock is defined. All these things have been defined for this particular test case. And I think CPP file we will not talk about right now because the CPP is for the API sections, and we are doing here very much simple analysis using the shell. At some later point we may look into the CPP and explore that particular side. Right now we will be focusing on the basic example. Now here is the simple.conf. Conf is nothing but it gives a shortcut of all the commands that we use. Generally here you can see all the commands sequentially they have mentioned in the conf file. So basically we can do it by hand once we turn on the shell. So now at this point, two things we are done. First, we have done the cloning of the test case. Second thing, we have made ourselves familiar with all of the files inside the test case, and also we know from which PDK all these cells have come. So here I would like to turn on the OpenTimer shell. Now there is a good point that OpenTimer I have created the alias. So let me invoke the alias. So when I do the which OpenTimer in my shell, I can see that the OpenTimer command is alias to this. So when I grab the CSHRC file and the text I am grabbing is OpenTimer, what I get? The alias. So alias OpenTimer, and this is the thing. Here the path of this. And how you set the path, all these things I have given in the description. So please check it out. This has also been told in the installation of OpenTimer. There also I have mentioned. This is for the CSH cell or TCSH cell. In case you are using the bash, this alias command will be changed, and I think you can find it once you Google it, how to do the alias in the bash. We are done up to this point. Now let me clear the screen. We are now cleaned. Now, so here we are now. Let me hit the OpenTimer. So here I have typed the OpenTimer. Let me do the ls. ls gives all the files here. So one good thing of this shell is that if you type right and if you hit tab, the command get completed. Let me show you how. So once I type read and then I hit the underscore, what I get, that all the commands I am getting. Okay. First, I'll read the lib file. Read cell lib, and then I give the cell lib name here. Okay. And the first thing is done. The next thing is that what we do is we read Verilog file. Read Verilog, and then we have the Verilog simple.b. We read the Verilog. Then we are using the read SDC. So I'm copying the commands from here and copying the file from here. Read timing. Okay. So read timing and then simple.timing. So I think all these files are done. Reading and internal loading of the files is done. Now let me do the report timing. Here once I doing the report timing, right, I am not giving any of the arguments at the beginning, and let me see what happens. So what you can see, that it has read the Verilog, then it has read the timing, and all this timing I have shown this file also, some few simple settings for this tool, and then loaded the SDC and then the lib, all these things, and you can see the units are here, and finally here it is giving this particular output. Now we are getting only one output. If we want to get all the outputs, so here let me bring up the report command. First let me clear the screen and we go back to the beginning, and here let me invoke the report timing command, and here this is num underscore path, and I hit 10. So here we can see a huge number of violations are coming. You know right that the max is for the setup violation and mean for the hold violation. If you can see here, it is mean violation and here is hold failing. I have already explained in the last episode, and here you can see again this is mean and it is hold failing. Now if I scroll down, right, also there are more mean violation means hold violation are there. There is also max, that is setup violation. So you can see here. Now if I want to just segregate the hold violations, let me clear the screen here, and here my screen is clear again. Let me push the up arrow of my keyboard, and here the report timing commands come, and what I have to do, I have to do the max analysis for the hold violations only. So this will provide only the hold violations. So once I type in, right, you can see the hold violations, that is the max violations are reported. So here, how to analyze this particular report, I have already explained in last episode. So please watch that episode to interpret this one. And you can see here, it is also the max is coming. So here you can see there are the start point is F1 colon CLK and the final is out. So this is clock to out this path. So that is a basically range to output path. So here you can see the difference lying in this particular column. So direction, that is fall, rise. Okay. So here this is the direction based on which the difference in the slack is coming. Okay. The slack is here minus 10.724 and here is 10.042. So the difference is in this particular column. Because of the path is same, F1 colon CLK2 out, and here is also the same path is there. Variation of the rise and fall transition. Say if we are considering this fall, then rise, and then finally we are having considering fall. So here you can see that combination is different, and because of this we are getting the particular difference in the slack. Now my question is, we have this, and then what if I want to segregate one level down? What I have to do? So let me clear the screen. We are again at the top, and here max, and then if I give the rise, okay, and I hit enter, so the rise split is displayed, and if I give the fall, the fall split is defined. You can see that here the two slacks are different for the rise and fall split. So this way we can further narrow down or do the filtering of hold violation or setup violation. In this case we are doing the max, that is setup violation. And now let me go for the hold violation. Okay, so let me clear the screen. I hit clear. The screen is cleared. Now let me erase these things and give min. So here once I hit the min, what I see that there are a lot of 1, 2, 3, 4 hold violations are there. The 4 hold violations are there here, and obviously these are the worst cases of violations. When we talk about, these are the pessimistic cases on which we are getting the violation. Now if I want to split the rise and fall category, right, what I do, let me clear. I have done the clear of this particular screen, and let me bring up that particular. Okay, now here we add rise. So here once we do the rise, right, we can see that two categories of rise split here. For the hold violation, in the rise split we have 2 violations here, and if we give, let me clear the screen again, and let me bring it, and in case of fall, we are getting how much? So again 2 are there. Okay, so for the fall split also we have 2 violations. So you can compare these columns for one particular category, right, for the fall or rise split. Okay, fall, rise, fall, rise, fall. Okay, and finally the fall. But in case both are similar, the directions are similar, right? And in case we had the rise, what we see here, if we see rise, fall, rise, and rise, fall, rise. So their transition directions also same. So these 2 are coming in the rise split, and these 2 are coming in the fall split. So this way you can also see that different branching outs of the violations in cases when there is a rise transition, when there is a fall transition, right? During the entire series, during the theoretical explanation, during the timing lib chapter or episode, I have mentioned that there are various rise and fall conditions. So the rise and fall delay and slew, etc. may not be same, may be same. So there could be different cases, and here you can actually see where these particular things get impacted. So this is kind of a hands-on experience on using the OpenTimer. So we are done for the report timing command for now, and for this test case, let's move on to the next examples. I'm clearing the screen here, and let me do the report I hit report and I hit tab. Okay. So here so many report commands are there. Let me see what we are getting here. First, I am interested how much area will this design will cost. So I am saying we can get the units, area units, get it from the dumping the units. I have already shown that in last episode. I think in the last slide I have shown how to dump the units. And here the report area is 176. Now I think the dump command is dump timer. Yes, the dump timer gives is the units. So here you can see all these units. Okay, whatever is there. So now let me clear the screen and I am hitting the report again. So there are so many report commands available here. What you can do, we can print different report commands here. Report area. So where is report TNS? We are reporting the TNS here. And if I hit the report WNS, it gives the WNS. Report FEP. So I have already given the description all these commands. I am not elaborating them. Otherwise this will become much more lengthy. Want to make it very crisp. That's why I am doing short and sweet things. So the report RAT. Okay. So you have to give the pin name. Not now. We will do it later. So these things, and now let me do the report slack. Report slack. Also we have to give the pin name. So let me do the report timing first to get the pins. So here simply we are getting one here. Let me put the report slack here and then dash pin. Here let me give about this pin. Okay, this particular pin I am picking up and giving it. So here the slack is -22.2. So even now if we want to go further down in the max, mean or rise fall, okay, we can go further. So if I give the max, so it will give the max. You can see the max here, and if we give the mean, we can get the mean slack. Okay, so whatever we are getting the here, it's the mean slack. So mean slack means because we are having the analysis type mean and we are getting the slack. So once I reported first, right, it gave the mean one. But in case you want to see the max, you can see that. Now let me add more switches. So for mean, if I want to give rise, for fall we have a different. So for rise one thing we have, for fall we one thing have. So this way we can go every pin by pin and get their slack. So this way we can do the analysis. Now let me give some more example using this report slack command, and here so pin, let me what is coming in the output. So here although we are seeing the path from input to F1:D, but if I give report slack, it's not dependent upon this report, but that's why I became curious and I wanted to see what is coming in the output pin, out pin. So here we can see this. Now if I want to vary it, max is coming as 10, Min is coming as 20, and then we can go for rise 20, fall 20.7. So here we want to report the slack in each and every branches. So min max analysis and then rise fall split. So we can do any type of combination and find out the slack of that particular pin. I think we are done with today's example, and in next we'll do some more experiments. We'll explore some more commands. So we are done for today.
Hey guys, welcome to the 12th episode of Static Timing Analysis. We are continuing hands-on practical using the OpenTimer STA. Today, we will dive into the design data analysis to OpenTimer STA, where we will focus on two different modes of analysis. First one is based on the single pin instance data, and the second one is consolidated design data for the entire design. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis.
Hey guys, welcome back. In today's episode, we are going to discuss these points: reporting overall failing endpoints, reporting overall leakage power, pin-wise reporting of slew, slack, AT, RAT, consolidated reporting of slew, slack, AT and RAT, consolidated reporting of pin capacitance, consolidated reporting of net load, consolidated reporting versus pin-wise reporting, side-by-side comparison. That's the menu for today. So without any further delay, let's begin. Hey folks, we are back in our terminal, and here we are doing the experiments for today. So let's begin. So these are the files. I am using the same test case as the last hands-on session. I am invoking the OpenTimer. The OpenTimer shell has opened. Now let me clear the screen. Let me do a fresh ls. So these are the file. Now I will load the file. First I load the library file .lib. Then I load the Verilog file. Then I load the SDC file, and then I load the timing file. I have loaded all the files. Now let me do the report timing. Now you can see that once I hit the report timing, all the things get processed one after another. So even if I load the files and don't do the report timing, the internal timing analysis process will not happen. That process has happened. So when it is happened, first time you can see there is a log created, as you can see in this section, right? And then you can see that there is a section here that is reported one particular path for the timing violation. So let me clear. And now I will begin the experiment about accessing the design data. Now there are two sides of the design data. First thing is that you have the design component, the pins, the cells, and the cells will have slew, load, etc. So this is one kind of design data. This comes as the input design data or the structural design data. Now there is another set of kind of design data, which is the output. That is when you are simulating the circuit will give some output. Those kind of data is like the timing. Already we have done the report timing and many other reporting. So one of the reporting is failing endpoint. So you can see the which endpoints are failing for the timing, and you can report the leakage power. So first let me try out the failing point. How many nodes are failing? Then let me hit the report and then hit tab here. So you can see here is the report failing endpoint. So this is very straight and simple. So when I hit, it gives the 4. The next one, the design data, that is the post simulation data, and the post one is the report leakage power. So if you can see, the leakage power has been reported here. There is another type of reporting that is much more structural. Now we will enter into that domain. First we'll do the pin by pin reporting and then we'll go overall entire design wise dumping. So first we'll start the pin by pin reporting. I'll pick one particular pin and on that pin I will iterate, because when we are in the static timing analysis, we come across the theories about the static timing analysis, and here in the shell when we are doing the analysis. The analysis will be done by you and you have to do the debug of the issues, and for that particular purpose you have to know how you can proceed node by node and pin by pin. So theoretically, what I mean that node by node, you have to go forward or backward in a particular timing path, and then you have to analyze where the subject to change can happen. How we are changing, I am not discussing in this episode. But you must know how to proceed and traverse inside a timing path so that you can pick up the points where you can make the changes to wave off the violations. Now here, when we are having this path here, the path, you can see the path starts from input 1 and the path goes up to F1:D. So this is the input port and it is the data pin of the flip-flop. So let me pick this data pin of the flip-flop for our analysis. You can pick up any point. Here you can see the rightmost column here. I'm hovering my mouse pointer. So here you can see at the rightmost column, all the pins are there. Corresponding cells are also there. You can pick any one of them when you are practicing. First, let me print out the slew. So I give the command report slew and then pin. Now it has given one value, but generally when we are getting, we will have 4 combinations. Okay, let me demonstrate you. Main. Here, now if I process further, you can see this is the mean plus rise combination. If I change it to fall, we can see the value changes. Now let me change min to max. So here I'm giving the rise, you can see here, and then I'm giving fall. So you can see there are 4 branches. These 4 branches have different branches, I mean to say the branches of this particular command, not your timing path branches. So here you can see the first value, the second value, the third value and the fourth value. So there are 4 set of values. And in last episode, I have shown you that based on this particular column, you may get a difference in the reporting values or the different slacks. Because based on which particular transition you are picking, the rise transition or the fall transition, and the type of analysis, whether you are doing a mean analysis or the max analysis, that actually invokes different values, because they are physically different values from the particular gate or their pins or their rise and slew condition, which actually are picked up from the .lib file. Mean is our hold violation and the max is the setup violation. At command line, we are using mean and max, so we are not every time saying hold or setup, but rather than min max, because we are traversing using the switches. So here we are done with particular the slew experiment here. Let me clear the screen. I keep the pin fixed and I vary the commands. Report slack. Then I give the pin and then I am writing F1:D. So here I just initiated another set of command how to report the slack of the pin. Now when I am experimenting and exemplifying this to you for one particular pin, it doesn't mean that you will stick to one particular pin. You can move to and fro inside a timing path from start to big end. So there you can analyze by your own. So here I give the main with rise. So you can see that this value was already printed. Now changes to fall. The value changed. Now I change max and then rise. Again you can see the value has changed. And here max with fall. So you can see if I am querying the slack of that particular pin, which is the data pin of the flip-flop, I can see that different slacks are reported based on the type of analysis, that is min or max we are choosing, and the corresponding transition rise or fall we are choosing. So accordingly all these values will be printed out. And in case you have no idea that how this value is coming, I have created one Tickle episode, the first episode of Tickle, how Tickle APIs work. There I have explained with infographics so that you can understand. So do watch that episode. I am providing the link in the description. Now we are done with the report slack command. Now for the same pin, what we will do, we will report 80, that is arrival time for pin F1 colon D. Here we just print it. Now we will proceed further again for the min and rise. You can see that this particular value was only reported when we have given no further switches. So now again we change the rise to fall. The value changed, the 80 changed. Here again when I changed, it's different from the previous two values. Here I am giving the fall, so you can see. Now let me bring my mouse here. So first value, second value, third value and the fourth value, each are different from one another. They may be close, I'm not talking about that, but the numerical value, they are distinctively different from each other. So this way you can pick a particular pin. Now I am making the pin constant here and I am varying the analysis type, that is report slack, report 80. When you are analyzing a timing path, your analysis type will remain fixed and you will traverse along the path, thus changing the pins. So this is the only difference. The next is report RAT in F1 column D. This is the RAT that is by default coming. Let me add the switches now. So this is the min plus rise combination. The min plus fall. So when I am bringing back the commands, I am using my up arrow in my keyboard to bring the command back. Here it is the max plus rise combination, and now I see the max plus fall condition. Here you can see. So you can see that here first, second, third and fourth. These two values are close enough. These two values are close enough. But since the mean and max are the two different analysis types, so these two are far apart. So the values of mean, they can be very near to each other, and the max, they can be near to each other. But the max is very far from the mean analysis type. And numerically each value is different here, whichever reported here. So I'll go for reporting the skew. And I am just clicking the values and pasting it here. So skews also can be picked up like this. And I'm adding mean rise, mean fall, max rise, max fall. So you can see that I have also analyzed the skew for this particular pin, and these values are different from each other. For the max analysis, these values are very close in the sense of they are in proximity of each other numerically, and these two are also numerically in the proximity of each other. However, the max analysis data and the mean analysis data are far apart. This is the way that you can analyze a pin by pin data of a design. Now again emphasizing, I have kept the pin constant because I am varying the commands here. You cannot vary everything at the same time. You have to keep one thing fixed and vary another thing for your analysis. This is for demonstration. I have kept the pin fixed and I have varied the analysis type. So report slacks, report AT, report RAT, report slew. Case of actual design traversing, you will just keep the analysis fixed. That means whether you are analyzing the slew, you will keep the slew and vary the pin. That is how you traverse in the timing path. You get the pins I have already shown in the report timing command. So once you do the report timing, you get all the pins in a timing path. So timing path starts here. Here is the start point and here is the end point. So if you want to traverse from this to this, you get the first input, first pin here. The next corresponding pin is here. The next corresponding pin is here. Then you go downwards and this is the final pin. So if you want to analyze this pin wise, this path, you can use the same analysis. Say you are reporting slew, so you keep the reporting slew and whatever particular branch you are analyzing. So if you are using a max analysis, then you do the max, keep it constant and vary the pin and note down the data. This way you can traverse along a path, timing path, and get all the data, and then you can think upon the data where you have to modify to root out the violation. So this was the analysis part of the static timing analysis. That is how you analyze. And now let me clear the screen. Now I will show you some commands which will dump different analysis data as a whole. You will see how this works. These are dump commands. Dump underscore and then hit tab, so all these options come. Another thing, if you want to just have a kind of command line manual, you can type help. So this will invoke the help. So you can see here all our dump commands are here, and they have a single switch only, except this particular one. They have a single switch, and all the dump commands gives output as a file. So you can see -o file. Whereas when we use this particular commands, report slew, AT, slack, they have a pin and then they have a division like mean or max and subdivision like rise and fall. So this is the difference between the overall dumping and the pin wise dumping. We vanish this particular So I am typing dump net load, then dash o net load dot. You can give any extension. I am giving report extension. So the data, whatever with us in the live shell, that data has been dumped into this particular file. We'll see how we can read them. For that, I have to open a terminal. I am clicking here another terminal. So here, so let me see. How many report file have been created. So netload.rpt I can see. Let me invoke that with begin. So you can see here the file is created. So these are the branches. So this is the min plus rise, min plus fall, max plus rise and max plus fall. And here you can see the net name. So here it is, this file you can get with a dump. So you can see all the nets are dumped and the corresponding loads have been dumped here. I'm closing the file right now and I'm going back to the OpenTimer shell. So this was our normal Unix shell where we are operating, and here OpenTimer shell is still alive. In the same way, we will dump slack we have dumped all slacks in the slack.report file. So dump 80, we have dumped the 80.report file. So we have dumped the RAT. Another important dump command is dump in cap. I have used the dump command to dump all kind of the RPT files. So here, let me go back to the Unix terminal and do the ls report. Now you can see that we are in the same folder. 5 report files are there, which we have created using these 5 dump commands. Okay, these 5 dump commands, we have dumped 5 report file and they are created in the hard disk, the working area. So the first one which we dumped is a net load. So net load I have already shown you. The second one is the slack.rpt. Opening the slack.report file, min plus rise, this is min plus fall, this is max plus rise, and this is max plus fall. And here you get the pins. So this column is based on the what you are reporting, this column. So you have seen this particular file, so we'll do some comparison later on this session. So this is for 80, that is arrival time. We have min plus rise, min plus fall, max plus rise and max plus fall. And here you can see all the pins. So when you keep one particular analysis constant and you traverse along the pins, right? So you can also get the data from here, overall reporting. It's up to you how you proceed. How you like to traverse, you can dump the report and then by hands-on calculation, you can traverse inside the timing path. The way is open to you. You can pick any method. So I am opening the RAT. You can see the RAT file has opened, rat.report, 1, 2, 3, 4 columns. Again, these are same columns already I have mentioned. And here the list of pins. We are, I think, major done. Did we missed anything? Net load already in the shown in the, okay, pin cap. Okay, let me on the pin cap. Pin cap dot report. Again, here pins are there and their capacitance values are there. You can see here the pin capacitance have been dumped. Close it. We're still done with the part where we have dumped the data in two fashion. First fashion is that we are dumping the data pin wise when we are traversing pin by pin, and also we have reported the things as a overall to the entire design. So two ways you have already seen that how you can dump these things and play with these things. One option is going pin wise, another one is entire design wise. So both option has been shown to you. And the next part, we compare these pin wise versus the table. This is called a sanctity check. So this is, as a VLSI engineer, your duty is to check the sanctity of any report. So guys, let us proceed towards the side-by-side comparison. Here all the report files. Let me pick one file, and for that file I'll pick one particular pin. Okay, so let me grab the F1:D pin on which we are operating. So which one to pick? Okay, let's pick the RAT. It has gripped the F1:D pin and the 4 column values, first, second, third, fourth, we have got from the output report file. So let us go back to the OpenTimer shell and let us do the one by one, that is pin by pin reporting for the F1:D pin. So let me do the access the data pin by pin data first, the 4 values, and then I'll compare with the table values. So we are ready with the 4 values that we have traversed pin wise. Here we keep the pin F1:D fixed, and we have done the mean plus rise and mean plus fall and max plus rise and max plus fall analysis of required arrival time, RAT. So 4 values are here. You can see, let me now compare the values. So here you can see the first value is 21.833. So you can see this value is the first one. Now 26.5. Here it is 26.5. The decimal places is varying as per the printing inside the file or printing inside the shell. Next is 71.8. So this is approximately 71.8 if we round off these two. Okay. And this is 76.3. So this is also, if we round off the decimal places, this is coming as 76.3. So this way we get the 4 values of mean plus rise, mean plus fall, max plus rise and max plus fall in the table. So here I have grabbed one row from the table for the F1:D. So let me do it for another particular file now. Okay, so here I don't see the Skew file. Let me dump Skew. So the skew.rpt is generated. Now let me grep from the skew report file. So we have these 4 values for f1:d. So here report view so let me first get the values one by one. So here we have reported the skew for f1:d. Now let us compare with the 4 column values that we have in the skew report file. The first one is 0.0987. So you can see if we round off, these values come. 0.0365. Here is the value rounded off. I think the next decimal points are rounded off. This is 0.428. So this is 0.428. This is exact match. And this is 0.426. This is 0.426. So we have verified and checked the sanctity for 2 different type of reporting. That is, one is report RAT, that is required arrival time, and the skew for one particular pin. So this way we do the side-by-side comparison. I think rest of the files you can try at your end and verify these things. We'll close today here. We're done with this side-by-side comparison.
Hey guys, welcome to the 13th episode of Static Timing Analysis. We are continuing hands-on practical using OpenTimer SDF. Today, we will dive into the timing path tracing through OpenTimer SDF, where we will focus on node-by-node comparison between arrival time versus required arrival time for both the setup and hold violation scenarios. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis.
Hey guys, welcome back. We are in our computer screen and we will start our exercise now. Let me launch OpenTimer. So OpenTimer shell has opened and we are in the directory where the OpenTimer test case is already there. So let me do the ls. So it's simple. The test case name. We are entering into the directory. And here all the files are there. So let me load the files. So one by one I am loading the files here right now. So loading of the files are done right now. What we'll do right now is we'll do the report timing command first, just to do the internal timing analysis. So report time has run. So the internal timing engine has read all the files and it's now ready to accept our commands. So first what I'll do in today's exercise, we will traverse the path for one type of analysis, either hold or setup, any one of them. Then we'll do the same thing with the another one. So let's begin. So this is the report timing and I am giving mean. The mean is for the hold analysis. I am path tracing here. We are doing for the path which starts at input 1 and it ends at f1:d. And the analysis type is mean, which is actually the hold violation. And first we will do AT and RAT using the specific commands, and then at the final we will compare with the value of the slack this is coming. So that real-time work, you can actually follow this method to find out where issue getting injected. So let's start. And before beginning, I'd like to remind you one thing, that in the timing report analysis episode, I have explained the slack equations, and for hold analysis and the setup analysis, the equation is a bit different. In case you have not seen, please see that episode to understand the slack equation. That will help you to understand today's episode. Without any further delay, let's begin. Report 80, then I give the pin name. Here input 1, and then I give, we are doing the mean analysis, so mean should be there, and if you look here, this is fall, so this has to be the fall branch. So when I give, it gives 0, so it is 0, you can see here, and we will proceed here. We will compare the result at the last. As soon as we proceed node by node, so this is a node and the next one is a node, the next one is a node, the values get accumulated. That means values are added with each other. We do not have absolute value, it's a kind of values are getting added once we progress to the path and node by node. When I am giving this, what I am doing here, next after pin, what we have, P1 colon A. So this is I am giving here, and this is 0, and let me proceed. So here it is rise. The next one again is, we are proceeding rise, and then this has changed to fall. If you follow this table, this has changed to fall, so I am changing it to fall. We have reached to the end node, and this is also false. So that's okay. You can see that 0, 0, 2.79, 2.79, and it gets accumulated. So whatever the values are here, it goes and it added. We can see here this arrival time. 80 is the arrival time, R80 is the required arrival time. So I'm looking at here the accumulated arrival time, or that is the total arrival time is here. We have traversed the path. Now let me traverse the path for the R80. I begin with the same again, here input 1, and I am just popping from here. So it gives this value. Let me proceed one by one. Now this was rise, so change this to rise, because here when I am picking, I should be picking in the corresponding branch. This is rise, the rise transition. So we are proceeding, and you can see that value is getting increased one by one. And let me go for the next node. Here this is final node we have reached. So here this is the 26.5 is the accumulated or the total required arrival time. Okay, this one. So you can see this is same as this. We already, when we reach the same node here, you can see that this was the arrival time. You can use the slack equation to calculate this slack. So this is how the engine actually internally traverses, and you can manually do that this single commands, or in case actual timing engine, you can write it this in a pickle script and you can source it and then compare. So that will be a very handy thing. That is the very beauty of pickle in these EDA tools, where you automate all the manual steps. For this, now you can see that whatever slack we are getting, whatever the total accumulated arrival time and the total accumulated required arrival time, we have already by individual command, and we are traversing by the node, we have already rechecked the sanctity of this particular timing report. Thus we are done. So this hold analysis, the mean analysis is a hold analysis, and we are done whatever our exercise. Now I'll clear the screen. So we are taking the max analysis, and this is for the setup violation. And here let me go one by one. Here in this path, this starts from F1:CLK and it finishes at the out, and this is max type analysis, that is setup violation we are checking. And here we start with this particular pin from the flip-flop, and we proceed further. So this way I'll continue further down. So we have come to the accumulated arrival time. You can see here the accumulated arrival time is same. So here it is rounded off, that's all, nothing else. So we have traversed the path, traced the path from start point to end point using the commands individually. We have done for the 80, that is arrival time. Now we will do it for the required arrival time. Start with the first pin. So folks, you can see that we have done the 80 and RAT. So the accumulated 80, that is this one, we can see that here is the value, this arrival time. And once we trace the path from beginning to end, we also get the RAT, that is required arrival time. You can see here it is. And according to the slack equations, the slack is calculated and this has been violated. So this was a path tracing for setup violation, and earlier we have done this for a hold violation. We are done for today, and I'll clear the screen. Bye for today.
Hey guys, welcome to the 14th episode of Static Timing Analysis. We are continuing hands-on practical using the OpenTimer STA. Today, we will dive into the gate sizing to OpenTimer STA, where we will cover the fundamentals behind the gate sizing to cure the STA violation. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis.
Hey guys, welcome back. Today we are talking about gate sizing. So first we'll discuss what is gate sizing and why. It's all about fixing the STA violations, specifically tuning the delay. So just to fix the timing violation, one important factor is the gate delay. And this gate sizing is all about tuning the gate delay to the right amount. We know that CMOS equal to PMOS plus NMOS. Why I'm saying this right now? Because the transistor delay is simply the multiplied product of R and C. R is inversely proportional to the width of the transistor. C is proportional to the size of the transistor. To reduce delay, we can decrease R, that is, increase the transistor width. In general practice, transistor length is kept fixed while the width is varied. Sizing an CMOS inverter by a factor 2 means that you make both the NMOS and the PMOS in the inverter twice as wide. This will behave in the same way that two standard inverters are in parallel. A 2x inverter will have a 2x stronger output. This means it can charge or discharge the load at its output 2x faster. So this way, we use the gate sizing method to tackle the gate delays at various points in a timing path. So we are done with the theoretical explanation here, and let's move on to the next section. Hey guys, welcome back. Let us go to the OpenTimer website. So here we go. And why I'm coming here, in today's episode, we will take another test case which is different from all the previous episodes. So, in today's episode, we will use this particular example. The test case name is Sizer and it's a NAND gate 45 nanometer open cell library test case. You already know that today's episode is based on the gate sizing. So we are picking up this particular test case and I am right clicking here and opening it in a new tab. So from here, I am copying the path. So here I am in the terminal and I am using gh-clone to copy the test case from the GitHub URL to locally to my PC desktop. So I am pasting the copied URL and I am hitting enter. So it started copying the test case to my local desktop PC and it's done. So you can see the entire test case has been copied from GitHub to my local disk. I'll come back here. Before that, let me go back to the OpenTimer website again. So here, let me open the OpenTimer wiki and there we have the command manual. Okay, and if we go to the command manual, we are looking for particular command. Yes, here it is, repower gate. So in today's episode, this command will be used and let me tell you why. First, let me describe this particular command. The repower gate command repowers a gate with another cell. The new cell must have the same topology with the old cell. So basically, this means that I am sizing the gate here and definitely with different dimensions, and obviously I'm not replacing a NAND gate with an OR gate. This is you I think understand very well. Then the functionality would change. We are not changing the functionality here. That is not the scope. What is our scope is that we will vary the gate size and from that we will fine tune the delay. This is our purpose. So for that we will be using this particular command. It has two arguments. First, gate name, which is actually the instance name, and cell name. This is a cell name from the .lib library, that is timing library. This is very plain and simple. So I think we are done here, and let me go to the terminal. We are here in the terminal. Let me open another parallel terminal which I will use for browsing the files, and this original terminal I will be using for the OpenTimer shell. Let me go to the inside the directory. Okay, and here I do the same. Now here you can see that several files are there. Timing library episode I have mentioned there. These libraries are characterized for various corners. So you can see this is from the fast corner, this is from slow corner, this is worst low corner, this is low temperature corner, and this is typical. For today's analysis, we'll pick this particular typical library. Let's take the tour of the test case. First start with the Verilog file. Here is the Verilog file, and I have opened it through the GVim. You can see here the module description is here, and all these ports are classified here as an input and output. You can see here, and next you have all the interconnecting wires, and at the final section we have the instances. So here you can see we are dealing with the NAND 2 X2 cell, and there are 16 instances starting from 0 to 5. So all these are interwired by all these nets. Now let me show you this particular cell and the two other size of the same cell in the .lib, that is timing library, which I'll be using in today's exercise. Let me open the typical .lib. I'm using GVim, and let me make it zoom. Okay, here it is the red. We have to turn off this highlighting. This is very annoying to the eye. We have turned off the syntax highlighting here. Now I will search for the particular gate name here. Let me copy it from here, and I'll go back in the timing library and search it. Here the search result, you can see that this cell NAND 2x2 has area 1.33. Remember it. Now let me go for x1. Here you can see the area is 0.79. Okay. Now let me go further for the x4. You can see here it is 2.39. So you can understand that we will be doing the resizing of the gates, and this timing library already has the record which gate has how much area, and it is now clear to your mind. That is, if we sort from low to high, the first comes x1, then x2, and then x4. We are starting with x2, we will move to x1, and then we will move to x4. Let me close it. The purpose is done here of this file, and the Verilog is also we are done. So in the repower gate we will be using this instance name and this particular cell name. Let me close it. Now there are some other files. SPEF file, yeah, this is new in this particular test case, which was not there in the previous test case which we have so far used. For the entire syntax description and details of this SPEF file I have already discussed in the SPEF file episode, that is PX episode. You can watch that episode already in the playlist, and also I'll provide the same thing in the description. So here you can see here the header section, then we have the DNet sections, and inside the DNet sections we have cap, race, all everything. So all the parasitics are with us in this particular test case. So let me close it. Another important factor is the design constant file. I'm opening it. I'll not go in detail because I have already created an episode on design constraints file. Please go ahead and watch that episode. That's also in the playlist, and I'll also provide the link in the description. So here it is the design constraints of this particular test case. They have been defined as per the syntax. So let me close it. So I think roughly we have done the tour of this particular test case and all the necessary files. In the next section, we will be doing the hands-on practice. I have cleared the screen. So folks, let's start the OpenTimer. Our OpenTimer shell is ready. Let me do ILS. So let me load one by one the various files. Okay, I have loaded the cell lib. Then the Verilog file. Then the SPEF. Then the SDC file. So I have loaded the files. Now let me clear the screen. Files are loaded and I am running report timing now. So our timing engine has run, all the files have been parsed and internal calculations are done and our shell is ready to take our inputs. We are with the native gates and first let me print report area. Okay. Then let me do the report host negative slack and there is TNS here. Report TNS and you also report the leakage power. So with the native gate that is already in the design, we are having the area as 7.98. WNS is 8.56 with a minus sign. TNS is minus 33.1 and leakage power is 209. Now so I am using the repower gate, then the instance name. So here are all our instances. So here I am picking up the instance name and I am picking up the cell name. Now we have x2 in our native design. First I will change it to x1. We'll keep on doing this thing for all the instances. So here you can see there are 6 instances 0 to 5 and we have replaced all the gates with NAND to X1 which were originally NAND to X2. Let me run the report timing again. So I'll do the same things. Report area, report WNS, report TNS and report leakage power. So if you can compare, so earlier the area was 7.98. Now since we have downsized the gate, it has become 4.79. WNS has become minus 8.67, which was this 8.56. TNS was 33.1 and it is 33.7. Leakage power is 104, which was 209. You see there is a significant difference in the numbers. Basically, this gate sizing has impacted the delay and hence the slacks are different. I'm copying this command and here instead of x1 I am moving to x4. Okay, so this one and I'll keep on doing for rest of the things. Here I have done changes 6 instances from instance 0 to instance 5, which were there in the original .verilog file. All these 5 things, it was originally x2. I have downsized them to x1. I have upsized them to x4. Let me run the report timing again. You can see here the slack is also different here and here. In each case, this is different. And let me print the area. Area is now 14.4, which was earlier when we downsized 4.79, and the original ones was 7.98. So you can see the significant area increase. WNS, and let me first print and then I will compare. Let me compare the leakage power. Here comes 417, which when we downsized it was 104, and in original this was 209. So you can see the significant difference of the gate sizing, and that has actually happened inside this particular simulator. Okay, so this way we are checking the overall reporting of the gate sizing, and we can see that the TNS, when we have done the upsizing, right, it has become 32.1. When we downsized it, it was 33.7, and originally it is 33.1. So you can see that originally it was 33.1. If we upsize it, it has become 32.1. So these things are already impacted, and you can see the leakage power. Native one, the leakage power was 209, downscaling it was 104, and upscaling it is become 417, that is double of the native one. So folks, I think we are done with the resizing, and that's all for today.
Hey guys, welcome to the 15th episode of Static Timing Analysis. We are continuing hands-on practical using OpenTimer STA. Today we will dive into the PVT variation in gate sizing through OpenTimer STA. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis.
Hey guys, welcome back. We are continuing our hands-on practical using the OpenTimer STA. In today's episode, we will be exploring different PVT corners, and one thing I'd like to mention here that we do not randomly vary the PVT corner for the static timing analysis. We have some de facto rules that for the worst case, we choose a specific corner. From company to company, this may vary. In general, the thumb rule is for hold analysis with worst case, we use the fast corner, and for setup violation with the worst case analysis, we use the slow corner. We will begin our exercise with the hold analysis. First, here you can see 3 terminal is there, first, second and third. So I will be using the sizer test case, in which we have one particular NAND gate which has 3 versions, that is X2, X1 and X4. X1 is lesser area than X2 and X4 is higher area than X2. We'll start with X2, we'll downgrade to X1 and we upgrade to X4. This is what we have done in the last episode. Today what I will do, I will parallelly open the terminal. In each one I will open the OpenTimer, and there in each case, in one I will use X1, another one I will X2, third one I will use the X4. Now this thing has to be done very carefully, and I will be using the repower gate command I have used in last episode. Since we do the worst case hold analysis with the fast corner, as you can see here, we have several corners here: fast, slow, force flow, low temperature, typical. Last episode we have used the typical. Today for hold we will use the fast corner. Okay, then let me start the exercise. The first OpenTimer I have turned on. We are in the same directory in all of the terminals. You can see here, this is same. This is same, and here this is same. And also in the fourth one here, there we'll be using the Unix terminal, and here also we are in the same directory. So here, let me also launch OpenTimer. So folks, OpenTimer has been launched in the 3 terminals. Let me clear the terminal. Now we have OpenTimer shell here. Also OpenTimer shell here. And also OpenTimer shell here. So first I do the ls. I will get the physical files. This is same as in the Unix terminal. Now let me load the files. So these are our read commands. I will read one by one. First, cell lib. I'm loading the cell lib. Then the Verilog file. Then the SDC file. Then the SPEF file. Then the timer file. All our files are loaded, and what I will do, simply the report timing, just to run the timing engine. So the timing engine has run. It has just come out with one particular worst case reporting here. And let me source the same commands in other shell. So for terminal 2 we are done. Let's do the same thing in terminal 3. So folks, in the 3 terminals the OpenTimer engine has run, and in the 3 terminal it is ready. Now you can see here we are using the NAND to X2. So X2 instance we are using. What I will do is that, and let me clear the screen. The screen is clear now. So in the 3 terminals, the OpenTimer is ready, the timing engine has run, and we are ready to go. So what I will do, in the first terminal I will use the instance X1. Here the X2 will remain as is, and here I will do the X4. For that repower gate, I will have to end the gates. So here I am changing the gate to X1, which is have a lesser area. So here we have the X1 instantiated. We have repowered the gate, that is we have done the gate sizing from X2 to X1 in the first terminal. So we have the sequence X1, X2 and X4. So I'll do the same repower gate command here. However, this will be X4. So here 0 to 5, all the instances I have instantiated and repowered the gate. That means I have done the gate sizing from X2 to X4 in the third terminal. So let me clear the screen. Then the screen is clear, and here also let me. So I'll do the report timing. So the mean analysis is for the old violation. So I have done the mean analysis here. So I'll execute the same thing in all the 3 shells. So let me see whether we have the same path here in X7 to NX23. Here we have NX7 to NX23. As I vary it only in the screen, some data is varying. Apart from all these, gate instance is fixed and their rise fall direction is same. So you can see there is no change in this and this column. Okay, let me do the same thing here. Again here we have starting point NX7, then NX23. It is same as that. So if I vary here, I can see only X4 is varying here to X2 and then X1. Okay, this column and this column remain same, except that means the pin is same except the gate instance which is varied. So folks, now first of all, when we do it sequentially, for us it is difficult to take a diff in between the 2 things, and here we are taking the diff in between the 3 different cases. So that's why I have made the parallel terminals in which we can look into the detail minutely and compare what is happening where. As you know that the first corner is chosen for the worst case hold analysis, and one thing I would like to mention here, the fixing of these violations, either the setup or the hold. There are several methods to do that, and this tool which we are using have very much limited capability. Obviously, not only this tool, the industry standard ST tools, they also have limited capability. They can operate on the live shell or based on the whatever files we have fed, but beyond those files we can do some custom changes, maybe in the ECO, maybe in the Verilog description, maybe we are inserting some gate, adding some buffer, we are rerouting some path. All these options can come. So the STA tool is for analysis. Fixing of the violation has to be done as per the root cause analysis, and that has to be done by the designer judiciously, taking the decision whether it has to be done in the ECO step, or somewhere we have to do a rerouting, or somewhere we have to add some buffer or anything else. Gate sizing is a method that we can do easily inside the timing engine, and obviously that gate sizing, when we are getting all these gates, in this case we have very much limited amount of size. When we have the actual standard cell library, there we have a lot of variation, or even if you want, you can ask your vendor to provide various size of standard cells based on their height, that is track, like it may be 40, 60, 70, 90, 12T. These are track heights. So one single cell can have different track heights, and as we go up in the track height, the cell size increases. This is how you can use in an actual case. When you are learning, take this as a learning purpose, and later on you can, when you are actually inside the industry, you will get a lot of flexibility to fix the violations. Now let us come back to our own exercise that we are doing. Here, first one we have X1. and the second one is x2. You can see the change here. First let us look in the change, and x4 is here. So our first goal of the exercise is done. We have done the gate sizing to the repower gate command, and now in each case we are doing the hold analysis by using the mean flag, and the worst case is dumped here. And in the three cases we can see the difference. Now if we have the x1, our slack is 8.605. I am ignoring the minus sign while I am talking, but you can see it in the screen. As we go to the x2, it becomes 8.492, and as we go here it becomes 8.282. So gradually, if you see that we move from x1 to x2 to x4, as we go higher in the size of the gate, what happens that this particular slack is the numerical value or the modulus value is reducing. That means we are proceeding towards the correction. Now this is not only the single correction. I already mentioned that there could be a different amount or different methods of fixing the ST violation. We are operating on the shell now, so whatever available in our shell I am showing you. But it is significantly, you can see that the slack has changed. Even you can see the change in this and this column, this delay and the time column. I have already explained first hands-on episode what are these columns and how to interpret them, or in the timing report. So there you can also go and see that particular episode. I'll provide the link in the description, or you can go to the playlist and find that particular video. Now here, this particular column and this particular column, you can see that in these two you will see the change. Not only here, you can see the changes here. The constant columns are this and this, except the instance, the pinner constant. So let me vary, and you can see the change in front of your eye. So it has changed. You can see that these and these columns is already changed. And again, when I go from here, you can see that it has also again changed. So the gate sizing is impacting on the final slack of this particular path. As we go higher in the size, it is reducing. Even there is a violation, the violation margin is reducing. So if we take some more measures, or if we had some bigger gate area, then this would have been reduced drastically, and this could be one of the method or one of the tools that we can use to fix the violation. So folks, here we are done with the particular analysis, and when you do something, it is whiz weak. That is, what you see is what you get, and here what you see is what you are actually getting. 8.605, then it goes down to 8.492, and then 8.282. So in this case, for the same path, we have varied the gate size, and we have seen a huge reduction in the slack. So here it is. And then we have to do a path analysis and see if we insert a buffer somewhere or do some changes in the routing, then whether this can be fixed completely. That is a different scope of the fixing. We will stay limited in the OpenTimer shell, and here I am showing what things we can do here. We are done with the hold exercise. Let's move on to the setup analysis. Hey guys, welcome back. We will do the setup analysis now. Here you can see for the hold analysis, we have picked up the fast case for the worst case analysis. And now we will pick the slow corner for the setup worst case analysis. I have the same configuration of the terminals here. First terminal will be for X1, second will be for X2, and third one will be for X4. And the fourth terminal I will use for playing around inside the Unix shell. Here, let me start the OpenTimer in each of the cell. Remember that in this particular section, while doing the setup analysis, we will use the slow corner, and we will load this particular .lib file. So here, let me start the OpenTimer in the three different shells. So first, second and third, the OpenTimer is ready for all the cases. Let me clear the screen everywhere. So here 3 terminals are very much clear, and the 4th terminal is our Unix terminal. So I would like to start here. Let's start here. I'm doing a ls for the files, and there comes all of our read commands. So let me read there. .lib. Verilog is done. Next comes the SDC file. So SDC file is done. Then the SPEF. SPEF is done. Finally, the timing. The timing is also done. I have done the report timing and our shell is ready now. So let me do the same for all the 3 OpenTimer shell. First, in every case, OpenTimer terminal is ready, and let me clear the screens. And here let me grab the cells. These are our cells which are used in the design. By default, now all the cells have the instance NAND x2. 2 will remain same. Here I will use the repower gate. So here I'll downgrade it to x1. I'll do for all the instances. The middle one will stay with the original gate, that is x2, and the third one I'll change it to x4. So folks, we are done with the gate sizing using the repower gate command, and let me run again the report timing. So I have done the report timing here. Here also done. So let me clear the screen. Here the screen is clear. Clear. So in the 3 cases, the terminals are now ready with the setup analysis, and we are ready with the slow corner, the .lib file. Now, in this particular case, we do not have any kind of setup violation. So what I'll do, So I'll do the max. So you can see this has come. Although this is not a violation, this is a path where the setup is met. Okay. And I'll do the same thing here. I'll do the same thing here. So you can see that this particular has changed in between this and this and this and this. So what I'll do, I'll pick one particular case, and in that case I'll pick the particular last node, and I will apply the report AT and RAT command, which is usually used for the calculation of the slack. I am picking one particular node, that is the endpoint, this and this. I am picking up this particular node for the report AT RAT command. So let me clear the screen. So the node is NX22. I have opened this once again just to fill up the particular command. Pin is NX22, and here when we come, we use the rise one. We are picking the rise case. We are using the max analysis. So you can see we have picked the max analysis, we are picking the rise, and we are picking the NX22 node. Here I'll do the same. I've done the leveling here. First case, the gate is X1, this is gate X2, and this is gate X4. So X1 has the smallest area, X2 has higher area than X1, and X4 has higher area than X2. And we are using the slow corner, the .liberty, and for the setup analysis as we go for the max. Now what we have the AT, which we can see the RAT is same everywhere, because RAT is something that we set as a goal that has to be achieved, and what we achieve is contained in AT, and the difference of these two becomes the slack, and that is already discussed in the timing report episode where I have explained the slack equation. So here what we can see, that first case, for the smallest gate area, we have the AT is 2.77, and we have 2.99 for the X2, which has a much higher area, and for X4 we have AT 3.39, which is the highest of the three. So we can see for the setup analysis, for the lowest area we have the less arrival time. So in this case we have the AT 2.77 Here we have 82.99 and we have 3.39. I think it is now clear that what will happen in both the cases, that is both the worst cases for either the setup analysis or the hold analysis, and picking up the corresponding worst case library. We have seen in today's episode, in the two worst case scenario, if we do the gate sizing, what will be the impact on the slack, that is AT/RAT. So we are done here with the setup, and also we have come to the end of this episode.
Hey guys, welcome to the 16th episode of Static Timing Analysis. We are continuing hands-on practical using OpenTimer STA. Today, we will dive into the what if then analysis combined with gate sizing through OpenTimer STA. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis.
Hey guys, welcome back. Here in our computer screen. For today's episode, we will download one particular test case from OpenTimer website. So let's go there. So this is our OpenTimer website. The first result which has come. Let us go there. And let me scroll down to the examples. So in today's episode, we will be experimenting with this particular test case, timing driven optimization example plus incremental timing update. We will be downloading the optimizer test case. So here the path is ready. Let me copy it. Here we are ready with the terminal and we are in the OpenTimer test case directory. So let me type chclone. Here I pasted. Let the test case clone. Meanwhile, let me tell you why I have kept 3 terminals. In the first terminal, I will do up to a certain point and stop there. In terminal 2, I will proceed with some further step till the end. And as usual, the third terminal will be our Unix terminal where we will do our Unix stuffs. Our test case is copied. Let us go into the directory. So I will be doing the same in the next terminal. Three different terminals. We are in the same folder, that is OpenTimer test case /optimizer. So let me do a ls. So you can see there are several files are there. You are already familiar with these file extension and how we load these things. So for today's episode, I have made one shortcut, easy to use flowchart in text so that I can move faster instead of typing. So let me display it. This is steps.txt I have created. I'll come to it later. First, let me launch the OpenTimer shell. In the first one and in the second one. The OpenTimer shell has been launched in the first 2 terminals as I mentioned. Now, let me clear the screens. The screens are clear now. Now here there are 2 libraries are there in the test case and we are analyzing using both of them, and let's have a diff between them. So for that we are using the tkdiff command. Also you can take a gvimdiff command. Let the tkdiff open them. And as you can see that early is used for hold analysis and the late timing dim is used for setup analysis. So here is our TK-diff. It has opened. You can see here library early and library late. And if I scroll down, you can see the TK-diff has been highlighting the difference points. So early is here for the hold and late is for the setup. You can see the changes are there in the lookup table. You can see in the left and the right. So here you can see how these 1, 2, 3, these things are different. Obviously subsequent things are also different. Here you can scroll down and see the differences, and TK-diff is highlighting everything in detail. This way is only the LUT segments. The different LUT segments are different in between these two libs. So let me close it. You can browse and explore by your own. In case you don't have the TK-diff command, I'll provide the TK-diff installation command for Ubuntu in the description. So let me close it. So here let me quickly load the files. Today I'll take the shortcut here using my steps.txt. So here for the first terminal, we have made the terminal ready to continue our experiment. You can see here it is written added min cell lib as early and added max cell lib as late. So it has picked up two different libraries, min for the setup and the hold part, and the command that we have used, that read cell lib early, we give the early.lib and we give the late flag and then we give the late.lib. So let me do the same thing here in the second terminal. So folks, again the second terminal is ready also, and let me just clear the screen. Before clearing the screen, I would like to pin this particular output pin, that is the endpoint D17. You can remember this one because later we will be experimenting on this particular pin. Let me clear. So since both are same, let me do this max analysis in one shell, means analysis in the another shell. I was just speaking about this G17, right? G17 is coming here. Again, we have G17. Similarly, for this case, for the mean analysis here, also going through here this endpoint is different. So here we just flashed two different commands for mean and max analysis, and there are violations in both of them. That means we have the setup and hold both kind of violations in this particular test case. So let me clear the screen. So we are done up to this point. Now comes the part where I will do up to some point and then I will stop there, as I mentioned for terminal 1. So here what I will do, TNS, WNS, this one, report slack has been done, report 80, report R80, so we already done this report timing, so I am not going in this particular command. So I'll come to this command, not right now, later I will come. Here I will pause for this terminal 1 and I'll move on to terminal 2, where what I will do is I'll execute the next steps. So here what we can see in the Verilog file, if we open up, there is an instance 10, and for this case using the repower gate, which I have already explained in past episode. Here we will do the gate sizing here for this particular instance from the Verilog file, and let me do it. We have done. So terminal 1 remains unchanged, and in terminal 2 we are doing the changes. We will do some what if then steps. So these things I have explained to you when I was describing the OpenTimer manual, where I also explained the timing reports theoretically through the slide. In the same episode I have this what if then cases. I'll also provide the link in the description of that particular episode so that you can go and see in detail. So here we'll insert a buffer into the design, and its syntax is insert get. Then the next field, this is the command insert get. The next one is that get instance name, the instance name where we are inserting, and the library cell name. Library cell name means the name which is there in the, at least in the .lib file, here whatever files are there. This goes our first what if then command. So then we will insert a net to connect. It's a simple command. Execute it, and we are done the entering the buffer, and then what we have done that we have insert the git, and then we have insert the net. And from Verilog we can again see that there is a instance 3 for node get. So what we will do with that, we will disconnect the pin Zn, you can see this Zn, and rewire it with the new net that we have defined. So tau net 1 which we have defined. So we will rewire this particular net with this particular pin. So the syntax is, first thing we will disconnect and then we will connect using these two commands, and the syntax is disconnect pin, then the pin name, and connect pin, then pin name. So we first disconnect this particular pin and then we connect the pin. Fine. So these steps are done. Now let's connect the newly inserted buffer in between the tau-gate 1 and net underscore 14. So tau-net 1 you are already inserted the net, and tau-gate 1 and net underscore 14. So you can see net 14 here, net 14 is here, and tau-gate 1 here we have already used tau-gate 1. So let's connect the re-inserted buffer in between tau-gate 1 and net 14. For that we are using the connect pin command here. And the second connect pin command. So you can see that A and Z are the two ports of the buffer. You can easily identify here and here. These two are the two ports of the buffer. Now in the test case it is already there ready, the SPEF file. As we have done the changes in the net, right? Definitely the parasitics will change and the corresponding SPEF is also supplied in the test case. So we will take the difference of the before and the after SPEF using the tkdiff command. Let me do the tkdiff. You can see that in the DNet connection here net 14 is there, it's changed, tau-gate 1 has come here. So this way you can see multiple changes have been introduced in the original, the optimizer SPEF and the change SPEF. Here the name is change underscore 1.spef. So these two you can see here the difference, and if you keep on scrolling down you may see some more changes. If it is there, yeah, here it is. Here you can see the changes. And here is 2. So the change is very much evident. I'm not going in details. I've done a complete episode on SPEF. I'll provide the link in the description in case you want to see and explore by yourself. Obviously, you can go ahead and do that. I'll close this tkdiff window. And here. So we have done this up to this point, connecting this one. You can see. Now let us add this particular SPEF. We have done the change in the SPEF. Here what I will do, I'll do a report timing. You can see whatever changes we have done, it has incorporated the changes, it has loaded the SPEF and added the nets. Let me clear the screen. The first terminal was paused at this point. The second terminal we have moved up to a certain changes. Now let me print out these things in terminal 2. You can see now the result has come. So here, so you cannot see any particular changes using this particular command. We'll move on to the next step. We'll use the dump slack command in both of them. Okay, here and here. What I'll do, copy the output up to this point and paste the entire thing here in the slack d4.txt. Come to terminal 2 here. I copy the entire thing. And I paste in the another file that is named slack after.txt. I save the file. Now let me take a tkdiff in between the two. So folks, when we finally use the dump slack command, we can see the significant difference. You can see the before.txt is in the left side and the after.txt in the right side. So this is from the left side pane and this is from the right side pane. You can see there has been a lot of change here in these columns: early rise, early fall, late rise, late fall, early rise, early fall, late rise, late fall. So all these columns you already know. You can see there is a significant change in the overall slack report, which has got impacted because we have done, these are end slacks. So whatever you can see, these are end slack for all these pins. And since we have inserted a buffer and we have repowered a gate, it has impacted whatever nodes were around it. So this way, all these 4 branches of slacks are affected. You can see it has impacted this timing, what if then analysis and the repowered gate analysis we have packed together in this particular example. Folks, we have come to the end of this episode. I'll close it. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section below. And bye for today.